So welcome to the NPTEL MOOC on the design and analysis of algorithms. So here are some of the things that we will be looking at in this course. When we study algorithms, the first thing that we need to convince ourselves is that the algorithm is correct, that it's doing the job that we expect it to do. So we will look at strategies for proving the correctness of algorithms. The other important aspect of algorithms, of course, is efficiency. How much time does the algorithm take on inputs? Now, of course, we have to factor in the size of the input, and we need a notation or a way of comparing two different algorithms which operate on the same types of inputs and produce the same types of outputs. So this will be achieved through the concept called asymptotic complexity, which measures the running time of an algorithm as inputs grow larger and larger as a function of the inputs. And we will develop some notation, typically the big O notation, in order to smoothen out some idiosyncrasies of algorithms and group them into large chunks which are equivalent. An important part of problem solving in any domain, and in particular in algorithms, is the art of modeling the problem at a suitable level of detail. In most algorithms that we will see, we need to find a suitable mathematical model. One of these will be graphs. We need a way of representing the concepts of these models in our algorithm. For this, we need appropriate data structures. And of course, typically, in order to solve a problem, we need to break it down into manageable subproblems. So we will look at strategies to decompose problems into smaller problems and see how to put them together to solve the problem at hand. Over the course of time, many generic techniques have been developed to solve a large number of problems. And we will see examples of how these techniques can be applied to very standard problems that we come across repeatedly. Among the techniques are divide and conquer, where we break up the problem into individual components which do not overlap with each other, and then combine these solutions in order to get the solution for the overall problem. In some cases, we can identify a strategy which looks at the local state of the problem and chooses an optimal path and arrives at the final solution without having to look at all possibilities. These kind of greedy algorithms are rare. It's important to know how to prove such an algorithm is correct. But if a greedy algorithm does exist, it is typically much more efficient than other types of algorithms. When greedy doesn't work, we need a systematic way of exploring all the possibilities and choosing the best one. In this process, sometimes we have to discard overlapping problems and make sure that we don't wastefully recompute things. So this is covered by the concept of dynamic programming. Now, along with the theory in this course, we will have some programming assignments. So we do expect that all of you have some background in programming. Now this could be in C or C++ or Java. We are flexible about the language we use, but you should be able to write standard programs and implement some of the basic algorithms that we are using in our course. In order to do this, we will of course cover some new data structures in this course, but we do expect that in the language that you use, you are familiar with basic concepts like arrays and lists, and also things like stacks and queues which build upon these. Of course, when we come to stacks and queues, we will try to give some detail about how they are used. But we do expect that you have seen them before, so this is not the first time you're seeing these concepts. Here is a kind of approximate list of the topics we expect to cover in the course. So after looking at a few examples, we will start with asymptotic complexity, which is the way of measuring the efficiency of an algorithm and writing down this measure in a way that we can compare easily across algorithms. We will then move to the most basic problem that we have for arrays, which is to search an array for an element. And in the process, we will realize that it's important to be able to sort the array efficiently in order to arrange the elements in a way where we can search in an effective manner. So we will look at searching and sorting. So we will look at binary search, and we will look at different notions of sorting, some of which are more elementary and intuitive, like insertion sort and selection sort, but are not the best in terms of efficiency. And then we will look at more efficient algorithms like merge sort and quick sort, which are not obvious to begin with. Moving on from searching and sorting, we come to graphs and graph algorithms. So we will introduce graphs, we will see how we can use them to model certain types of problems. We need to know how to represent a graph. A graph is essentially a picture. So how do you translate this picture into something that an algorithm can manipulate? So that's representation. We will look at standard problems in graphs, reachability and connectedness. We will look at a special class of graphs called directed acyclic graphs, which are very useful for modeling certain kinds of problems. And then we will look at other canonical problems on graphs, including shortest paths and spanning trees. As we mentioned before, there are some basic algorithmic design techniques which apply across a class of problems. So we will look in particular at divide and conquer, greedy algorithms, and dynamic programming. Among the data structures that we will encounter in this course are priority queues, which are often implemented through heaps. We will look at binary search trees, which are efficient ways of maintaining information in a sorted order dynamically as information comes and goes. And we will look at a very useful data structure to maintain a partition of a set into a disjoint collection of subsets, the so-called union find algorithm. And finally, depending on how much time is left, we will look at some miscellaneous topics. It's important to realize that not every algorithm admits an efficient solution. So we will look at problems of intractability and some provably hard problems and some other problems for which the status is unknown. This is an 8-week course. The tentative schedule is as follows. In the first week, we will do some motivating examples, and we will look at some notations and work out some problems involving asymptotic complexity. In the second week, we will move on to searching and sorting. In the third week, we will introduce graphs and look at basic graph algorithms. We will continue with more graph algorithms and then in the process introduce the disjoint set data structure. We will then formally look at divide and conquer, which we will already have seen along the way, but we will look at it again. And then we will introduce heaps. In the sixth week, we will do search trees and some examples of greedy algorithms and their proofs. The seventh week will be devoted to dynamic programming. And in the last week, we will cover miscellaneous topics. Now you should remember that this is only an approximate schedule and there will be some variations, but roughly this is the sequence and the speed at which we plan to cover the material in the course. You can also see alongside the weeks, the calendar weeks that these correspond to. So the first week of the course is the current week, which is January 5th to 9th, and this course will go on to the last week of February. Now, as part of the evaluation for the course, there will be continuous evaluation. Every week there will be quizzes. There will also be programming assignments, roughly 6 programming assignments across the 8 weeks. After the course ends, there will be a certification exam. In order to get a certificate that you have successfully completed this course, you need to score 60% in the quizzes and in the certification exam. You need to submit at least 5 or 6 out of the 6 assignments, and at least 4 of them you must do something non-trivial. We will be following 2 main textbooks, although I will not use the textbooks directly in the course, but if you want to look up some material, you will find them in these 2 books. The first book is called Algorithm Design by John Kleinberg and Eva Tardosh. And the second book is just called Algorithms by Sanjoy Dasgupta, Christos Papadimitrou, and Umesh Vaisirani. The book by Kleinberg and Tardosh is more detailed, and it has a number of really nice examples to illustrate many of the concepts and quite detailed proofs. The book by Dasgupta, Papadimitrou, and Vaisirani is a slimmer book. It's more easy and accessible to read on your own. But on the other hand, it does leave a lot of details as exercises. So in order to really understand the material, you really need to spend more time working out the exercises and not just go by the material that's presented in the chapters. So before we start the formal part of the course, I would like to discuss a few examples to motivate the kind of problems we'll be looking at. So we start with the problem of air travel. So we have an airline, Barbet Airlines, which serves several cities in the country. And of course, although it serves several cities, it doesn't really connect all these cities directly. Only some of the cities are connected by direct flights. And for other pairs of cities, you have to take a hopping flight. You have to go via an intermediate city. So our first goal may be to compute every pair of cities which are actually connected by this network served by this airline. So how do we find out all pairs of cities A, B such that A and B are connected by a sequence of flights? So first we need to look at the network. So this is a typical way that we might find the network. For example, if we open the in-flight magazine of an airline, you find a route map and it's written like this. You have a physical map of the country and you have the cities which are served marked out. There are about 10 cities: Delhi, Varanasi, Ahmedabad down to Trivandrum in the south. And you have some arrows indicating the flights. Now in some of these flights are in one direction. You can go from Delhi to Varanasi, but you can't come back directly to Delhi. You must go to Ahmedabad and then come back. So this is quite common. If you look at airline schedules in airlines, you will find that you have these kind of triangular routes where you go around a triangle and you can't go back directly without hopping in between. Some pairs of important cities, like in this case Mumbai and Delhi, might be connected by flights in both directions, or even Mumbai and Calcutta. Okay, and so now we have these 10 cities and we want to know, is it really possible to go from, say, Varanasi to Trivandrum, or is it not possible? Is it possible to go from Hyderabad to Delhi, or it's not possible? So our first step is to model this problem in such a way that we retain the essential details which are relevant to solving the problem and get rid of all the unnecessary details. Okay, so this case, what we really would like to know is the structure of this network. Right? So the map itself is not relevant. We just need to know how many cities are there which are on the network and how are they connected by flights. So the picture below, which has these gray circles and arrows, represents this network. The cities are the gray circles and the flights are the arrows. The arrowheads indicate the direction. So if there's an arrowhead in one direction, it's a one-directional flight. If there's an arrowhead at both ends, it means it's a bi-directional flight. The actual names of the cities are not so relevant. We can call them 1, 2, 3, 4, 5 or A, B, C, D, E or whatever, okay, and solve the problem. So this kind of a picture is called a graph. We will study graphs more formally when we come to this module in our course, but a graph is just a picture of this kind. So it has some nodes, these dots, and edges. So now one nice thing about moving to this abstract level is that the actual picture can be distorted without changing its meaning. So we can move, for instance, if you look at this city here, right, we can move it to the right and it doesn't make any difference in terms of solving the problem. Or we could simplify the picture by moving, for instance, this edge outside, right, so that we get no crossing edges. And this is again the same picture, though it looks quite different from the picture that we started with. This is again the same network. Now in some situations it is useful to realize that the graph that we have looks like this, that there are no crossing edges. Technically such a graph is called a planar graph. It can be drawn on a flat piece of paper without any edges crossing. For planar graphs, we might have better algorithms than for arbitrary graphs. Now what do you want to do with such a graph? Okay. So in this case, we want to compute what we call a path. That is a sequence of edges going from one city to another city, where of course the direction must be correct. So you can't go backwards across an edge which is flying from A to B. You cannot take the same flight from B to A unless there is another flight. So our first question is, how do we take this picture and put it into form that we can manipulate using a program or an algorithm? So we need a suitable data structure in order to represent this graph. Now, given the way we represent the graph, we need to manipulate it to answer the question at hand. In this case, connectivity. How do we go from A to B? Or can we go from A to B? Or which all cities B can I reach from A? So how do we design such a data structure, an algorithm, given the way we have represented the cities in this graph? Does it depend on the representation? Are there multiple representations, some of which give us more or less efficient algorithms? These are all questions that we need to answer before we can decide on whether we have got the best solution at hand. Now, in terms of efficiency, we have to look at what are the things that determine the complexity of the problem. It's fairly obvious in this particular case that if we have more cities, the problem is more complicated. So the number of cities, which we can call n, is certainly one parameter which determines how complicated the algorithm is going to be, or not how complicated the algorithm is going to be, or rather how long it is going to take to run. The other question which determines how complex the network is how many direct flights there are. Obviously, if there are fewer flights, there are fewer places which can be connected, and we have to explore fewer possibilities. So from this, it follows that computing the paths depends on both n and f. So we will not have an algorithm which will always take, say, 20 steps. It will have to depend on some number of steps depending on n and f. Now, what is this dependency? How does it grow? If n doubles, does our algorithm take 2 times more time? Does it take 4 times more time? Okay, if n goes by a factor of 10, does it take 10 times more or 100 times more time? The other question related to this is, given this dependency on n and f, what realistic size of networks can we handle? Okay, if the airline grows to 20 flights, will we still be able to give our answer in a reasonable time? Remember that this kind of an answer is typically required when somebody is making an online booking or something and you want to reply in a few seconds, right? It's not enough to come back after an hour and say, yes, there is a flight from Trivandrum to Calcutta. So what is the limit of our efficiency? Can we scale this algorithm to cover airlines, multiple airlines? So we have a website which actually says across all airlines I can take you from place A to place B. That depends on how large a value of n and f we can handle. And then of course the problem that we have looked at is a very simple problem. Can I get from A to B? But very often it's not good enough to get from A to B. You want to get from A to B within some reasonable time frame. For instance, it's not usually acceptable to break journey overnight on air travel. Okay? At the same time, you also don't want to spend more than a certain amount of time waiting in between flights. So there are only some connections, although they may be, theoretically there may be connections, only some of them may actually be feasible. So now our problem becomes a little more constrained. So we don't just want to look at connected paths from A to B, but connected paths A to B which meet some additional constraints in terms of timing and other things. Okay? So can we solve this problem with the same approach that we solve the simpler problem? Or do we need to take a radically different approach? Or do we need more information in order to decide how to solve the problem? Suppose, as we would expect, each sector on this thing has a cost. As a passenger, the cost would be the price of the ticket. So if you are trying to compute the best way to go from A to B, your motivation might be to choose the cheapest route in terms of the ticket cost. Of course, cost is not only money, cost could be time as well. You might also want the quickest route from A to B, the one which involves the least waiting. So it depends on what your priority is. Are you urgently required somewhere, in which case you don't mind paying more? Or are you going on a vacation with the family, in which case you have a relaxed time schedule, but you want to make sure you get value for money? From the airline's point of view, there may be other questions. Periodically, aircraft have to be brought down for a day for maintenance. Now, you don't want to have so many aircraft that you keep all the routes flying and wastefully keep planes unused. At the same time, if you keep too few planes, then when you bring an aircraft down for maintenance, you have to sacrifice some routes. Now, which routes should you sacrifice so that you ensure that the connectivity of the network remains the same? If you could earlier go from Trivandrum to Calcutta during a maintenance shutdown, you should still be able to go from Trivandrum to Calcutta, maybe by a different route. So this is a problem to be addressed by the airline staff, whereas the cheapest route might be a problem to be addressed by the customers. So there are very many different kinds of questions you can ask about this basic this air network that we have described using a graph. And we will see answers to some of these problems in this course. So our first example was to do with airlines and scheduling in the network and using a graph. Now let's look at a different problem. So suppose we have a photocopying shop, Campus Xerox, inside a university campus. The deadline for projects is approaching and a bunch of students want their projects copied urgently. So they all go and submit their reports to the photocopying shop and say we want so many copies made within such a time. So now the question for the shop is how best to schedule these jobs. Now there are many different ways in which this problem can be phrased, so let's look at one of them. Right? So suppose these students have submitted their jobs and this shop, Campus Xerox, is competing against some rivals. So it's offering a special deal. Okay? So it says that it will give each customer a promised delivery time. And if it doesn't meet the schedule, like a pizza shop, it'll give a discount, right? So I'll promise you a report within 6 hours, and if you don't get it within 6 hours, then you pay less. Now, in this time frame, there are of course some bigger jobs and some smaller jobs. So some photocopying jobs will be faster to finish, some will take longer. But at the same time, they all have to run on the same machines that the Xerox shop has. So now you can reorder things. So you could take something which came later and put it earlier on the machine and hope to finish it within its deadline, and therefore not have to give a discount, and take something which is going to take longer and postpone it, saying anyway you're not going to meet the deadline, and give up the discount on that job. Right? So the problem that the Xerox shop has is how to do this schedule. Right? So there is always in the background what is called a brute force approach. You can say, okay, now I have to allocate these photocopying jobs to the machines in some order. So let me try every possible order and choose the one which gives me the best return. Now the problem with this is that it will take a very large amount of time to do this because the number of possibilities is exponential. Even if we have just 30 requests pending, it will take several hours to find an optimal schedule, and in those several hours you might as well have gone ahead and done some work so that you got the jobs done, and perhaps not optimally, at least got some money for it. So here is where we come to the idea of decomposition. Right? So can we solve this problem by reducing it to a simpler problem? Okay? So supposing we fix one job to run first. If we fix this job to run first, we are left with the remaining jobs. Now the remaining jobs are smaller in number. So if there was a way to optimally solve for n-1 jobs, then we can pick each of the jobs to be the first job, and for each of them determine how much time it takes efficiently, if we can, to do the remaining n-1 and choose the best one. So this would give us a kind of recursive solution. Pick one and solve the rest, and then add the time for this one. Another option is to just come up with a strategy. Looking at all the jobs which are yet to be done, we find some criterion by which we choose one to do next. Now, we could have different criteria for this. For instance, we could choose the one to do next which has the least number of pages, that will take the shortest time to process. Or we could take the one to do next which is closest to its deadline, that is the one for which we are most likely to miss finishing it in time and having to give a discount. So for each of these, we could have a strategy which would tell us which job to do next without looking at all the possibilities of doing the other jobs. But then we have to justify that the strategy that we have chosen is actually optimal. Is it better to choose shortest processing time? Is it shorter to choose the earliest deadline? Or is there yet another criterion? And how do these criteria justify the choice? Will I always get the best possible return on my machines by choosing this strategy? Now, as we saw with the airline network problem, the basic problem has many different variations which are possible. For instance, if we assume that the shop has many photocopiers, it is reasonable to assume that some are new and some are old. So the ones that are new may work faster than the ones that are old. Therefore, the time that it takes to finish a job depends on which machine we put the job on. So if we have this additional complication, does the strategy that we chose for the type where all machines are uniform still hold, or do we have to look at a different strategy? The other factor is, of course, that the cost of doing something varies across machines. Right? So if we use a machine, we use some resources. We use some ink, we use paper, we use electricity, and this cost may vary from one machine to another. So now the question becomes related to the first question, the previous question, which is that now if I split my job across machines, it might not only take more or less time, it also may cost the shop more or less. So the actual revenue that the shop realizes may be more or less depending on which machine it chooses. The other thing that you might want to keep in mind is that a machine cannot run indefinitely without having to be stopped for some time for maybe some maintenance, for loading paper, for something. So you can't realistically assume that every machine is continuously available. Now, under all these situations, is there still a valid greedy strategy, or do we have to do something else? Right? So you see the general idea. The general idea is that there is a basic problem with some constraints which you want to solve. But that problem can be amplified or made more realistic by adding several new features. And each time you add a new feature, you have to see whether the solution that you have for the simpler problem still works, or whether the new feature demands a radically new approach. And if so, how you should get that. So for our final example, before we really get into the course, let's look at a problem involving documents. So we have two documents, and our goal is to find out how similar they are. Right? So are these two documents really variations of the same thing? Now there may be many different scenarios where this problem is interesting. So one question may be for plagiarism detection. So it could be that somebody has posted an article in a newspaper or on a website, and you believe that this author has not really written the article themselves, but they have copied this article from somewhere else. Or if you are a teacher in a course, you might be worried that two students have submitted the same assignment, or one student has copied his assignment from some source on the internet. Right? So by looking at how similar, if you can measure how similar two documents are, you can try to quantify this notion that somebody has copied from somebody else. Now, it may not always have a negative connotation like this. It might also be to look at some kind of things when some people are writing code, typically if you're writing programs for some application, over a period of time, documents evolve. In this sense, the program evolves, right? So people add features. Now you might want to look at two different pieces of code and try to figure out what are the changes that have happened, how similar they are, how different they are, what are the actual changes that have happened. Another place where there is a positive notion towards document similarity is to look for web search. Right? If you ask a question to a search engine and it reports results, typically it tries to group together results which are similar because they are not really different answers. Now, if there are 10 different copies or similar copies of a document saying more or less the same thing, and these show up as your first 10 search results, then another document which will be highly relevant and quite different from these will now be lost to you because it will be off the first page of searches. So it is useful to be able to group together the results of a search query by similarity so that the user is actually presented with an effective choice between different answers to the search query and not just a large number of variations of the same answer. So if this is our motivation, we need a way of comparing documents. What is a good measure of similarity of documents? Now there are many different notions that people have come up with. Obviously it has to do something to do with the order of the words and the choice of letters and so on. But one way of quantifying the distance between two documents is to use what is called the edit distance. Namely, how many changes do you have to make to transform one document into another document? Right? And by edit, we mean supposing you actually loaded the document in a text editor or a word processor. Okay, what would be the kind of things that you could do? Well, we could limit, because you could of course block out and delete the entire document and then cut and paste another document and say I did it in 2 steps, but this would be kind of cheating. So we have to limit what operations you do so that we have a uniform way of counting this. So we could say that edit involves how many characters you change. Right? So each step of editing will either add or remove a letter, and perhaps we can allow you to replace one letter by another letter and call that one change. Okay? So now we want to count these as our basic steps, adding or removing a letter or replacing one letter by another, and find out how many steps it takes to edit one document to make it into another document. So the minimum number of edit operations will then determine the distance. Now the question that we have as an algorithm problem is, how do you compute this minimum distance? Right? How do you decide what is the best way to edit one document and make it another document? Of course, there is always a trivial solution like that block cut and block paste. You can just delete all the letters and then type in the new document. So there is a brute force way of doing it, but this is not likely to be the best possible way. Right? So you can also try out all possible delete and insert sequences and see which among them gives you the best solution. But all of these are very inefficient kind of solutions. So again, we can go to this question of decomposing the problem. Right? So supposing our first goal is to just make the first character of the two documents the same. If they are already the same, we leave it and go on. If they are not the same, well, then we have two options, right? We can either transform the character, the first character, to be equal, or we can insert a character in one of the two documents, right? So supposing the first document starts with an X and the second document starts with a Z, either we can say we do one operation to make X into Z or Z into X, or we can insert an X before the Z or insert a Z before the X, right? Or you can delete the X, but then we don't necessarily get the same array. And then once we have done this, once we have made the first character the same, then we can recursively try to fix the rest of the document. So now one of the difficulties that we face when we do recursion in this manner is that the same subproblem becomes up for solution many times. So a typical example of this is the recursive solution to finding the nth Fibonacci number. So the Fibonacci numbers are defined, it's a very classical sequence. So the first two Fibonacci numbers are 1 and 1. After this, you get the next Fibonacci number by adding the previous two. So after 1 and 1, the next one is 2, which is 1 plus 1. The next one is just 3, which is 1 plus 2, and so on. 5 is 2 plus 3, and so on. So in general, the recursive relationship is given by the fact that Fn is the sum of the previous two numbers, n minus 1, n minus 2. And then you have, as a base case, that the first two numbers, f1 and f2, for which n minus 1 or n minus 2 may not be defined, for these two numbers, the value is 1. Now the problem is that when you apply this recurrence directly, so if you try to compute the 7th Fibonacci number, for example, it will say, okay, for this I need to compute f6 plus f5. But if I then recursively apply this for f6 and f5, we find things like f4 coming up twice, right? So we have an f4 which comes here and an f4 which comes here, because when I do f5, I need to apply this recurrence. When I do f6, I need to apply this recurrence. So if I naively do it, I compute f4 twice, and in fact, when I compute this f5, I actually get another f4. Okay, so I'm computing f4 a number of times, f3 a number of times, and so on. So this is really an inefficient way to calculate it. Whereas if I just do it, for instance, here, I get 1, 1, 2, 3, 5, 8, 13, 21, and I find that the 7th Fibonacci number is actually in the sequence is 30, right? So there is intuitively a very fast way to do this. The recurrence is respected, but if I do it recursively, I end up solving a lot of problems again and again. So how do we get around it? And this is what we call dynamic programming. So dynamic programming says, do not compute the same subproblem twice. Okay? Whenever we solve a problem, if we have found f of 4 before, just look it up, store it somewhere, look it up, and make sure that you don't do f4 again and again. So this is one of the techniques that we have seen in the beginning that we are going to do in this course, and it's important that when we break up subproblems, problem into subproblems, it's not always the case that these subproblems can be solved efficiently unless we look slightly more deeply into the structure of subproblems and make sure we solve them in an effective sequence. Now, as usual, this problem of the difference or similarity between two documents can be at many different levels. So we are focused on the words, the actual text, okay? But if we don't really look at the sequence of words, okay, we just want the set of words, then they might be far apart in terms of edit distance because we need to rearrange the words. But the content, if we just measure in terms of what types of words are there, this might give us an accurate understanding of the meaning of the document. So if you actually search for a document in a typical search engine, you will often find that the words that you ask for may not occur together or may not occur in the sequence that you mentioned them. It will just find documents which have that collection of words. Okay? So this is very useful for web search. Okay? And the other thing that you might want to do is measure similarity of words in terms of meaning. So if you search for a document which contains the word car and there is another document which contains the word automobile, it might be a good idea for the search engine to report the documents containing automobile because automobile and car are essentially the same thing. Okay? So like the other examples we have seen before, there can be variations on the problem, and the solution that you have for the original problem may or may not be valid for these variations. So there is always a whole space of new and interesting problems to solve in all these things. So this course is called Design and Analysis of Algorithms. So design is something that is easier to understand. We have a problem, we want to find an algorithm, so we are going to design an algorithm. But what exactly does analysis mean? So analysis means trying to estimate how efficient an algorithm is. Now there are two fundamental parameters that are associated with this. One is time. How long does the algorithm actually take to execute on a given piece of hardware? Remember, an algorithm will be executed as a program, so we'll have to write it in some programming language and then run it on some particular machine. And when it runs, we have all sorts of intermediate variables that we need to keep track of in order to compute the answer. So how much space does it take? How much memory does it require? Now, we will argue that in this course at least, we will focus on time rather than space. One reason for this is that time is a rather more limiting parameter in terms of the hardware. It's not easy to take a computer and change its speed. So if we are running algorithms on a particular platform, then we are more or less stuck with the performance that that platform can give us in terms of speed. Memory, on the other hand, is something which is relatively more flexible. We can add a memory card and increase the memory. And so, in a sense, space is a more flexible requirement. And so, we can think about it that way. But essentially, for this course, we will be focusing on time more than space. So, if we are looking at time, we have to ask how we measure the running time. So of course we could run our program on a given computer and report the answer in seconds or in milliseconds. But the problem with this is that the running time of an algorithm measured in terms of a particular piece of hardware will of course not be a robust measure. If we run it on a different computer or if we use a different programming language, we might find that the same algorithm takes different amount of time. More importantly, if we are trying to compare two different algorithms, then if we run one algorithm on one computer and the other on another computer, we might get a misleading comparison. So instead of looking at the concrete running time in terms of some units of time, it's better to do it in terms of some abstract units of how many steps the algorithm takes. So this means that we have to decide what a notion of a step is. So a step is some kind of a basic operation, a simple one-step operation that our algorithm performs. And the notion of a step, of course, depends on what kind of language we are using. If we are looking at a very low level, at an assembly language kind of thing, then steps involve moving data from the main memory to a register, moving it back, doing some arithmetic operation within the CPU, and so on. But typically, we look at algorithms and we design them and we implement them at a higher level. We use programming languages such as C, C++, or Java, where we have variables, we assign values to variables, we compute expressions and so on. So for the most part, we will look at basic operations as what we would consider single statements or steps in a high level language. So this could be an operation such as assigning a value x equal to y plus 1 or doing a comparison. If a less than b, then do. So checking whether a is less than b is one step for us. Now we could look at slightly more elaborate notions of steps. For example, we might assume that we have a primitive operation to actually exchange the values into variables, though we know that to implement this we actually have to go via a third temporary variable. What we will see is that we will come up with a notion which is robust so that the actual notion of a basic operation is not so relevant because we will be able to scale it up and down according to what notion we choose to focus on. The other important thing to realize, of course, is that the algorithm will take a different amount of time depending on the size of the problem that it is presented with. It's quite natural and obvious that if we are trying to sort an array, it will take longer to sort a large array than it will to sort a short array. So we would like to represent the efficiency of an algorithm as a function of its input size. So if the input is of some size n, then it will take time t of n, where t will be a function depending on the input n. But even this is not immediately an obvious definition because not all inputs of size n are going to take the same amount of time. Some inputs will take less time, some inputs will take more time. So what do we take? Right? So it will turn out that the notion that we will typically look at is to look at all the inputs of size n and look at the worst possible one, the one that takes the longest time. Right? So this is called a worst case estimate. It's a pessimistic estimate, but we will justify it as we go along. But this is what we mean now. When we are looking at the time efficiency of an algorithm, What we mean is, what is the worst possible time it will take on inputs of size n, and express this as a function of n. So before we formalize this, let's just look at a couple of examples and get a feel for what efficiency means in terms of practical running time on the kinds of computers that we have available to us. So let us start with sorting, which is a very basic step in many algorithms. So we have an array with n elements, and we would like to arrange these elements, say in ascending or descending order, for further processing. Now, a naive sorting algorithm would compare every pair of elements, more or less, and try to determine how to reorder them. This would take time proportional to n square, because we are comparing all pairs of elements. On the other hand, we will see soon in this course that there are much cleverer sorting algorithms which work in time proportional to n log n. So we can go from a naive algorithm which takes time n square to a better algorithm which takes time n log n. So what we have really done is we have taken a factor of n and replaced it by a factor of log n. So this seems a relatively minor change. So can we see what the effect of this change is? So one way to look at this is to actually look at concrete running times. We said that we will not look at running times as measuring the efficiency of the algorithm, but of course the efficiency of the algorithm does have an impact on how long the program will take to execute, and therefore on how usable the program is from our practical perspective. So if you take a typical CPU that we find on a desktop or a laptop, which we have these days, it can process up to about 10 to the 8 operations. These are these basic operations in a high-level language like an assignment or checking whether one value is less than another value. We can say that it can do about 10 to the 8 operations. Now this is an approximate number, but we need to get some handle on a number so that we can do some quantitative comparisons of these algorithms. So it's a useful number to have for approximate calculations. Now one thing to remember is that this number is not changing nowadays. We used to have a situation where CPUs were speeding up every 1.5 years, but now we have kind of reached the physical limits of current technology. So CPUs are not speeding up. We are using different types of technologies to get around this, parallelizing, multi-core and so on. But essentially the sequential speed of a CPU is stuck at about 10 to the 8 operations per second. So now when we take a small input, supposing we are just trying to rearrange our contact list on our mobile phone, we might have a few hundred contacts, maybe 1,000 contacts, maybe even a few thousand contacts. If we try to sort our contact list, say by name, it really would not make much difference to us whether we use an n square or an n log n algorithm. Both of them will work in a fraction of a second, and before we know it, we will have the answer. But if we go to more non-trivial sizes, then the difference becomes rather stark. So consider the problem of compiling a sorted list of all the mobile subscribers across the country. It so turns out that India has about 1 billion, that is 10 to the 9 mobile subscribers. This includes data cards, phones, various things, but these are all people who are registered with some telecom operator and own a SIM card. Okay, so this is the number of SIM cards which are in active use in India today. So suppose we want to compile a list of all owners of SIM cards in India in some sorted fashion. Since we have 10 to the 9 subscribers, if we run an n square algorithm, this will take 10 to the 18 operations, because 10 to the 9 square is 10 to the 18. Now 10 to the 18 operations per second, since we can do only 10 to the 8 operations in 1 second, will take 10 to the 10 seconds. So how much is 10 to the 10 seconds? Well, it's about 2.8 million hours. Okay? It's about 115,000 days. And that's about 300 years. So you can imagine that if we really want to do this using an n square algorithm, it would really not be practical, because it would take more than our lifetime, more than several generations in fact, to compute this on the current hardware. On the other hand, if we were to move to the smarter n log n algorithm, which we claim we will find, then it turns out that sorting this large number of phone users takes only 3 times 10 to the 10, because the log to the base 2 of 10 to the 9 is 30. It's useful to remember that 2 to the 10 is 1000. So log to the base 2 of 1000 is 10. Now since logs add, 1000 times 1000 is 10 to the 6, right? So the log of 10 to the 6 is 20, log of 10 to the 9 is 30. So 30 into 10 to the 9, n log n is 3 times 10 to the 10. So this means that it will take about 300 seconds. So it will take about 5 minutes. Now 5 minutes is not a short time. You can go and have a tea and come back. But still, it will get done in a reasonably short amount of time so that we can then work with this useful information and go on. As opposed to 300 years, which is totally impractical. So let's look at another example. So supposing we are playing a video game, right? So this might be one of these action type games where there are objects moving around the screen and we have to, identify certain objects, shoot them down, capture them, whatever. So let's assume that as part of the game, in order to compute the score, it has to periodically find out the closest pair of objects on the screen. So now how do you find the closest pair of objects among the group of objects? Well, of course, you can take every pair of them, find the distance between each pair, and then take the smallest one. Right? So this will be an n-square algorithm. Right? So you compute the distance between any two objects, and then after doing this for every pair, you take the smallest one. Now it turns out that there is a clever algorithm, again, which takes time n log n. So what is this distinction between n square and n log n in this context? Now on a modern kind of gaming computer with a large display, it is not unreasonable to assume that we could have a resolution of say 2500 by 1500 pixels. If we have one of these reasonable size 20-inch monitors, we could easily get this kind of resolution. So we will have about 3.75 million points on the screen. Now we have some objects placed at some of these points. So let us assume that we have 5 lakh objects, 500,000 objects placed on the screen. So if we were to now compute the pair of objects among these 500,000 which are closest to each other, and we use the naive n-square algorithm, then you would expect to take 25 times 10 to the 10 steps, because that is 5 into 10 to the 5 whole square. 25 into 10 to the 10 is 2500 seconds, which is around 40 minutes. Now if you're playing a game, an action game in which reflexes determine your score, obviously each update cannot take 40 minutes. That would not be an effective game. On the other hand, you can easily check that if you do an n log n calculation for 5 into 10 to the 5, you'll take something like 10 to the 6 or 10 to the 7 seconds. So this will be a fraction of a second, 1/10 to 1/100th of a second, which is well below your human response time. So it will be essentially instantaneous. So we move from a game which is hopelessly slow to one in which you can really test your reflexes as a human being. Right? So we have seen in these two examples that there is a real huge practical gulf between even something as close to each other as n log n and n square. The size of the problems we can tackle for n square are much smaller than the size of the problems we can tackle for n log n. So when we look at these functions of n, okay, typically we will ignore constants. Now this will partly be justified later on by the fact that we are not fixing the basic operation, but essentially by ignoring constants we are looking at the overall function of the efficiency as a function of n as it increases, right? So this is what we call asymptotic complexity. As n gets large, how does the function behave? So for instance, supposing we have some function which grows like n square with a large coefficient and something which grows like n cubed with a coefficient of 1. Initially it will look like n square, say 5000 n square is much more than n cubed. But very rapidly, say at 5000, right? At 5000 we'll have both will be 5000 cubed. And beyond 5000, the function n cubed will grow faster than the function 5000 n square. Right? So there will be a point beyond which n cubed will overtake n square, and after that it will rapidly pull away. Okay? So this is what we would typically like to measure. We would like to look at the functions as functions of n without looking at the individual constants, and we will look at this a little more in detail. So since we are only interested in orders of magnitude, we can broadly classify functions in terms of what kind of functions they look like. Right? So we could have functions which are proportional to log n, functions which are proportional to n, n square, n cube, n to the k, which is, so any n to the fixed k is a polynomial. So we can call all these functions we will look at as polynomial. Right? So these are polynomial complexity. And then we could have something which is 2 to the n. If 2 to the n essentially comprises of looking at all possible subsets. So these are typically the brute force algorithms where we look at every possibility and then determine the answer. Right? So we have logarithmic, polynomial, and exponential functions. So what do these look like in terms of the numbers that we were talking about? So if you look at this chart, the left column varies the input size from 10 to the 1 to 10 to the 10. And then each column after that is a different type of complexity behavior, okay, as a function which ignores constants and only looks at the magnitude. So we have log n, then we have something which is polynomial n square, n cube. In between we have n log n, which we saw before, and then we have these two exponential functions which are 2 to the n and n factorial. Okay. So now in this we are trying to determine how efficiency determines practical usability. Okay. So now if you look at this, we said that we can do 10 to the 8 operations in 1 second. So maybe we are willing to work up to 10 seconds. So 10 to the 9 operations is about the limit of what we would consider efficient. 10 to the 10 operations would mean 100 seconds, which would mean 2 minutes, and maybe 2 minutes is too long. Okay. So now clearly if we are looking in a logarithmic scale, there's no problem. Up to 10 to the 10, right, we can do everything in about 33 steps, which will take very, very little time. Now in a linear scale, given that we are expecting 10 to the 9 as our limit, this becomes our limit, right? So we can draw a line here and say that below this red line, okay, things are impossibly slow. N log n is only slightly worse than n. So we can do inputs of size 10 to the 8 because n log n for 10 to the 8 is something proportional to 10 to the 9. Now there's this huge gulf that we saw. If we move from n log n to n square, then the feasibility limit is somewhere between 10 to the 4 and 10 to the 5. Okay, because the 10 to the 5 we've already reached a running time of 10 to the 10, which is beyond what we want. And now if we move to n cube, then the feasibility limit drops further, so we can't go beyond about an input size of 1000. Okay? So we can see that there's a drastic drop, and when we come to exponentials, really beyond some trivial things of size 10 or 20, we can't really do anything. Anything which is even 100 will be impossibly slow. Right? So we have these kind of this sharp dividing line of feasibility. Okay? And so we can see that it is important to get efficient algorithms, because if we have inefficient algorithms, even if we think that they work correctly, they will not be able to solve problems of any reasonable size. Right? And when we are looking at computational algorithms running on a PC, we would really expect our input sizes to be hundreds, thousands, and much more. Right? So when we are sorting things, we really do expect large volumes of data. If you want to look at voters lists or population data or data coming out of, say, a biology experiment about genetic material. Now these things are typically very large volumes of data. So it's really important to get the best possible algorithm to do these things. Otherwise, the problem at hand will not be effectively solvable. So we argued that we would like to measure efficiency of an algorithm in terms of basic operations, and we would like to compute the running time of an algorithm in terms of a function of its input size n. And we also saw that if you go from say n squared to n log n, then the size of inputs you can effectively handle becomes dramatically larger. Now today we will try to formalize some of these notions a little more clearly. So the first thing is the input size, right? So remember that the running time of an algorithm will necessarily depend on the size of the input. So we want to write the running time as some function t of n. And the main thing to remember is that not all inputs of size n will give the same running time. So there is going to be a notion of worst case estimate, which we will need to explain and justify. Before we do this, let's look at the notion of input size itself. How do we determine the input size for a given problem? So the input size more or less represents the amount of space it takes to write down the description of the problem, or in terms of the natural parameter of the problem. So for instance, when we are sorting arrays, what really matters is how many objects there are to sort, because we have to move them around and rearrange them. So the size of an array is quite a natural notion of input size for a sorting problem. On the other hand, if we are trying to do something like rearranging elements, or say we have some items which we need to load into a container and we are looking for an optimum subset to load in terms of weight or volume, then the number of objects would be a natural input parameter. We saw in one of the early lectures an example of air travel, where we constructed a graph of an airline route map where the nodes were the cities and the edges were the flights. And we argued that both the number of cities and the number of flights will have an impact on any analysis we need to do. So this is a general property of all graphs. If we have a graph, then both the number of nodes or vertices and the number of edges will determine the input size. Now there is an important class of problems where we have to be a little bit careful about how we talk about input size, and these are problems involving numbers. Suppose we were to write an algorithm for primality, checking whether a given number is prime. Now, how should we think of the size of the input? For instance, suppose we ask it to solve the question for say 5003, and then for 50,003, then 50,003 is roughly 10 times 5,003. So would we expect the time to grow proportional to 10? So should the magnitude of n actually be taken as the input size? Now, it's quite obvious when we do arithmetic by hand, the kind of arithmetic we do in school, that we don't go by magnitude, we go by the number of digits. When we do arithmetic such as addition with carry, we write down the numbers in columns and then we add them column by column. So the number of digits determines how many columns we have to add. The same is true with subtraction or addition or multiplication or long division and so on. Okay? So clearly it's the number of digits which matters, and the number of digits is actually the same as the log. If we have numbers written in base 10, then if we have a 6-digit number, its log is going to be 5 point something. Okay? When we get to logs 6, we will have a 7-digit number and so on. So the number of digits is directly proportional to the log, and so we can think of the log of the number as the input size. So this is a special case. So for arithmetic functions involving numbers, it is not the number itself which is the input size, but the size of the number as expressed in how many digits it takes us to write down the number. Now the other thing we mentioned is that we are going to ignore constants. We are going to look at these functions in terms of orders of magnitude. Does the function grow as n, n square, n cube, and so on? So one justification for this is because we are ignoring the notion of a basic operation, or rather we are being a bit vague about it. So let us look at an example. Right? So supposing we originally consider our basic operations to be assignments to variables or comparisons between variables. Now we decide that we will include swapping two values, exchanging the contents of x and y as a basic operation. Now, one of the first things we learn in programming is that in order to do this, we need to go via a temporary variable. So in order to exchange x and y in most programming languages, you have to first save x in a temporary variable, then copy y to x, and then restore y from the temporary variable. This takes 3 assignments. So if we take swap as a basic operation in our language, as compared to a calculation where we only look at assignments, we are going to collapse 3 assignments into one basic operation. So there is a factor of 3 difference between how we would account for the operations if we account for swap as a single operation. So in order to get away from worrying about these factors of 3 and 2 and so on, one important way to do this is to just ignore these constants when we are doing this calculation. So that's another motivation for only looking at orders of magnitude. So let us come back to this notion of worst case. So as we said, we are really looking at all inputs of size n, and among these inputs, which inputs drive the algorithm to take the maximum amount of time. So let's look for a simple algorithm here, which is looking for a value k in an unsorted array A. So in an unsorted array, we have no idea where the value k can be. So the only thing we can do is walk from beginning to end. Right? So we start by initializing this index I, which is a position to 0, and then we have a loop which says, so long as we have not found the array element, so long as ai is not k, we increment, right? We move to the next element. So this is the loop, and when we exit this loop, there are 1 or 2 possibilities. Either we have found the element, in which case I is less than n, or we have not found the element, in which case I has become n. So we check whether I is less than n. If I is less than n, then we have found it. Okay, and if I is bigger than n, that means it is not found. Okay, so this is a simple algorithm. So now in this algorithm, the bottleneck is this loop, right? So this can take up to n iterations. Now when will it take n iterations? That is the worst case, right? So the worst case in this particular algorithm is it must go till the end either if the last element is k, or more generally if there is no copy of k in the array, right? If there is no k in the array, we have to scan all the elements to determine that k does not exist, right? So this becomes our worst case input. So it's important to be able to look at an algorithm and try to reconstruct what input would drive it to take the maximum amount of time. So in this simple case, this simple example, we can see that a case which forces us to execute the entire loop can be generated by choosing a value of k which is not in the array A. Okay? And in this case, therefore, the worst case is proportional to the size of the array n. But the crucial thing to remember is that in order to determine which is the worst case input, we have to understand the algorithm and look at it. We can't just blindly determine what is the worst case without knowing the problem at hand. With different algorithms, we have to come up with different worst cases depending on what the algorithm is supposed to do and how the algorithm is constructed. Okay, so the worst case input is a function of the algorithm itself. Now we could look at a different measure, right? So supposing we don't look at the worst case, we say look at the average case. So look at all possible inputs and then try to see how much time it takes on each of these inputs and somehow average it out. Right? Now mathematically, in order to compute this kind of an average, we need to have a good way of estimating what are all the possible inputs to a problem. Okay? So although this sounds like a very attractive notion, in many problems it's very difficult. So supposing we are doing the airline route problem, right? How do we consider the space of all possible route maps, okay? And what is a typical route map and so on, right? So what are we going to average over? Are all these inputs equally likely? So we need to look at probabilities, and it's very often very difficult to estimate the probabilities of different types of inputs. So though it would make more sense from the point of view of the behavior of the algorithm in practical situations to look at the average case, that is, how does it behave over a space of inputs. In practice, it is very hard to do this because we cannot really quantify the space of possible inputs and assign them with meaningful probabilities. So to summarize, we look at worst case even though it could be unrealistic because the average case is hard, if not impossible, to compute. Okay? There are very limited situations where it is possible to do an average case analysis, but these are very, very rare. So the good thing about a worst case analysis is if we can prove a good upper bound, saying that even in the worst case this algorithm performs efficiently, then we have got a useful piece of information about the algorithm. That is, it always works well. On the other hand, if we find out that this algorithm has a bad worst case upper bound, we may have to look a little further. How rare is this worst case? Does it often arise in practice? What type of inputs are worst case? Are they inputs that we will typically see? Are there any simplifying assumptions that we can make which will rule out these worst cases and so on? Okay? So though worst case analysis is not a perfect way of doing it, it is something which is mathematically tractable. It is something that we can kind of hope to compute. So that is one good reason for doing it, so that we can actually come up with a quantitative estimate. And secondly, it does give us some useful information, even though in some situations it may not be the most realistic situation that we are likely to come across in practice. So we have said that we will measure the time efficiency of algorithms only up to an order of magnitude. So we will express the running time as a function t of n of the input size n, but we will ignore constants. So we will only say that t of n is proportional to n square or n log n or 2 to the n or something. So now the next step is to have an effective way of comparing these running times across algorithms. If I know the order of magnitude of one algorithm and the order of magnitude of another algorithm, how do I compare them? So the notation we need, or the concept we need, is that of an upper bound, which is given by the notation big O. So we say that a function g of n is an upper bound for another function t of n if beyond some point g of n dominates t of n. Now remember that g of n is going to be now a function which is an order of magnitude. So we have thrown away all the constant factors which may play a role in g of n. So we allow ourselves this constant. So we say that it's not g of n alone which dominates g of n, but g of n times some constant. So there is a fixed constant c, okay? And beyond some limit, so there is an initial portion where we don't care, okay? But beyond this limit, we have that t of n always lies below c times g of n. In this case, c times g of n is an upper bound for t of n, and we say that t of n is big O of g of n. So let's look at an example. So supposing we have this function t of n is 100n plus 5, then we claim that it is big O of n square. Now remember that n is supposed to be the input size. Okay? So the input size to a problem is always going to be at least 1. There's no problem that needs to be solved if your input is 0, and certainly we cannot have negative input. So we are always having in mind the situation that n is bigger than or equal to 1. So if we now start with our function 100n plus 5, then if we choose n to be bigger than 5, then n will be bigger than this value. So we can say 100n plus 5 is smaller than or equal to 100n plus n. And now we can collapse this as 101. Right? So 100n plus 5 is smaller than 101n provided n is bigger than or equal to 5. Now since n is at least 1, n square is bigger than n. So 101 times n is going to be smaller than 101 times n square. So by choosing n0 to be 5 and c to be 101, we have established that n square is an upper bound for 100n plus 5. So 100n plus 5 is big O of n square. Now we can do this using a slightly different calculation. So we can say that 100n plus 5 is smaller than 100n plus 5n for n bigger than 1, because n is at least 1. So 5 times n is going to be at least 5. So now if we collapse this, we get 105n. Now by the same logic, 105n is smaller than 105n square whenever n is bigger than 1. And so we have a new way of establishing the same fact, where we have chosen n0 equal to 1 and c equal to 105. Right? So n0 and c are not unique. Right? Depending on how we do the calculation, we might find different n0 and different c, but it doesn't matter how we choose them, so long as we can establish the fact that beyond a certain n0, there is a uniform constant c such that c times g of n dominates t of n. Now notice that the same calculation can give us a tighter upper bound. This is kind of a loose upper bound. We would expect that 100n is smaller than n square, but we can also say that this is big O of n. Why is that? Because if we just stop the calculation at this point, we do not come to this stage at all. We have established that 100n plus 5 is less than or equal to 101n. Therefore, for the same values, n0 equal to 5 and c equal to 101, this also tells us that 100n plus 5 is big O of n. Likewise, at this point, if we just ignore this step, then we say that 100n plus 5 is smaller than 105n. So for n0 equal to 1 and c equal to 105, we have established this one. Let's look at another example. Supposing we look at 100n square plus 20n plus 5. Now again, assuming that n is bigger than 1, we know that we can multiply by n and it will not get any smaller. So 20n will be dominated by 20n square, right? And 5 will be dominated by 5 times n, 5n square. So I now have 100n square plus 20n square plus 5n square is bigger than my original function, 100n square plus 20n plus 5. So I combine these, I get 125n square. And now all I have assumed is that n is bigger than or equal to 1. So for n0 equal to 1 and c equal to 125, we have that n square dominates 100n square plus 20n plus 1. So you can easily see that in general, if I have a n square plus bn plus c, right, this is going to be dominated by a plus b plus c times n square. Okay, so this is going to be less than this for all n greater than or equal to 1. Okay, so we can, generally speaking, take a function like this and ignore the lower terms because they are dominated by the higher term and just focus on the value with the highest exponent. So in this case, in this whole thing, n square is the biggest term, therefore this whole thing is going to be big O of n square. So this is a very typical shortcut that we can take. We can just take an expression, ignore the coefficients, pick the largest exponent and choose that to be the big O. Now we can also show that things are not big O. So for instance, it's intuitively clear that n cubed is bigger than n square. Now how do we formally show that n cubed is not big O of n square? Well, supposing it was, then there exists some n0 such that for all n bigger than equal to n0, n cube must be smaller than or equal to c times n square. Right? If this were big O of n square, this is what we must have. Now, supposing we choose n is equal to c, then we have on the left hand side c cube. On the right hand side we have c cube, and certainly we have that c cube less than equal to c cube. But if I go to c plus 1, I will have c plus 1 whole cube. On this side I'll have c times c plus 1 whole square. And now the problem is that this is bigger, because c plus 1 whole cube is bigger than c times c plus 1 whole square. And therefore, no matter what c we choose, if we go to n equal to c, we will find that the inequality that we want gets flipped around. Therefore, there is no c that we can choose to make n cubed smaller than c n square beyond a certain point, and therefore this is not big O. So our intuitive idea that n cube grows faster than n square can be formally proved using this definition. Now here is a useful fact about big O. If I have a function f1 which is big O of g1 and another function f2 which is big O of g2, then f1 plus f2 is actually dominated by the max of g1 and g2. You might think it is g1 plus g2. This is the obvious thing that comes to mind looking at this, that f1 plus f2 is smaller than g1 plus g2, but actually it is max. Okay? How do we prove this? Well, it's not very difficult. By definition, if f1 is big O of g1, there exists some n1 such that beyond n1, f1 is dominated by c1 of g1, c1 times g1. Similarly, if f2 is big O of g2, there is an n2 such that beyond n2, f2 is dominated by c2 times g2. Right? So now what we can do is we can choose n3 to be the maximum of n1 and n2, and we can choose c3 to be the maximum of c1 and c2. So now let's see what happens beyond n3. Beyond n3, both these inequalities are effective. So we have f1 plus f2 will be less than c1 times g1 plus c2 times g2. Right? Because this is beyond both n1 and n2, so both f1 is less than c1 g1 holds and f2 is less than c2 g2 holds. So I can add the two, and this is the first obvious thing that we said, is it g1 plus g2. But now we can be a little cleverer. We can say that, okay, we have c3, so c1 is smaller than c3 because this is the maximum, c2 is smaller than c3, so I can combine these and say that this is less than c3 g1 plus c3 g2. Now having combined these, I can of course push them together and say this is less than c3 times g1 plus g2. But g1 plus g2, if I take the maximum of those, then 2 times the maximum will be bigger than that. So I will get that this is less than c3 times 2 times the maximum of g1 and g2. Right? Now I can take this 2 out and say that therefore this is less than or equal to 2c3 times max of g1 g2. Right? So now if I take this as my n0 and this as my c, then I have established that for every n bigger than n0, namely max of n1 and n2, there is a constant which is 2 times the max of c1, c2, such that f1 plus f2 is dominated by c times max of g1, g2. Now why is this mathematical fact useful to us? Right? So very often when we are analyzing an algorithm, it will have different phases. It will do something in one part, then it will continue to do some other thing and so on. So we could have two phases, phase A which takes time big O of GA and phase B which takes time big O of GB. So now what is a good upper bound for the overall running time of the algorithm? So the instinctive thing would be to say GA plus GB. But what this result tells us is that it's not GA plus GB that is useful for the upper bound, but the maximum of GA and GB. Right? In other words, when we are analyzing an algorithm, it is enough to look at the bottlenecks. It goes through many steps. Look at the steps which take the maximum amount of time. Focus on those, and that will determine the overall running time of the algorithm. Right? So when we look at a function, an algorithm which has a loop, we typically look at the loop. How long does the loop take? We ignore maybe the initialization that takes place before the loop or some print statement that takes place after the loop, because that doesn't contribute as much to the complexity as the loop itself. Right? So when we have multiple phases, it is the most inefficient phase which dominates the overall behavior. And this is formalized by the result we just proved. Now there is a symmetric notion to an upper bound, namely a lower bound. Right? So just like we said that T of n is always lying below C of C times G of n, we might say that T of n always lies above C times G of n. And this is described using this notation omega. So this is just a symmetric definition. It just says that T of n is omega of G of n if for every n beyond n0, T of n lies above C times G of n for some fixed constant C. So here we have the same thing. We have an initial thing that we are not interested in because at this point nothing can be said. But beyond this n0, we have that T of n lies above. Okay, so T of n is always above C times G of n. So we earlier saw that n cubed is not big O of n square, but intuitively n cubed should be lying above n square. And this is certainly the case because n cubed is greater than equal to n square for every n bigger than equal to 1. Right? So at n equal to 1, both are 1, but n equal to 2, this will be 8, this will be 4, and so on. So given n0 equal to 0 or n0 equal to 1 and c equal to 1, we can establish this fact. Now, of course, when we are establishing an upper bound, we are usually talking about the algorithm we have. We are saying this algorithm has an upper bound of so much, and therefore I can definitely solve the problem within this much time. Now, when we are talking about lower bounds, it is not that useful to talk about a specific algorithm. It's not so useful to say that this algorithm takes at least so much time. What we would like to say is something like this problem takes at least so much time. No matter how you write the algorithm, it's going to take at least so much time. So typically what we would like to do to make a useful lower bound statement is to say that a problem takes a certain amount of time no matter how you try to solve it. So the problem has a lower bound rather than an algorithm has a lower bound. Now, as you might imagine, this is a fairly complex thing to say because what you have to be able to show is that no matter how clever you are, no matter how you design an algorithm, you cannot do better than a certain thing. This is much harder than saying I have a specific way of doing it and I'm analyzing how to do that. So establishing lower bounds is often very tricky. One of the areas where lower bounds have been established is sorting. Okay? So it can be shown that if you are relying on comparing values to sort them, then you must do at least n log n comparisons no matter how you actually do the sorting. So no matter how clever your sorting algorithm, it cannot be faster than n log n in terms of comparing elements to each other. But this is hard to do, remember, because you have to really show this independent of the algorithm. Now, we could have a nice situation where we have matching upper and lower bounds. So we say that T is theta of G of n if it is both big O of G of n and omega of G of n. In other words, with suitable constants, T of n can be dominated by G of n and it also lies above G of n for two different constants, of course. Okay? So what this really means that T of n and G of n are basically of the same order of magnitude. Okay? They are essentially the same function. Okay? And therefore, you have reached a kind of optimum value. So as an example, we can say, for instance, that n into n minus 1 by 2 is theta of n squared. In order to prove something like this, we have to show that there is an upper bound, that is, we can find a constant such that c times n squared dominates this, and a lower bound. There's another constant that says c times n squared is below this. So for the upper bound, we just expand out n into n minus 1 by 2, so we get n squared by 2 from the first term and n minus n by 2. Now, since it is an upper bound, n squared by 2 minus n by 2, if I ignore the n by 2, this is going to be less than n squared by 2. And therefore, now I have an upper bound saying that with a constant half, this is dominated by n squared for n bigger than 0. On the other hand, if I want to do a lower bound, okay, then I will say the same thing. I will expand out n into n minus 1 by 2. I will get the same expansion. And now I will want a lower bound, right? So now what I will do is I will make this even smaller. Okay, so I will say that I subtract not n by 2 but n by 2 times n by 2. Right? I subtract more. So this will be bigger than this because I'm subtracting more. So n squared by 2 minus n by 2 will be bigger than n squared by 2 minus n squared n by 2 into n by 2. But this is again n squared by 2. Sorry, this is n squared by 4. Right? So this is n squared by 4. So I have n squared by 2 minus n squared by 4. So this simplifies to n squared by 4. So in other words, I've shown that n into n minus 1 by 2 is bigger than or equal to n squared by 4. But now, in order to justify this, okay, to justify that n by 2 is this is increasing, n must be at least 2. Because if n is smaller than 2, this is a fraction, and so I'm actually reducing a small. So here I have a different n. I have n greater than or equal to 2. So I have established a lower bound which says that for n bigger than or equal to 2, n into n minus 1 by 2 is above 1/4 of n square. So therefore now if we choose our constant to be 2, for all values bigger than 2, I have that n into n minus 1 by 2 is less than half of n square, and n into n minus 2 is bigger than 1/4 of n square. So I have found this matching upper and lower bounds, which shows that n into n minus 1 by 2 is actually theta of n square. So to summarize, when we use big O, we have discovered an upper bound. So if we say f of n is big O of g of n, it means that g of n dominates f of n, so f of n is no bigger than g of n. And this is useful to describe the limit of the worst case running time. So we can say the worst case running time is upper bounded by g of n. On the other hand, if we use omega, we are saying that f of n is at least g of n. G of n is a lower bound for f of n. As we described, this is more useful for problems as a whole, sorting as a general problem, rather than for individual algorithms, because it tells us that no matter how you do something, you will have to spend at least that much time, but this is hard to establish. And if you have a situation where a lower bound has been established for a problem, and you find an algorithm which achieves the same bound as an upper bound, then you have found, in some sense, the best possible algorithm, because you can't do any better than g of n because we have a lower bound of g of n, and you have achieved g of n because you have shown your algorithm is big O of g of n. So theta is a way of demonstrating that you have found an algorithm which is asymptotically as efficient as possible. So for the last lecture in this unit, what we are going to do is actually look at some examples of algorithms and see how to compute their upper bounds. So we will look at two basic classes of algorithms in this unit, in this lecture. So we will look at some iterative examples and some recursive examples. So an iterative example will basically be something where there is a loop. And a recursive program, of course, will be something where you have to solve a smaller problem before you can solve the larger problem. So you have to recursively apply the same algorithm to a smaller input. So our first example is a very standard problem which you must have done in your basic programming course. Suppose we want to find the maximum element in an array A. So what we do is we initially assume that the maximum value is the first value, and then we scan the rest of the array, and wherever we see a value which is bigger than the current maximum value, maxval, we replace it. And at the end of the scan, we return the value of maxval that we have found, which should be the largest value that we saw in the entire array. Now remember that we said that if we have two phases, in this case we have one phase where we do an initialization, we have three phases actually, we do then a loop, and then we do a return. It is enough to look at the bottleneck phase. We said that if we have two parts, F1 and F2, then the order of magnitude of F1 plus F2 is the maximum of the order of magnitudes of F1 and F2. So in this case, it is clear that this loop is what is going to take the most amount of time. So it's enough to analyze the complexity of this loop. So now this loop takes exactly n-1 steps. Okay, so the worst case, any input is the worst case because we must go from beginning to end in order to find the maximum value. We cannot assume anything about where the maximum value lies. Now when we are scanning the loop, in every iteration we do at least one step. So this is a comparison, okay, one basic operation, and this may or may not happen. Okay, so the assignment happens if we find a new value ai which is bigger than maxval. But since we are ignoring constants, we can treat this as some C operations, some constant number of operations per iteration. So we have some C times n-1 basic operations. Okay? And if we ignore the C and we ignore this -1, overall this algorithm is linear. It takes order n time. So let's now move on to an example in which we have two nested loops. So supposing we are trying to find whether or not an array has all distinct values. That is, no two values in the array A are the same. So what we will do is, we will take this array A, right? And then we will compare every AI and every AJ. And if I ever find an AI equal to AJ, then I will return false. Right? If I find no such AI and AJ, then I will not return false, I will return true. Now the point is that in order to optimize this, if I am at position I, then I will only look at elements to its right. Right? So I will start with I plus 1 and go to n minus 1, and this will be my range for j. Right? So in order to not compare AI, AJ and then AJ, AI, just to avoid this duplicate thing, what we have written is for I equal to 0 to n minus 1. So as I look at each element, for j equal to I plus 1 to n minus 1. To its right, check if AI is equal to AJ. Right? So now if I look at the number of times this actually executes, then when I is equal to 0, okay, j varies from 1 to n minus 1, so there are n minus 1 steps. Right? When I is equal to 1, there are n minus 2 steps, and so on. So as I go down, when I is equal to n minus 1, there will be 1 step. Right? When I is equal to n minus 2, there will be 1 step. And when I is equal to n minus 1, the outer loop will terminate, but the inner loop won't run at all, because we will go from n to n minus 1. Right? So overall, what we are doing is, we are doing 0 plus 1 plus 2 plus n minus 2 plus n minus 1 steps. So this is a familiar summation, the summation of I is equal to 1 to n minus 1 of I. Right? And this, you should know, is n minus 1 into n by 2. This is a very familiar recurrence. And this we have already seen actually, this is O(n) square. Right? If you just ignore constants, you have an n square by 2 minus n by 2. O(n) square, actually we showed that it is theta n square, but for this moment we are only looking at upper bounds. So let's say that this algorithm is O(n) square. So it's not a trivial O(n) square, in the sense it's not two nested loops of equal size. It's not I equal to 0 to n, j equal to 0 to n. It's I equal to 0 to n minus 1 and j equal to I plus 1 to n minus 1. But still, the summation 1, 2, 3, 4 up to n is O(n) square. And this is something we will see often, so it's useful to remember this. So this is another example of a nested loop, and this is one which has 3 nested loops. Now here what we are trying to do is, we are trying to multiply 2 square matrices A and B. Right? So we have 2 matrices A and B, and we are trying to compute the product C. Now in this product C, okay, if I want the ijth entry, then what I have to do is, I have to look at row I in the first matrix, column J in the second matrix, and then I have to pairwise, I have to do the first entry here in this row times the first entry in that column, so I have to multiply those two, then I have to multiply the second entry, and so on, and then I have to multiply the last entry, and then I have to add that up. So that's what this program is saying. So this is for each row, for I equal to 0 to n minus 1, then for each column, for j equal to 0 to, so this is going through all possible entries Cij. Now it's saying that for this new entry, I start by assuming Cij is 0, and then I run through this row, k equal to 0 to n minus 1. I look at aik, that is the kth element in the row, bkj, the kth element in this column, multiply them and add it to Cij. Okay? So this is a loop, outer loop of size n, this is another outer loop, inner loop of size n, and the innermost loop of size n. So this is order n cubed. Right? So this is a natural example of an n cubed algorithm. So our final iterative example is one to find the number of bits in the binary representation of n. So this is just the same as dividing n by 2 until we reach 1 or 0. Right? So let's assume that n is a non-negative number, so n is 0 or 1. So we assume by saying that the number of bits is at least 1. Okay? And then so long as we have a number which is bigger than 1, we will add one more to the count, number of digits, and then this is a short form for integer division. Okay? So we will replace n by 2. So for instance, supposing we start with a number like 9, okay, then we will start with count is equal to 1, because that's how it says. Then while n is bigger than 2, I will divide by 2 and add 1 to the count. So I'll replace count, make it 2, and I'll make this 4. Then I will say that it's still greater than 1, so I'll make this 3, and I will make this 2, 4 by 2. Then I will say this is still bigger than 1, so I'll make this 1, and I'll make this 4. So now I have count equal to 4, I have n equal to 1, so this loop exits and I return count. So it says that it requires 4 bits to represent the number 9, which is correct because the number 9 in binary is 1, 0, 0, 1. Okay. So now what is the complexity of this loop? Well, how many times does this execute? Well, it will execute as many times as it takes for n to come down from its value to, so I want n by 2, n by 4, etc. to come down to 1. Okay, so how many times should I divide n by 2, okay, to reach 1? And this is the same as going backwards. How many times should I multiply 1 by 2 to reach n? Okay, so dividing n by 2 repeatedly reach 1 is the same as multiplying 1 by 2 repeatedly to reach n, and this is nothing but the definition of the law. Right? What power of 2 reaches n? So this iterative loop actually, though it doesn't decrement by 1, decrements by halving n each time, we can still calculate it explicitly as requiring log to the base 2 n steps. So we have seen iterative examples of linear time, quadratic time, cubic time, that is n squared, n cubed, and also a linear example with log n time. So now let's look at one recursive example to see how we would try to do this when we have a recursive solution. So we won't look at a formal algorithm, but rather an informal puzzle. So this is a well-known Towers of Hanoi. So in the Towers of Hanoi puzzle, we have, as we see in this picture here, we have 3 wooden pegs, which we will call for the moment A, B, and C. Right? So we have pegs A, B, and C. And our goal is to move these end disks from A to B. Right? So the thing that we are not allowed to do is to put a larger disk on a smaller disk. So if we take this small disk and move it here, okay, so we move the first disk here, then we must take the second disk and move it there, because we can't put the second disk on top of the first disk. Right? So the goal is to do this in an effective way. So the actual goal is to move everything from A to B, okay, and this is our intermediate thing, because as we saw, if we move the first disk from A to B, we are stuck. We can't move anything else onto B, so we must use C as a kind of transit peg or a temporary auxiliary peg in order to do this job. So if you haven't seen this problem before, you might want to think about it in your spare time, but this is a very classical puzzle and it has a very standard recursive solution. And the standard recursive solution is the following, that you first assume that you know how to solve the problem for n-1 disks. So at this moment, you want to move n disks from A to B. So what you do is you first move n-1 disks. So you have on A only the bottom disk left, and you have now B empty, and you have moved all the other n-1 disks to C. So there are now n-1 disks here. Right? So you have assumed that you can do this using B as my transit peg. So now I moved things from A to C. Now what I do is I move this disk here. So I now have this here and I no longer have anything here. So now I have one biggest disk on B, so I can put anything on it, and I have n-1 disks on C. So what I do is I apply the same algorithm for n-1 to move things from here to here using now A as my transit peg. Right? So this is a recursive way to solve the problem. You move n-1 disk from A to C, move the biggest disk from A to B, and then move n-1 disk back from C to B. So the question we want to ask ourselves is, how many times do we move disks in this procedure? So supposing we write m of n to indicate the number of moves we need to transfer n disks from one peg to another peg. Okay? So what we have seen is that in order to transfer n disks, we first transfer n-1 disks from A to C, then we transfer one disk from A to B, and then n-1 disks back from C to B. So it's m of n-1, this is to transfer n disks, plus 1 for that one disk, and then m of n-1. So this I can simplify as 2 times m of n-1 plus 1. Right? So m of n in general is 2 times m of n-1 plus 1. And if we have only one disk to transfer, then there's no problem. We can do it directly in one step. So m of 1, where n is equal to 1, is 1. So this kind of expression of describing mn recursively in terms of smaller values of capital M is called a recurrence. Right? So we have a recursive expression for mn. Now we have to solve this. So the way we are going to solve this is to use a notion of repeated substitution. We are going to repeatedly use the same rule to simplify this expression until we reach everything in terms of m1, and then we can plug in the value 1. Right? So we start by the basic expression. So m of n is 2 times mn minus 1 plus 1. Now what we do is we substitute for mn minus 1 the same expression in terms of n minus 2. So mn minus 1 by the same expression is 2 times mn minus 2 plus 1. Right? Because in general for any m we have mn is 2 times m of n minus 1 plus 1. Right? So this is a general expression. So we are taking this. So we do this and we simplify it. We get 2 times 2, so we get a 2 square coming from this mn minus 2, and then we take 2 times 1, that gives us this 2, right, plus 1. Right? So we have just rewritten this as 2 square m minus 2. Now again, if we take this expression 2 times mn minus 2, that becomes 2 times mn minus 3 plus 1, and then this 2 square plus 1 is this 2 square, remember, is 4. So this I get a 4 inside, and 2 square times 2 is 2 cubed. So I get 2 cubed mn minus 3 plus 2 square plus 2 plus 1. Now you can see that if I do this k times, I will have 2 to the k m of n minus k. Remember, everywhere I have this and I have this, it's the same number. And this is 1 plus 2 plus 4. It next time will be 1 plus 2 plus 4 plus 8. So this is actually 2 to the k minus 1. So this is nothing but 2 cubed minus 1. This is nothing but 2 squared minus 1. Okay. So in general, after k steps, I have this. Now when I do this n minus 1 times, then n minus n minus 1 is nothing but 1. Right? N minus n plus 1. So if I do this to n minus 1 times k is n minus 1. Okay. Then n minus k becomes 1. And this is n minus 1. So since n minus 1 is 1, I can just omit it from this thing. So I have 2 to the n minus 1 plus 2 to the n minus 1 minus 1. But this is nothing but 2 times 2 to the n minus 1, which is 2 to the n. Right? So I can combine these as 2 to the n. Okay? So therefore, this gives us, by this repeated expansion, substitution, whatever you would like to call it, we have that mn minus m of n is 2 to the n minus 1. In other words, it takes an exponential number of steps in order to solve this puzzle. Right? So there is a very famous story by Arthur C. Clarke which talks about this some temple where these pegs are there, and it has 64 such discs, and it says that the world will come to an end when the 64 discs are transferred. So you can think about how much time it will take to transfer 2 to the 64 discs in order to solve the puzzle with 64 discs. Remember, we said that 2 to the 30 is about 1 billion, right? So this is an enormous amount of time, so I don't think we really need to worry about this as a serious problem if that is indeed the case. So to summarize, we have looked at some examples just to illustrate the flavor of how we apply the concepts we have studied in terms of Vigo in an actual algorithm. How do we look at an algorithm and actually extract its complexity? So for an iterative program, basically you focus on the loops. Right? Because the loops are what take up the time, and you have sometimes to be a bit clever about trying to understand how many times a loop executes. For recursive programs, we saw only one example. We will see more as we go along, but the main idea is you express the time complexity of the program as a recurrence. You write t of n, the time taken for n steps, in terms of a smaller value which is obtained from the recursive call. So for the Hanoi case, we had n and n minus 1. Right? So in order to solve the problem for n disks, we needed to solve the problem twice for n minus 1 disks. We will of course find examples which don't fit any of these. It will not be a simple loop that we can calculate. Okay? And then we will have to be a little more careful about how we actually count the operations. So in a sense, actually estimating the efficiency of an algorithm is really like accounting. Right? So you are kind of keeping track of all the basic operations, and you have to do a good job of making sure that you do the to keep track of them in the best possible way so that you get an accurate picture of the answer. So in this unit, we are going to look at searching and sorting for a value in a list of values. So let's review how lists of values are actually stored in a computer. So there are two basic ways of storing a sequence, as you know, arrays and lists. Now, functionally they may look similar, but from a complexity theory point of view, from an efficiency point of view, how the data is organized makes a difference. So let's just review some basic ideas about arrays and lists. So an array, to begin with, is a single block of memory. So if you have an array, you should think of it as something which has consecutive elements storing the values in the array. So if we have an array A of size n, then A0 is immediately followed by A1 and so on until an minus 1. So the crucial fact now is that if I know where the array starts, then if I want to get to some value ai, then I just have to multiply by I the size of each unit of array to find out exactly where ai is. So this amounts to saying that we can access any value ai, any position I in the array in constant time, regardless of whether I is at the beginning or at the end, because we just have to compute the offset, right? So we have the starting position, and then given I, we can compute directly in one shot, just doing arithmetic with respect to the starting address, the position of ai. Now on the other hand, if I want to insert an element between ai and ai plus 1, this becomes a bit complicated. But because supposing I now want to push a value here, that means I have to take these values, right, and move them down. That means each of these values has to be shifted by 1. Therefore, the time taken to insert an element depends on the position, but in the worst case, I might have to shift all the elements by 1. So this could take time proportional to the size of the array. So this could be an order n of operations. The same way, contraction can require me to take an array, and then if I want to remove this element, then I have to shift all of these elements up by 1. Right? So if I want to expand or contract an array, it's an expensive operation, but I can access any given element in an array in a fixed cost time, which is independent of the position, and I can just treat it as like any other access, like accessing a variable x or y or anything else simple in my program. A list, on the other hand, is generally a flexible structure, and as elements are added, they get scattered around the memory with no fixed relationship to each other. So typically a list will have values in different parts of the memory, and the idea is that each value will point. So supposing this is the beginning of the list, right? Then this will point to the next element, this will point to the third element, this will point to the fourth element, and so on, right? So because of this linking structure, usually in most introductory data structures courses, lists are often referred to as linked lists. So a linked list is just a concrete way of implementing such a flexible structure. So now what this means is that if I want to find where, say, L2 is, so let's assume that this is L0, L1 and L2, okay, then I have no idea in general where L2 is located, but I know where L0 is located because my list name in my program L will point to L0. So I'll have to follow these arrows until I reach L2. Right? So in general, if I want to go to LAI, I have to start at A0, then follow my link to A1 and so on. So this will take me I steps. So therefore, the further down in a list I need to go, the longer it takes me. So accessing AI is proportional to I. So in general, if I have to access the ith element of a list, it's a linear time operation. On the other hand, inserting and deleting is comparatively easy. If I know where I am, supposing I want to insert something between L2 and L3, then what I would do is I would first construct a new node here, okay, and then I will do what I would call plumbing. So I will remove this link, and I would instead insert a link from L2 to the new node and from the new node to L3, and I know which links to add because this is a node I've just created, so I know its location, and L2 points to L3, so I can transfer that information to the new node so that these links can be established. Right? And a similar thing happens when I want to delete a node. If I want to delete this node, for example, right, then what I have to do is I just take this link and I bypass it and go directly here. Right? So by just shuffling these links around in a local sense, in a constant amount of time, you can insert or delete at any point in a list, but finding a position requires me to start at the beginning and go to the end, which takes linear time. So this distinction has an impact on what we can do. Suppose we want to take a sequence of values, right, and we want to take a value at position I and position j, and I want to exchange them. Right? So if I know the positions I and j, in an array I can easily get to ai and aj in constant time and exchange them. So this is exactly like swapping x and y. Okay, there's no difference between swapping x and y and swapping ai and aj. But if it is a list, then I have to walk down to find this, then I have to walk down to find that. So I have to find these two things and then I have to exchange. So it will take me linear time just to locate the positions to exchange. On the other hand, as we have already seen, if we wanted to delete an element from the middle of a list, or we want to insert an element into a list, this takes constant time, provided we are already at AI. So if we reach AI and we find at this position we want to do something, we can do that operation, insertion or deletion, in constant time. But at that position, if we want to insert a value or contract the array, then we have to shift a whole number of elements forwards or backwards, and this will take linear time. So sometimes this impacts what we can do, and algorithms that work well in one data structure will not work in the other, though they are abstractly representing the same thing, a sequence of values from 1 to n or 0 to n minus 1. As an example of this, we will see soon binary search. Binary search works on arrays but does not work on lists because it requires us to repeatedly probe the array at some index I in an efficient way. So let's look at the problem of searching for a value in an array. So in general, the search problem is to find whether a value k is present in a collection of values A. Now in our case, we will think of A as generally as a sequence of values. And moreover, we'll also assume that the sequence is something like integers, where we can talk of one value being less than another value. So the values can be ordered with respect to each other. So we already saw that we can keep such sequences in two different ways, as arrays and as lists. And depending on whether we keep it as arrays or lists, the way we can access the elements is different. So the first question we might ask is whether searching makes a difference in a list versus an array. And the second question we might ask is there some importance to how the values are arranged in the sequence? Does it help if they are in ascending or descending order? Or does it not matter? Is it equally the same to search for something in a randomly collected collection of values, randomly ordered collection of values, or when it is structured in some particular way? So in the unsorted case, we have no choice basically. We have a sequence A which runs from 0 to n minus 1. So we must look at all the values because we have no idea where k may be. So a systematic way to do it is to start with the position 0 and just scan all the way to n minus 1. So we have this loop here which scans, okay? And the scan either terminates when you reach the end without finding it, or when at some position I we find that ai is equal to k. And then depending on that, we either say that it is found, in which case we return the position, or we have reached I equal to n, which means we have gone beyond a n minus 1, and so we return minus 1, which is an invalid position to indicate that it's not found. So we saw before that the worst case actually happens when k is not an element of A. That k doesn't come in A, we have to scan A0 to an minus 1 in order to determine that k is not there, because we have no evidence in advance which position it's likely to be at. So this means that in the worst case, searching for an element in an unsorted array takes linear time. And of course, it doesn't matter now whether it's an array or a list, because in a list we could also in linear time start from the first element and follow the links all the way to the end. In an array, we start with A0 and go all the way to an minus 1. Both of them take linear time. On the other hand, if the sequence is sorted, and in particular if it is an array, we can be a little more intelligent. Right? So what we know is that the values are, say, in ascending order. So if we probe the value in the middle, okay, and check this, is this equal to k? Right? If the value that we have is equal to k, of course we have found it. If it is smaller than the value here, then we only need to search in this half. Okay? And if it is larger, then we need to search in this half. Now this is something that we intuitively do all the time. This is how we look for, say, words in a dictionary, or when we play 20 questions. Right? We try to ask questions about the age of a person, then we'll say, is this person less than 40, is this person greater than 65, and so on. Right? So this is something we know intuitively, but we can formalize it. Right? So we take the midpoint of the range we are searching for. If the midpoint is a value that we want, we have found it. Otherwise, depending on the value we are looking for and what the value is at the midpoint, we search either the bottom half or the top half. So this has a name, which many of you may already know, and this is called binary search. So here is a simple recursive algorithm for binary search. So in general, it searches an array. Remember that when we do this search, we might be searching different segments depending on how far we have progressed in the search. So in general, binary search takes a value k to search an array and two endpoints, left and right. And just to make sure that we get everything right, we will have the convention that it searches from the index L to the index R minus 1. That is, it searches from L to R, but not including R itself. So now if L and R are actually the same, then we have an empty array, right? Because L to R minus 1 is actually something where there are no elements in between. So we say we haven't found it. So when the interval that we are searching for becomes empty, the array definitely doesn't contain the value we are looking for. Otherwise, we compute the midpoint between L and R by taking the sum and dividing by 2. And because this might be an odd number, we use integer division. Now we examine, at this point we have found the midpoint, right? So now we examine if the value that we want is there at the midpoint. If so, we return true. Otherwise, if the value that we want is smaller than the midpoint, then we go to the left, okay? And if the value that we want is bigger than the midpoint, then we go to the right, right? So this either goes from left to mid minus 1 or mid plus 1 to right. In other words, we exclude mid from our search, right? So the first case runs the search from left to mid minus 1, because that's our assumption. If we call it with mid, it goes to mid minus 1. This one starts at mid plus 1 and goes to right minus 1. So the original thing was from left to right minus 1, and we have now excluded mid from this, and we have also halved the interval to search. So the crucial advantage of binary search is that each step we halve the interval to search, and at some point we will reach 1, and then when we halve 1, we'll get an interval of size 0, and so we will get an immediate answer, right? So we can write, as we saw for such recursive functions, we can write what is called a recurrence, right? A recurrence is just an expression for the time in terms of smaller values of the same expression. So the base case is that when we have T of n, we mean the time taken to search in a list or an array actually of size n, right? So T of 0 is 1. So if we have an empty array, we have nothing to do. And T of n in general is one step to find and compare. So this 1 is actually a constant number of steps to compare with the midpoint and decide to go up, down and all that. So those operations, plus the time taken to search whichever half we focus on, the left half or the right half. Remember that if we look at the left half, we are never going to look at the right half again. Okay? So one way to solve such a recurrence is to unwind it. Right? So we have Tn is 1 plus Tn by 2. So we take n by 2 and we do n by 2 divided by 2, and rather than write it as n by 4, we will write it as n by 2 squared. Okay? And this is because now if I do it one more time, it will be 1 plus 1 divided by 2 cubed and so on. So in general, you can see that if I do it k times, then I'm going to have k ones here. Okay? So if I do 3 times, I'll have 1 plus 1 plus t n by 2 to the 3, 4, or 4 plus t n by 2 to the 4 and so on. So after k steps, I have k plus t of n by 2 to the k. Now when n by 2 to the k becomes 1, at the next step I'm going to get t of 0. Right? So when does this become 1? When n is 2 to the k. In other words, when k is log 2 of n. Right? So when I get log 2 of n, then this has become t of 1. Okay? And at the next step, this is going to become 1 plus t of 0. So this is going to be log n ones, and so overall the complexity of binary search is just order of log n. Right? So we have gone from a linear search in the case of an unsorted array to a logarithmic search in the case of a sorted array. So we mentioned in the previous unit about arrays and lists that things that work on lists may not work on arrays and vice versa. So here is an example of something which works only for arrays. Right? The idea of looking up the midpoint and then going left works only if you can find the midpoint at constant time. If you have to spend time looking for the constant for the midpoint, then you cannot get this recurrence anymore. It's not going to be 1 plus t of n by 2, but it's going to be n plus t of, or n by 2 plus t of n by 2, and then we'll actually get a linear. So binary search for a list will actually turn out to be linear because of the time it takes us to go to the midpoint. Right? So this works only for arrays. But really the remarkable thing about binary search is that by only looking at a very small fraction of the sequence, we can conclude that an element is not present. So we know, for instance, that 2 to the n, 2 to the 10 is 1024. So if I give you 1,000 values, okay, we can look at 10 or maybe 11 and say that something is not there. So the overwhelming number of values we don't even have to look at in order to decide whether a value is there or not, and this makes binary search a truly remarkable uh, procedure if you think about it carefully. So having seen how to search for an element in an array, now let's turn to sorting. So the most basic motivation for sorting comes from searching. As we have seen, if you have an unsorted array, you have to search for it by scanning the entire array from beginning to end. So you spend linear time searching for the element. Whereas if you had a sorted array, you can probe it at the midpoint and use binary search and achieve the same result in logarithmic time. And logarithmic time is considerably faster than linear time. Now there are other advantages to having the elements sorted. For instance, if you want to find the median, the value for which half the elements are bigger and half the elements are smaller, well, the median in a sorted array is clearly the midpoint of the array. If you want to do some other kind of statistical things, such as building a frequency table of values, when you sort these values, they all come together, right? So all the equal values will be in a contiguous block, so it's much easier to find how many copies of each value are there. And in particular, if you want only one copy of every value, if you want to remove all duplicates from the array, then you can scan the sorted array from beginning to end, and for each block of values, keep just one copy. So there are very many different reasons why one might want to sort an array to make further computation on the array much easier. So let's imagine how we would like to sort an array. So forget about arrays and think about just sorting something which is given to you as a physical collection of objects. So say you are a teaching assistant for a course, and the instructor, the teacher who is teaching the course, has corrected the exams and now wants you to sort the exam papers in order of marks. So say your task is to arrange them in descending order. How would you go about this task? So one naive strategy is the following. You would go through the entire stack and keep track of the smallest mark that you have seen. At the end of your pass, you have the paper in your hand which has the smallest mark among the marks allotted to all the students. So you move this to a new pile. Then you repeat the process. You go through the remaining papers after having discarded the smallest one into a new pile and look for the next smallest one, move that on top of the new pile, and so on. So after the second pass, you have the second smallest mark on the pile. After the third pass, you have the third smallest mark on the pile. And as you can imagine, after n passes, you have moved all n papers from the old pile to the new pile in descending order. So this particular strategy can be illustrated as follows. So supposing we have this list or array of 6 elements. So in the first pass, we look for the smallest value. So the smallest value in this case is 21. So we move 21 to a new list and remove it from the original list. Now we repeat the scan. Among the remaining values, the value 32 is the smallest one. So we remove that and move it to the new list. We keep doing this. So at the next step, we move 55, and then we move 64, and then we move 74, and then we move 89. Right? So in this process, if this had been a vertical stack, 21 would be at the bottom, 89 would be at the top, and so we would have the list sorted from top to bottom in descending order. In this case, it is from right to left in descending order, or from left to right in ascending order. So this strategy is called selection sort. So we select in each round the next element which is the smallest, and therefore the next to be put out in the sorted order, and move it to its correct position, that is to the end of the final sorted list. Now this version of selection sort that we just described builds a second list. In other words, in order to sort one pile, we have to create a second pile of papers. Now we can easily eliminate the second pile of papers if we do the following. When we find the minimum element, we know it must go to the beginning of the list. So instead of creating a new list, we move it to the beginning of the current list. Of course, in the beginning of the current list, there is another value. So we have to do something with that value. So we just exchange the positions. So we find the minimum position and swap the value at that minimum position with the value at the first position. Now the smallest value in the entire array has moved to the beginning. So now we start from the second element onwards and look for the minimum again. This will be the second smallest. So we now, having found that, we will move that to the second position in the array. So we keep doing this, and without using a second list, we are able to do the same sorting that we did before. So to see how this works, we take the same array that we had before, As we said, in the first round, we identified 21 as the minimum element, which is marked in red. And the first position is 74. So we would like 21 to be at the beginning of this list. So since 74 is there, we exchange 21 and 74 and we get this new list. In this new list, now 21 is marked in green to indicate that it is in its final position. It is the smallest value. It has moved to where it should be in the sorted list. So now we scan the remaining elements and we identify that 32 is the smallest element. Now 32 already happens to be in the second position, so we could think of exchanging it with itself or doing nothing depending on how we want to interpret it. So 32 now becomes marked green so that it stays in the correct position. Now in the remaining list, 55 is the smallest element marked in red, but it has to be at position 3, which is occupied by 89 marked in yellow. So we exchange these two and now we have 55 in third position. So we keep doing this. So at the next step, we will identify 64 and swap it into the fourth position. And then we find that 74 is already in the correct position, so we leave it where it is. And finally, of course, 89 is the only element. So when you have a list of one element, there's no sorting to be done. So this procedure can be described by a very simple iterative algorithm. So what we do is that we have, if you remember, we start by scanning the entire array, that is from 0 to n minus 1. We look for the minimum element in that segment. Right? So we have an iteration which basically starts at the starting position, and then from the starting position onwards, it assumes that the beginning is the minimum value, and whenever you find a smaller value, you mark that as a minimum position. Now, having done all this, right, you have now found the minimum from A0 to an minus 1. Then you move this value to the beginning. So you swap the starting position and the minimum position. Now we have the smallest value at A0. So now you go back to this loop and now you move starting position from 0 to 1. So you do the same scan for A1 to an minus 1. Right? And now in starting position is 1. So at the end you swap the second smallest element to A1. Then you do it for A2 to an minus 1 and so on. Right? So this is the simple iterative version of selection sort, where we just start with the entire array, move the smallest element to the first position, then we take the rest of the array from A1 onwards, move the smallest element to A1, then start with A2, find the smallest element, move it to A2, and so on. So how much time does this algorithm take? So clearly, in order to find the minimum element in an unsorted segment of length k, we have to scan the entire segment, and this takes k steps. And in each iteration, the segment to be scanned reduces by 1. So we start by scanning all n elements, then we scan n minus 1 elements, then we scan n minus 2 elements, and so on. So we have overall the number of steps is n plus n minus 1 plus n minus 2 down to 1, which is just the usual summation I is equal to 1 to n of I. And this we know is n into n plus 1 by 2, which is order n squared. Right? So this naive algorithm selection sort in this iterative implementation is n square. Now there is another way of looking at selection sort. So remember we said that we start by finding the minimum element, moving it to the front, and then doing the same thing. Whenever you say do the same thing, it's useful to think of this as a recursive algorithm just to convince yourself that what you're doing is correct. So in order to sort in general A from some position I to n minus 1, what we do is we find the minimum value in the segment, that is from AI to an minus 1, and move it to the beginning, which is AI, right? So we have an array A, okay, and then we are at a position I, and the last position n minus 1, and we are trying to sort this. So what we are saying is we'll find the minimum somewhere, and then exchange the value here. And now what is now achieved by this is that this position is now correct. Right? So the value at AI is now in the correct position, and therefore we now need to sort from I plus 1 to n minus 1. And how do we do this? Recursively. We just apply selection sort, right? So we apply selection sort to A from I plus 1 to n minus 1. And this procedure stops when we have only one element. So if we are going to start from AI is equal to n minus 1 to n minus 1, then we do nothing. Right? So the reason to think of it recursively, one reason is that the code becomes a little easier to read. So you say that you want to sort A from start to n, where start is the index of the unsorted segment where it begins, and n is the total size, so the last position is actually n minus 1. So if start is n minus 1 or bigger, then you do nothing, you just return. Otherwise, you find the smallest value in this segment from start to n minus 1. Right? So this is the same loop we did earlier. We start with the minimum position being the beginning of this segment, and then we keep walking forwards, and whenever we find a value which is smaller than the minimum position, we update it. And at the end of this loop, we exchange the position that we have found, the value at that position, with the starting position. So now the correct value, so some value from say here, has moved to the correct position. And now we recursively sort A, starting at the position start plus 1 up to n. So is this any different in complexity? So let us write, so remember when we did recursive calculations, we said that typically you would write a recurrence, right? You will express the complexity of the algorithm itself in a recursive way. So suppose Tn is the number of steps you need to run selection sort in length n. Right? So the first thing is it requires n steps in order to find the minimum and move it to the beginning. And then having moved it to the beginning, the rest of the array that is left to sort is of size n minus 1. So you need time recursively Tn minus 1, right? So therefore you have Tn, so this is the time to find the minimum. Tn is n plus Tn minus 1, which is the recursive step. And we said that if we are sorting an array of size 1, we don't have to do anything, we just return. So T of 1 is 1. So T of n is n plus Tn minus 1. But now if I take Tn minus 1 and I expand it using the same expression, I get n minus 1 plus Tn minus 2. Now if I expand Tn minus 2, I will get n minus 2 plus Tn minus 3 and so on. And so this will expand out to exactly what we got for the iterative algorithm, namely n plus n minus 1 plus n minus 2 down to n. Right? So what we have seen in this unit is that we have seen that a very natural algorithm which we would apply if we did things by hand, called selection sort, can be formalized both iteratively and recursively, and it gives us a complexity which is order n square. So let's continue with our discussion of sorting and look at another simple sorting algorithm. So as we said before, there are many motivations for sorting, starting from searching to removing duplicates to computing some statistical properties such as frequency tables and so on. And the example that we have in hand is one where we are asked to sort a bunch of exam papers in descending order of marks. So a second strategy to sort this bunch of exam papers would be the following. So you take the topmost paper in this stack that you have and create a new stack with that. Now you take the second paper and compare it to the first paper. If the mark is bigger, you put it above because you want it in descending order. If the mark is smaller, you put it below. So after this step, you have two stacks of paper in descending order. Now a stack of two papers rather. And now you take the third paper and now you see where it fits with respect to the first two. Either it goes all the way to the bottom, or it goes between the two, or it goes all the way on top. Right? So in this way, at each point you pick up the topmost paper in the unsorted stack and you insert it into its correct position in the sorted stack that you are building up. Right? So let's see how this would work. So supposing we have our old array of unsorted elements. So what we do is we start with the very first element, namely 74. So we take 74 and we start a new stack. Now we have to take, now the topmost element at this point is now 32, the leftmost in this case. So now we have to take 32, and since it is smaller, it should go to the left of 74. Right? So we do this, so we now get this array. Now we look at the next element, namely 89, and once again it must go at the appropriate position with respect to these two, so it must go to the right of the 74, so we get this array. Now we take 55 and we have to find out where it goes, so we can start at the end and say it's not here. It must go to the left of this. And then we finally find that this is the correct place for it to go. Right? So this is the insertion step. We take each element and we walk down to the point where we want to insert it. Right? So 55 comes between 32 and 74. Now where does 21 go? Well, if we try to insert it, it turns out it must go all the way to the beginning because it's smaller than everything that we have so far. So this is the next step. And finally, when we do 64, it will come between 55 and 74. Right? So at each step, we pick up the next element and we insert it into the already sorted segment that we have created with all the previous elements. So we start by building a sorted sequence with one element. So this is called insertion sort. And we insert each unsorted element into the correct place in the already sorted sequence. So it's because of this insertion step, okay, that every element is inserted into its correct place, that this is called insertion sort. So this is a very straightforward iterative implementation again. So what we do is we have our initial array A, right, from position 0 to n minus 1. So what we do, of course, is at the beginning we have to do nothing. So we can assume that we actually start with position 1. So we start with position 1 and then we look backwards. So we start with the current position and we work backwards, and so long as the value that we are looking at, okay, is smaller than the value to its left, we keep moving. Right? So we have assumed that we have this swap operation which basically takes two positions in an array and exchanges them. Right? So swap A next post minus 1 means take the value at A next post, take the value at A next post minus 1 and swap them. As we explained at the beginning, we can assume that such things are basic operations. It's convenient for us to express algorithms like it. As adding this only adds a constant factor to the number of overall operations that we have to do, which we can ignore in asymptotic complexity. So we swap each element with the element on its left so long as it is the element on the left is smaller, and we stop when we come to a position where the value on the left is greater than or equal to the current value. At this point we stop. Right? So this brings the value that we started with to the correct position. So in general, if we had, say, done up to some I, okay, and then I start walking backwards, then so long as I is bigger than so long as I is smaller than I minus 1, I will exchange. I will keep exchanging until I reach a position where I find that the values on the left are smaller than this value, and I will stop. So this is this basic loop, and I do this for all elements. So for each element I have to insert it. The first time I have to insert it in a smaller segment. As I go along, the segments we have to insert it in become longer and longer. Okay. So we can see now how this works on our array given to us. So we first of all start with looking at this segment. So this is my initial configuration. So this is sorted and this is unsorted. Okay. So now I will immediately see that 32 is bigger than 74, so I will exchange, and then because it reaches the beginning, so one of the conditions in that loop is that if I reach the beginning of the loop, so if next pos is equal to 0, I will also stop. So if I found it to the leftmost position, then this loop terminates. Right? So having done that, then I have this. So now I must try to insert 89 into this. Okay, so I will find that 89 is already bigger than 74, so nothing needs to be done. So the first non-trivial step that happens is with 55. So when I do 55, I compare it with 89. I find that 89 is bigger than 55, so I will exchange them. Right? Now I will compare 55 with the element on its left, 74, and then again it is in the wrong way, so I will exchange them. And finally, having found that 55 is now bigger than 32, I will stop. Okay? So this is now the end of this phase. Now I will look at the next element to do, which is 21. Right? So I will look at 21. So 21 will get exchanged with 89. Then 21 will be exchanged. So it will get exchanged all the way to the left. So I'll exchange 21 with 74. Then I will exchange 21 with 55. Then I will exchange 21 with 32. And now once again I will stop because I've reached the leftmost position. There's nothing to the left. Okay. And the last round I will take 64. Right. So now this part is all sorted. So I will take 64 and try to insert it here. So it will swap with 89. It will swap with 74 and then stop. Okay, so this is how insertion sort works. And this is a very intuitive sort. If you take a pack of cards and you try to sort it, typically this is how you would sort them. So if you look at the analysis, it is quite similar to selection sort that we saw before. Right? So inserting a value means you have to walk down that segment till the very end. Now, of course, one might argue that to find the position to insert, you can use binary search. Okay? You need not go one element at a time. If you want to actually find the position where it must go, you can use binary search. But even if you find the position where it must go in logarithmic time, you need to shift all the elements, and that is what really takes linear time. You need to actually make space for this. So in the worst case, you might have to put it in the leftmost position. So all the k elements which are already there must be shifted right by one, and that takes k steps. Okay, so binary search, although it can help us find the position faster, doesn't really help us to implement insert any faster. So insert takes linear time for a segment, and these segments keep growing. Initially, I want to insert A1 into a segment of size 1, then A2 into a segment of size 2, and so on. So I have 1 plus 2 plus 3 up to n minus 1. Finally, A n minus 1 must be inserted in the segment A0 to A n minus 2, which is of length n minus 1. Right? So again, I have T of n is 1 plus 2 up to n minus 1, and this is just a variation of this summation we have seen many times before. It's n into n minus 1 by 2. So this is again an order n squared search. So once again, as we saw for selection sort, there is a natural way to think of insertion sort as a recursive thing. We sort part of the array and then we insert an element into that to grow it, right? So in this case, we think of the array as being in two components, right? So we have a sorted portion and an unsorted portion, right? So what we do is we take the first element here and insert it, and then we recursively apply the algorithm to the rest of the unsorted portion. So if A0 to I minus 1, so if this is position I and this is position I minus 1, so I minus 1 is the last sorted position, I is the first unsorted position, then we insert AI into the sorted portion, and then we recursively sort AI plus 1 onwards, and once again when I is actually here at n minus 1, then we don't have to do anything, so we can just trivially return. So now we have a recursive formulation in two parts. Okay, so we have insertion sort itself, which says sort this unsorted segment from start to n minus 1. Okay, so if start is already at n minus 1, return. Otherwise, insert the value at position start into the rest of A, which we will see below, and then recursively sort the rest of the array from start plus 1 onwards. So what does insert do? Well, it starts at the position start and tries to insert it into the segment 0 to start minus 1. So it walks backwards exactly as we had done it in the iterative thing. It finds the first position such that the value on the left is at least as small as the value we are currently looking for and stops there. Okay. So this insert is basically what was in the body of the iterative loop, but instead of doing an outer loop, we do it recursively. So how much time does this take? Once again, this is just to give you practice in looking at recursive algorithms and writing down the analysis. So whenever we have a recursive algorithm, we write a recurrence. That is, we write a formulation of T of n in terms of smaller values of T. So let's try to analyze this recursive algorithm. So we will analyze it looking at it slightly differently from the way we have formulated the algorithm. So if we want to sort A0 to An minus 1, then what we are doing is we are recursively sorting this segment and then inserting this value, right? So it takes time Tn to sort the entire thing. This breaks up into taking time Tn minus 1 to sort the first part up to n minus 2, right? And then n minus 1 steps to do the insert, right? So we get the same recurrence as we did for insertion, for selection sort. T of n is T of n, this is the insert phase, and plus T of n minus 1, which is the recursive phase, right? And if we expand this out exactly as we did before, we get n minus 1 plus n minus 2 down to n, which is n into n minus 1 by 2, which is order n squared. So again, there is no difference between the time for the recursive and iterative versions, except that one should keep in mind in general that recursive calls are more expensive than iterative loops. Okay, we will come back to this point a little later, but otherwise, if we count recursive calls, calling a function as a basic operation, then there is no difference between the recursive and the iterative versions. The recursive version is sometimes easier to conceptually understand and to code. So what we have seen is that the two natural algorithms that we would typically apply when we do something manually, selection sort and insertion sort, are both order n square. There is another algorithm which you may come across, which we will not discuss in this course, called bubble sort, which is not something that we would do naturally, but it seems to be a favorite way of describing how to do things on a computer. Okay, so bubble sort basically does this insertion kind of swapping, except it takes the maximum or the minimum value depending on which you want to do. Say it takes the maximum value and moves it to one end of the array. So then you have, like selection sort, the largest value at one end. Then you go back to the beginning, and again you keep looking at adjacent values and take the second largest value to the second last position, and so on. Right? So bubble sort is also n square. But as we have seen, n square algorithms are not really feasible for large values of n. So if we have n above about 10,000, somewhere between 10 to the 4 and 10 to the 5, then n square is going to take several hundred seconds to execute, and therefore this is not going to be useful for large bodies of data. But this is not to say that these algorithms are all equally bad. In particular, it turns out that if you actually look at experimental evidence, then insertion sort usually behaves better than selection sort. And both of them are better than bubble sort. And to think about why insertion sort behaves well, just imagine what happens when we apply insertion sort to an already sorted list. Right? So whenever we want to insert something into the already sorted list, we will find that it's already in the correct position. So the bottleneck, which is the insert phase, is the bottleneck. The insert phase will basically terminate after one comparison. So insertion sort will essentially become linear time if we apply it to an already sorted list. So this is why in many situations, insertion sort actually behaves a little better than other order n square sorts. But in general, order n square sorting algorithms are not acceptable, and we would like to look at more clever ways of sorting data, because in order to sort large volumes of data, this is impractical. So we have seen two intuitive sorting algorithms, selection sort and insertion sort. Okay, but unfortunately for us, both of them turn out to be order n square. And we know that order n square is not really good enough for sorting large arrays. So what can we do instead? So here is one way to sort an array more effectively. So suppose we divide the array into two equal parts. So we just break it in the middle. We look at the left separately and the right separately. Now assume that we can sort the left and right into independently sorted halves. So we have the left half sorted and the right half sorted. Now if there were a way to combine the two halves efficiently to get a fully sorted array, then we can say that we have achieved the sorting by breaking it up into two smaller subproblems and combining the result. So let's first look at this combining step. Right? So we are given two sorted lists A and B, or two sorted arrays A and B, and we want to combine them into a single sorted list. So this is something that we can easily do. Supposing we had two stacks of cards in front of us, each of them is arranged in the same way in, say, an ascending order, then what we would do is we would look at the topmost card in each stack and take the smaller of the two and move it to a new stack. And we would keep doing this until eventually we have moved all the elements into a new sorted stack. So this is an intuitively merging. So I have two stacks. So I have two stacks of cards, right? So I look at the topmost card in each, and then one of them goes to a new stack, and then this is gone. And so now I look at the next value and compare it with this, and then one of these goes here, and so on. So eventually I build up a new stack of sorted things. So let's look at this in a very simple example. So supposing we want to merge these two sorted lists. So this is sorted in ascending order, and so is this sorted in ascending order. Right? So the first step is to look at the topmost. So let's assuming that in terms of topmost that these are written like this. So I have this stack and I have this stack. Right? So I look at the topmost element and then I say that the smaller of the two must be the topmost element of my new stack. Right? So in this case I take 21 out and I move it here. Now I have to compare what is the topmost element in the two stacks, namely 32 and 55. So now I compare the smaller of the two as 32 and move it out. Now I compare 55 and 74, and so 55 moves out. Now I compare 74 and 64, so now 64 moves out. Now I have nothing left in the second stack, so the first stack is in sorted order, so I just copy it out in order. So I first move 74 and then I move 89. Right? So this is a very intuitive merging thing that we do again quite naturally when we are dealing with physically two sorted lists, right? And we can do it with a normal array as well. So now how do we use this to sort? As we said, our aim is to break up the problem into two equal subproblems, solve the subproblems, and then merge the two solutions into a final solution. So we will sort A0 to A n by 2 A by n by 2 minus 1 to make it distinct. So we have A with indices 0 to n minus 1, right? So we take n by 2 minus 1 and n by 2 as the midpoint. So we sort this separately, and then we merge them. Right? So this is the strategy that we have, and this is, since the final step involves merging two solutions, this is quite naturally called merge sort. Now, I've said that we will break up the thing into two sub-problems. So how do I solve this? Well, I will recursively do the same thing. I'll break this up into two sub-problems, and I will merge this. I'll break this up into two sub-problems and merge this, right? So you keep breaking up the thing into sub-problems until you reach a trivial sub-problem, which is, as we have seen, which is an array of size 1. Okay? So let's look at an example before we proceed. So here is an example of an array that we would like to sort. So the first step is to break it up into two parts, right? So we take the left part, so this is our midpoint, right? So we take the left part, which is the first 4 elements, and the right part. And now we will apply merge sort separately to these parts. Finally, we will merge the answer. So having applied merge sort to the left part, you must again break it up into two parts. So I have to take this point and divide it into two parts, right? And similarly on the right, I will have to take this point, okay, and divide it into two parts. Now, we could say that we can easily do arrays of size 2, but let's just keep going till we reach the base case, right? The base case is when we have only one element and no sorting is required. So we'll again split each of these into two parts, okay? So notice that for convenience we have taken something where I can keep dividing by 2, but there is no limitation in merge sort. It will work for any size. At some point when you do an unequal split, the two halves will not be the same size, but that doesn't really matter. Okay. So now we break the last step into two parts. So 43 is now, so this is in green to indicate that this is now a single element and hence sorted. So is this. And in the same way, we can take each of these last steps and get now 8 single elements which are sorted. Now we start merging, right? So we want to merge these two in order to sort that thing. And similarly, we want to merge these two. And we want to merge these two. And we want to merge these two. Right? So we merge the first two, and then when we merge this, the smaller one goes first. So this is now sorted. Similarly, we merge the second pair. It doesn't change in order because 22 is smaller than 78. We merge the third pair and they get exchanged. And we merge the fourth pair and again they get exchanged. So it is important to note this exchange did not come by looking at this array of size 2 directly, but rather by looking at these two values, taking the smaller one up first and then the bigger one. Okay? Now I want to merge these two arrays into a sorted segment of length 4 and these two arrays into a sorted segment of length 4. So again I apply merging. So note that 22 will come first, okay, then 32 will come here, then 43 will come here, and then 78 will come there. Right? So if I apply this, I'll get 22, 32, 43, 78. The same way here, 13 should come here, then 57, then 63, and then 91. Right? So this is the effect of merging. And finally I have to merge these two. So the smallest one, 13, will go here. Then I will get 22, then I will get 32, then I will get 43, then I will get 57, then I will get 63, I will get 78, and then I will get 91. Right? So merging these two sub-arrays of size 4 will give me the final answer. Right? So this is how merge sort works. You break it up into two parts, recursively solve the two parts using the same strategy, and merge them. So this is generally a principle that can be applied to many problems. So if you can take a problem and divide it into two or more parts, okay, such that this part can be solved independent of that part and there is no overlap. So you solve this separately, you solve this separately, and now you want to somehow combine. In this particular algorithm, the combination is merging. We will look later on at other divide and conquer algorithms where the combination might require a different strategy. But the whole idea is that if you can break up the problem into smaller problems and then combine them, then you can sometimes get a lot of benefit in terms of efficiency. Okay? So the crucial thing is to identify how to break up the problem into disjoint subproblems and how to combine the solutions to these subproblems efficiently to solve the problem at hand. So let's come back to our merge sort and try to formalize the algorithm in terms of actual code. So how do I combine two sorted lists or two sorted arrays A and B into a third sorted list C? Well, as we saw, if one of the two is empty, then I don't have to do anything. I just have to copy the other one. So if there is no element left in A, then I can just copy the rest of B into C. If B is empty, I can copy A into C. Otherwise, we compare the first element of A and B and move the smaller of the two into C, and we repeat this until everything has been moved. Right? So here is a simple iterative merge function. So it takes two arrays as input. It takes an array A of size m, so 0 to m minus 1, and it takes an array B, which may be of a different size, 0 to n minus 1, and the aim is to construct a new array C. Now we know the size of C because everything there must come here, so it will be 0 to m plus n minus 1. Right? So what we do is we maintain some position. So we say that, okay, let I be the current position I'm looking at in this, J be the current position I'm looking at in B, and K be the current position I'm trying to fill in C. Right? So now we know that there are m plus n steps. So we put a loop which says that this thing must run m plus n times. Okay. So if we have already reached the end, if J has already reached the end, okay, or if AI is smaller than Bj, right? So this is the real merge step. If AI is smaller than or equal to Bj, what we will do is we will copy this value here, and then we will increment I and we'll increment J, right? So we will move Ck will be AI and I will be incremented and K will be incremented, okay? So this, but this also happens in case J is equal to n. Because if J is equal to n, what it means is that this pointer actually reached all the way there, so there's nothing left to scan. So J is equal to n means it's actually beyond the right point, right? So it's beyond that. So there's nothing to scan, and so we will just copy everything from A to C. So either we copy the current element from A to C if AI is smaller than Bj, or if there's nothing in B, we copy the current element because we are just copying everything from A to C. So the symmetric case is when we have AI bigger than Bj. So if AI is bigger than Bj, right, then what we want to do is copy this value here. So we want to move J up and K up. So we copy Ck is equal to Bj, copy the value at Bj to Ck, and increment both J and K. And like we did earlier, the other reason we might want to do this is if we have already exceeded the length of, so if we are currently here, so A has been exhausted, then we would also move the next element blindly from B to C. Okay. So this is a simple while loop, right? It takes exactly as many steps as there are elements to move, and in each step I move one more element to C, either from A or B, depending on the criterion of the current element I'm looking at. So having got merge out of the way, now we can look at merge sort itself. Right? So if we want to sort A of size n, indices 0 to n minus 1, we have to create a new array, as we said, because merging has to copy the two things into a new thing. Right? So we're eventually going to take A and merge sort it into a new array B of the same size. So if n is 1, if we have an element of size 1, we have the base case and nothing is to be done. Right? Otherwise, we will sort the left part into a subarray L, we'll sort the right half into a subarray R for left and right, and then we will merge the two using the function we just wrote. So this is a very clear recursive algorithm. So we want to merge sort A from left to right. So we will assume that when we say from left to right, we mean that the leftmost position is called left, right? And the rightmost index is actually right minus 1, right? So this is actually one more than the index of the position that we want to sort up to. So we want to sort the segment starting at A left and going up to and including A right minus 1. So first of all, if this segment is of length 1, right, then we just copy the value into B, we copy the value at A left, right? Otherwise, what we do is we find the midpoint, right? And then we copy up to but not including mid. This is why we use this convention that it's up to mid minus 1. So this will be from left, A left to A mid minus 1. And this will merge sort from A mid to A right minus 1, right? So what we want to make sure is that we are not accidentally overlapping. So we want to make sure that this mid value which appears in both things, the value at A mid is only in one of them, namely it's in the right hand side, not in the left hand side. So having done this, then I will use my earlier merge function to merge L, which is of size mid minus left, and R, which is of size right minus mid, into B, right? So this is the function that we already had before. So it's a very simple recursive thing. Find the midpoint, sort the left half, sort the right half, and merge them. Okay? As we said, it doesn't really matter that A is of even length or it's a multiple of 2. So it might be that the left half and the right half are not of same length. One will be longer, one will be shorter. It doesn't really matter. This works in all cases. To analyze this is not so straightforward, so we will postpone that to the next module. So we have seen how to use a divide and conquer strategy to implement a sorting algorithm called merge sort. So now we want to analyze whether merge sort actually behaves better than our order n squared intuitive sorts like insertion sort and selection sort. So in order to analyze merge sort, we first need to look at the merge operation itself. So remember that when we merge two sorted lists, what we do is we take both lists side by side and we keep copying the smaller of the two elements at the head of each list into the final list C. So this was the code that we wrote last time. So basically we have a list A which runs from 0 to m minus 1, and we have another list B which runs from 0 to n minus 1, and we produce the output in a third list C which has indices from 0 to m plus n minus 1. Right? So what we do is we start by putting an index ij into these two lists and index k into the list C, and we compare these two values and we take the smaller of the two values and move it here, and then we move this and then we keep moving these two indices, and all the while we keep moving k. So the question is, how long does this take? So in each iteration, notice that we add one element to C, right? But the size of C is exactly m plus n because there are m elements in A and there are n elements in B, and each of them will eventually make it to C. So there are m plus n elements, right? And in each iteration of this loop, the loop that we had before, right? So in each iteration of this loop, one element gets added to C, either in this if or in this if k is incremented, right? So this list, as you can see, k will make progress in every iteration. So there is a bound of m plus n steps for this loop, and in the loop we will, if you count very carefully, we have a comparison, we may have one more comparison, we have an assignment and so on, but you can check that there are no more than 7 steps involved. So some constant number of steps regardless of which branch we take in this, right? So we have m plus n iterations, each of which has some constant number of steps. So we have overall order m plus n steps. But m plus n is of course bounded by 2 times the maximum of m plus n. So we can just say that this thing takes order of maximum m plus n. If m is roughly the same as n, which will typically be the case in merge sort because we split it in half, so the two will differ by at most 1 in terms of length, then we find that merging is a linear time operation. So if we want to merge two lists, it takes time proportional to the length of the two lists together. So now coming to merge sort itself, what we want to do is we want to take a list of size n, right, and we want to split it into two lists of size n by 2, right, and then we sort these separately and then we merge. So in order to do this, it's very clear that if we look at Tn as the time taken by merge sort on an input of size n, then this requires us to sort two lists of size n by 2, and then as we have seen, it takes order n time in order to merge them. Now, in order to compute this T of n explicitly, we will assume that n is a power of 2. Now it turns out that merge sort does not in any way require n to be a power of 2, not even an even number. If it is not even, then when we split into two parts, they will not be equal because we cannot split an odd number into two equal parts. But it doesn't matter, the algorithm will still work correctly. This assumption that n is 2 to the k is only a simplification for us to be able to come up with a nice calculation. So we have two problems of size n by 2, 2 times t of n by 2, and then we have a merge of n. So how do we solve something like this? Of course, we also have a base case which says that when we have only one element, it takes no time except to just check that you have only one element. So t of 1 is 1. Right? So if you have a solution, an expression like this, two recurrences like this, then how do we solve them? Right? So the basic idea is to keep the simplest way to do it. Of course, you can come up with more sophisticated ways which we will not go into right now. But one simple way is to just keep expanding using the same analysis, the same expression until you come down to the base case. So we start with the base case t1 equal to 1, and the general case Tn is 2 times t of n by 2 plus n. So now what we can do is we can use the same equation to expand t of n by 2. Right? So if we expand t of n by 2, then we find that t of n by 2 becomes 2 times t of n by 4 plus n by 2, because I take whatever is here, divide by 2, so n by 2 is n by 4, and I take whatever is here and plug it in here, so n by 2 comes. Now if I expand this out carefully, then this 2 and this 2, rather than write it as 4, I will write it as 2 squared. I will also observe, and this will be useful, that this 4 is again 2 squared, right? And then this n by 2 is multiplied, so this n by 2 is multiplied by 2. So I get 2 times n by 2, so that's n plus n, so I get 2n. Okay? So it's not an accident that I have 2 squared and 2n. As we will see, if you do one more step, now if I take this expression t of n by 2 square and I apply the same rule to this, right, then this t of n by 2 squared expands out like this, right? It's n by 2 squared divided by 2 is n by 2 cubed. So I get 2 times t n by 2 cubed plus n by 2 square. Now this and this will cancel, right? So I get 1 n here, I already have 2 n, so I get 3 n's. And this 2 into 2 square I will write as 2 cubed. Right? So I have gone from 2 squared t n by 2 square plus 2n to 2 cubed t n by 2 cubed plus 3n. So it's easy to verify that if you do this j times, you will have 2 to the power j times t of n by 2 to the power j plus jn. Right? So now when do we reach the base case? We reach the base case when n by 2 to the power j goes to 1. So when does this happen? Well, n by 2 to the power j is equal to 1. It means that 2 to the power j is equal to n. Right? So j is nothing but log of n to the base 2. Right? So we will always use log n in general to mean log of n to the base 2 unless otherwise specified. Okay? So after log of n steps, we end up with something which looks like this. Right? It has 2 to the j t n by 2 to the j plus jn. After log n steps, j is log n, so I have 2 to the log n, then t of n by this, so this is t of 1 now, so this is just 1, so this multiplied by 1, and then I have j times n, so j is log n, so j is log n and n is n. Right? So I have, after doing this expansion log n times, I end up with 2 to the log n plus log n times n. 2 to the log n by definition is just n, right? Because that's the definition of log. That is the exponent of 2 which gives you n. So this is n, and I have this gives you n log n, and we know from general things that n is big O of n log n, so this is bounded by 2 times n log n. So we can say that overall merge sort takes times O n log n. Right? So we have achieved a significant improvement, because remember that so far both insertion sort and selection sort were O n square, and we have come down from O n square to O n log n by using this divide and conquer strategy. So why is this a big deal? We saw right at the beginning that O n log n is much more efficient than O n square. Okay? If we assume, as we have said, that a reasonably standard desktop machine can do 10 to the 8 operations per second, then the size of the feasible input of what we can sort with a sorting algorithm goes from 10,000 for an n square algorithm to 10 million or 1 crore for an n log n algorithm. So therefore, if we really have to sort large volumes of data, n log n makes it feasible for us to do so in a reasonable amount of time, whereas n squared would take years, as we saw before. So before we conclude, there are some nice things to notice. So this merge operation which we have used in merge sort is actually a very useful operation on any sorted list. Right? So one thing that we do in merge is that we actually combine the lists without losing anything. So if we merge two lists such as say 1, 2, 4 and 2, 3, 6, then in our final thing we will have 2 copies of 2, okay, because there are 2 copies, and then 3, 4, 6. Right? So sometimes we may want to not have this. We may want to keep only 1 copy. We might want to treat these as sets. So if I take this as a set 1, 2, 4 and the set 2, 3, 6, then the resulting union of the 2 sets is 1, 2, 3, 4, 6 with only 1 copy of 2. Well, we can easily do this in our merge procedure by just saying that when I find, so earlier we had two cases, we had AI less than or equal to bj, and then we had AI greater than bj, right? So in the first case we copied from AI, in the second case we copied from bj, and in either case we only incremented either I or j along with k. In this case we say that if the two sides are equal, we keep one copy of it in the final list, but we skip over both these copies. We increment all three pointers, right? So if we are at this position and this position, right, then in our output we will copy a 2, and then we will move this pointer to the right and this pointer to the right, so I don't copy 2 twice, right? So this is one thing that we can do. The other thing that we can do is to intersect two lists. So if we again have 1, 2, 3, and maybe 2, 3, 6, right? Then maybe we want to make sure that we have in our output only 2 and 3. Right? So now what we do is when we start looking at these two, if they are not equal, then obviously they are not in the intersection. But which one should we leave? Well, 2 could still be there because 1 is smaller, so we move this pointer right. So if AI is smaller than bj, we increment I. Now we say when AI and bj are the same, we will, as we did for union, we will move the 2 out, and we will merge, we will move both pointers. So now both pointers come to this position. Now again we will say that we have 3, and we will continue, and then when we see the other way around, if bj is smaller than AI, we will increment j and not I, right? So the important thing to note is that merge is a very generic operation. We can do what we did earlier, which was to actually shuffle the two sorted lists into one big sorted list where no elements are lost, or we can remove duplicates while we are doing it, treat it as a set union operation, or we can only keep the common parts, which is a set intersection operation. Okay? So to check that you have understood this, maybe you should try out the following exercise. So supposing we want to do what is called list difference. So set difference is sometimes written like this. So if I take the set 1, 2, 3 and the set say 3, 4, 6, right, and I ask the set difference, it says whatever is in A but not in B. So the answer should be, in this case, 1 and then 2 but not 3, because 3 is there in both. Okay? So you can do the same thing for lists. So for example, if I had the list 1, 2, 3 and the list 3, 4, 6, then I might want to keep the list only 1, 2. So just check whether you can adapt merge in the way we have done now for union and intersection in order to list difference. So merge sort, though it is an order n log n sorting algorithm and therefore is significantly faster than insertion sort or selection sort, it does have some shortcomings. The main problem with merge sort is that it requires extra space. See, when I take A and B and I merge it into C, it's almost impossible to do this without storing the merged array in a separate place. Because if I start merging in place, then the sorted order of A and B gets messed up, or I have to keep shifting things, and so the merge is no longer linear time. So if I want a linear time merge of A and B, this can only be achieved by using an external list of the size which is the sum of the two lists in order to store this. This means that if we are sorting large arrays, I'm also extra space is being used, because I have to keep duplicating the space in order to do the merge operation. And of course, the other thing about merge sort, which is very difficult to overcome, is that it is inherently recursive. I mean, there is no way to actually easily make it iterative, because we need to construct the sorted things and then merge them. So we need to store these recursive solutions at each point in order to combine them. Right? So the recursive call and return can be expensive also. So although merge sort is a very attractive sort in terms of its theoretical complexity, it is not sometimes used in practice because of these limitations, and we will see how to overcome this in some other way. So the main reason we need extra space in merge sort is because of the merge operation. As we saw, in order to combine A and B into a list C in linear time, you need extra space. Now suppose, and the reason this happens is because we could have something like the left side could be say 2, 4, 6, and the right side could be say 1, 3, 5. And now we need to take things from both sides. So sometimes I need to take something from here, then I need to take something from here, then I need to take something from here, and so on. Right? So though each of the two halves is sorted, there are elements from the left which must go to the right, and there are elements from right that must go to the left. So now, if we could come up with a way to avoid doing this, so that everything in the red part is smaller than everything in the green part, then once I have sorted the red part and I've sorted the green part, then automatically everything in the red part stays to the left of everything in the green part. Right? So if I had had, instead of this, if I had had on the left, I had started with say 2, 1, 3, and on the right I had started with say 6, 4, 5, and then I had locally sorted these things. So I had got 1, 2, 3, and then here I had got 4, 5, 6. Then after this, if I had guaranteed that the split was such that everything on the left is smaller than everything on the right, after doing this divide and then solving the sub problems, there is no combination occur. There is no need to merge. Okay? So our next sorting algorithm will look at a strategy to implement this idea. So we are now ready to look at another algorithm called quicksort. So quicksort was invented by a computer scientist called Tony Hoare in the early 1960s. That's about 50 years ago. And Tony Hoare is a very well-known computer scientist, and he has in fact won the Turing Award, which is one of the highest achievements awarded for academic computer scientists. So what is the purpose of quicksort? Well, the purpose of quicksort is to overcome some of the shortcomings that we saw in merge sort, right? So one of the things that we saw in merge sort is that because of the merge operation, we need extra storage, and so this makes merge sort a little expensive. So we also observed that the reason that we need this extra storage is because we have in the merge operation that we might be pulling out elements from both sides when we are populating the merged array. So basically some elements on the right might be smaller than some elements on the left, and this is what results in merging. So can we divide everything so that this doesn't happen? Everything on the left is smaller and everything on the right is larger. Right? Is it possible to do a divide and conquer in this fashion? Well, if this is the case, then what we need to do is we need to put the middle value in the center, right? So supposing we can find the median. So remember what the median is. The median is the value such that exactly half the values in the array are bigger and half are smaller. So now we move everything which is smaller than m to the left half. So we have a set of values here which are less than or equal to m. And then we have on the right side something which is strictly greater than. Right? So of course we have to do the shifting, but the claim is that we can do this shifting in linear time, and we will see a way to do this. So assuming we can do this, pick a value m which is the median and shift everything smaller than m to the left, then this is roughly going to be the half point, because m is a value which splits the array into two parts. Those which are smaller are half and those which are bigger are half. Now I do this recursive thing, I sort this and I sort this, and now remember there's no need to merge because everything on the left is already smaller than everything on the right, so I can just go ahead and assume the array is sorted. So if I do this, then by the same analysis as for merge sort, I have a recurrence which is t of n is 2 times tm by 2 plus n, and we know that this is order n log n. So this will give us the same complexity as merge sort, but it will avoid some of the overheads involved with creating extra space, because when I do the recursive call here, I can easily sort this part in place and this part in place, because I don't need to refer to the other part at all when I do the solution. So of course there must be a catch, and the catch is, how do we find the median? Right at the beginning of our discussion, we said that one of the reasons that we want to sort is to do statistical things like find the median. So if we have sorted the array, then the median value is the middle value. But of course, our goal now is to sort the array. So we can't assume that we have the median, because we have already seen that sorting is an easy way to find the median. So it's kind of a chicken and egg problem. We can't use the median to sort. Right? So what quicksort Tony Hoare's algorithm says is, don't necessarily pick the median, just pick some value in A and do what we said before. So you pick up this pivot and then you break it up into two parts, those which are smaller than the pivot and those that are bigger than the pivot. Right? So the pivot is just some value in the array. It need not be the median. Okay, and we'll see that if it's not the median, then this results in some problems in terms of the worst case complexity, but let's just ignore it. So we just pick some value in the array, and we take all those values that are smaller than that, move it to the left, all those which are bigger than that, move it to the right, and then we sort them recursively, and then we are guaranteed that nothing on the left needs to be combined with anything on the right after this, so the resulting array is sorted. Okay? So this is quicksort. Choose a pivot element. So for example, you might just pick up the very first value in the array as a pivot element. Partition this array into the lower and upper part. So the lower part is those which are less than the pivot. The upper part is that which is greater than the pivot, right? So the crucial step is this partitioning. We'll see how to do this. How do you do this partitioning? That's what we will see now. Okay. Then we move this pivot here so that it's in the correct place, right? And now we recursively sort this part, and we are done because nothing needs to move. So here is a kind of high-level description of the algorithm, okay, through an example. So supposing this is my array, then I pick the first element as a pivot, namely 43. So with respect to 43, I now partition this array so that everything smaller than 43. So what are the elements smaller than 43 here? We have 32, 22, and 13. So these elements should come to the left, and the elements which are bigger, namely 78, 63, 57, and 91, should go to the right. So I do this partitioning, right? And how do I do this partitioning? Well, I kind of, okay, so I brought everything to the left, okay? And then after this, I recursively sort the left. So this is no longer assumed to be sorted. It just has everything smaller than 43. This is not sorted. It has everything bigger than, but then recursively, if I assume I can sort it, then I've sorted the entire array, because now nothing in the yellow side needs to be combined with anything on the green side. The red pivot value separates these two. Okay. So the first thing that we need to understand is how to do this partition. So there are two ways to partition. So we will look at one in detail and show some code for it, and then we will look at another through an example, and you will have to write the code yourself if you are interested. So here is one way to partition. So I start with the pivot element at the left, and now I have this entire range of values to the right which are unsorted. Right? So I will put two indices which I'll indicate in this picture with two colored pointers, a yellow pointer and a green pointer. The significance will become a little clearer once we move a couple of steps in the algorithm. So what we do is that everything to the right of the green pointer, okay, so the green pointer indicates the end of the part which has already been partitioned. So anything to the right of the green pointer is going to be, so anything to the right of this green pointer is unpartitioned. And the yellow pointer, on the other hand, is going to indicate, so this is going to indicate the limit of the lower part, right? So I need, so basically in general I'm going to have this picture. So I'm going to have the pivot here, okay? Then I'm going to have the lower part here, which I've already found. Then I'm going to have the upper part here. So these are the elements I've already scanned and partitioned. And then I have the part that is to do. Right? So in the beginning everything is to do, and there's no lower part, there's no upper part. So what I'm saying is that we will keep these pointers like this, right? So this thing will point to the end of this, and this thing will point to the end of this. So this is what we want to achieve. So we start, as I said, with this picture. So what we do is, if we see something which is lower, then I extend the lower part and I move to the next element. Okay. Again, we see something that is lower, so we extend the lower part. So at this point, what we're saying is that the lower part has two values, 32 and 22, and the upper part is empty, and everything from 78 onwards is not sorted. Now I look at 78, so 78 is bigger than 43, so the lower part stays here, and I now have a non-empty upper part, namely 78. Now I look at 63, once again 63 belongs to the upper part, so again I move this forward. 57 again belongs to the upper part, so I move it forward. 91 again move it forward. So the first interesting thing happens when I come to 13. So now when I come to 13, I find that it must go into the lower part. Okay? But the lower part is far away. So how do I achieve this? So what I will do is, I know that this element to the right of the lower pointer, so this is bigger than P, right? And this element is smaller than P. So one way to achieve what I need is to exchange these two values, right? So I exchange the 13 and 78, right? So I take 13, I label it as lower, and then I exchange and move both pointers, right? So this is a forward partitioning algorithm which keeps reducing the length of the unpartitioned part. Okay. If I see something which is upper, I just move the green pointer. If I see something that is lower, I exchange that lower element with the first part of the upper thing, and then I extend both partitions. Then finally, at this point, I still don't have the final thing because I want this pivot element to be in between these two. Okay. So now the point is that I know that this is the last So what is to the right of the yellow pointer is the first upper limit, and what is to the left of the yellow pointer is the last lower thing. So I can exchange the 43 and the 13, right? And then I get the final array partitioned as I want, with the pivot in the middle, the lower part on the left, the upper part on the right. Okay? So this is how we do quicksort in general. So in general, now remember that after we do this partitioning, we are going to have to quicksort this part and quicksort this part. So the recursive calls will be sorting different segments. So it's useful to say for each call that I'm sorting from some left limit to some right limit. Okay? So in general, quicksort will take the array and it will take 2 pointers. It will say sort from L to R minus 1. Okay? Now if this length is small, in other words, if I have only one value, if R minus L is less than or equal to 1, if I either have only one value or if I have no values to sort, then I do nothing. So this is the base case. So this is a recursive algorithm. If the sorting array to be sorted has only one element, you do nothing. Otherwise, using the terminology of the previous example, we use the yellow to indicate the position of the yellow pointer, and we use green to indicate the position of the green pointer. Okay, so these two variables indicate the position of these two arrows. Okay, so remember that we start to the right of the pivot. So initially we have at the position L, we have the pivot, and R minus 1 is our last index. So this is our pivot P. So our initial thing is to say that put both these pointers here. Right? So initially yellow is L plus 1. So that is this position. Okay, and we start now moving the green. So green starts at L plus 1 and goes until R. So if we see that the green value is smaller than the pivot, so this is the pivot, right? So A of L is the pivot. So if the green value, the value I'm looking at under the green pointer is smaller, then I do this exchange, right? So if I'm here somewhere and I have this green value, then what happens is if this is smaller, then I exchange these two values. So that's what this is saying. Swap A, the position, the element at position yellow and the element at position green in A should be swapped. And then I will also increment the yellow pointer. The green pointer is being incremented anyway at every loop, right? So finally, after this loop, right, I have done this partitioning to the extent where I have the pivot element, I have the lower part and the upper part. And now what I want to do is I want to move the pivot to the center. So at this point I have the yellow pointer here and the green pointer here. Right? So I need to take the last element here and exchange it with the pivot, and that's what this is doing. It's saying exchange the value at position L with the value at position yellow minus 1. Now having done this, now I want to recursively sort. So I want to sort from the beginning L up to and to the left of this yellow pointer. So I sort from L to yellow. And then I want to sort everything on the right. So I start at yellow plus 1 and sort until R. Right? So these are the two recursive calls. But now the important thing is that at this point, everything between L and yellow is smaller than the pivot. Everything beyond yellow plus 1 and up to R is bigger than the pivot. So after these two sorting recursive calls to quicksort, nothing more needs to be done. We are done. So as I said, this partitioning strategy can also be implemented in a different way, and in fact this is the original partitioning strategy proposed by Tony Hoare. So in his original strategy, the idea was to not start from one end and sweep until you claim all the elements, but to start at opposite ends. So you start building up, in some sense, you start building up the lower side from here, and you start building up the upper side from here. And gradually the lower side grows until it can expand no more, and the upper side grows, and then everything is in place, and then you do the final swap as before. So here what you do is you start with, again I will use the same color thing. So yellow refers to lower, green refers to upper. So what I will do is I will take the yellow pointer and keep scanning until I find a value which is not yellow. So 32 is smaller than 43. So remember that we are trying to grow, the yellow partition is the lower partition. So we're trying to include in the lower partition everything smaller than 43, and we're trying to include in the upper partition everything which is bigger than 43. So I keep moving the yellow thing until I find the first error in some sense. So 32 is okay, so I skip over it. 22 is also smaller than 43, so I skip over it. And now I reach a value 72. So at this point my partition ends here, and 72 cannot be included because it's bigger than 43. Now I start on the right hand side and I look for the position where I can include things in the upper thing, but the very first thing I see 13 should not be there, right? So at this point our upper limit is here. So now what I do is I exchange these two values, right? So if I exchange these two values, then this will become 13, this will become 78, right? And then I will be able to shift these two boundaries by 1, right? So this is the basic step in this partitioning strategy. So at the next step, what I do is I exchange the 13 and 78, and now I say that I have a lower thing up to here, and I have an upper thing up to here. So this is the invariant now. We have the lower thing on the left half, the upper thing on the right part, and in between we have the unsorted elements, but we have these two indicators, the leftmost unsorted guy and the leftmost unpartitioned element and the rightmost unpartitioned element. So now again I start doing the same thing. I move the yellow right until I can no longer extend lower. Here I can't extend it anyway because 63 should already not be there, so I cannot move this partition. On the other hand, the upper partition can move because 91 is bigger, so I will move it left. Okay, 57 is still bigger, so I'll move it left again. 63 is still bigger, so I move it left again. And now I find that the right partition indicator has moved to the left of the left partition indicator. So when this exchange happens, then it terminates this partition. So when the right boundary crosses the left boundary, then we have finished partitioning all the elements because there's nothing in between the two elements to be partitioned anymore. So once we have terminated, now we have the same problem as before, which is that we want to move this element to the center. But now remember that at this point, when this thing terminates, the right marker is pointing to the end point of the lower limit. So I can just exchange these two. So I exchange the 13 and the 43. So I take this there and move this here. And then I get my answer. Okay. So if I move this and then I simultaneously move the green pointer, now I have a pointer to the last of the lower elements. I have a pointer to the first of the upper elements. And now I can apply quicksort recursively to this part and to this part. And I'm done. Right? So we will not write pseudocode or describe this algorithm in more detail, but you can definitely try and work out a similar way of keeping these indices moving as we did for the earlier partitioning and see if you can get it right. This is also discussed in many of the books. So both these partition algorithms appear in textbooks and you can choose whichever one you find easier. In both cases, remember that there's basically an invariant condition. There are these two markers and these two markers indicate the part which has already been partitioned, the limits of the lower and the upper part. And then there is an unpartitioned part, and when the unpartitioned part becomes empty, you are done. So we have seen quicksort, which is a divide and conquer algorithm which overcomes the requirement for an extra array as in merge sort. So let's do an analysis of quicksort. So remember how quicksort works, right? You pick a pivot element, say typically this first element of an array. Okay? And then what you do is you partition this into two parts such that you have a lower part which is less than or equal to p, and maybe you have an upper part which is bigger than p, and you move this pivot in between. And then you sort this lower part and upper part separately recursively, and then you don't need to do any combining step because these two things are in the correct position with respect to each other. So the first thing we observed is that this partitioning actually is quite efficient. We can do it in one scan of the entire array, so we can partition with respect to any pivot in order n time. So the question is, how big are the recursive problems? So if the pivot is the median, then you would expect that by definition of the median that these are of size n by 2, because the median is that element which splits the array into two parts. Those half of the elements are bigger than the median, half are smaller than the median. And if we do have this fortunate situation that the pivot is the median, then we end up with a merge sort recurrence which says that t of n takes time 2 times t n by 2 for the two parts, and this is the partitioning step. So it's not the merge step after the recurrence, but the partitioning step before the recurrence. So we have, as we saw in merge sort, this recurrence takes order n log n if we expand it out. But the pivot is in some sense the best case. What do we think is the worst case? Well, the worst case is when the pivot is an extreme value. It's either the smallest value or the biggest value. So if it's the smallest value, then what will happen is that everything will be bigger than the pivot, right? So you will have an upper element set which has n minus 1 values because the pivot is the smallest value, and you'll have nothing on this side. Symmetrically, if the pivot is the largest value in your array, then you would have everything in the lower element set. So this is again be size n minus 1, right? And the pivot would be something which is on one extreme end and there's nothing in the upper set. So now what we see is that in order to sort this array of size n, I have to then sort a smaller segment which is only n minus 1. It is not no smaller than n minus 1. So I have Tn takes Tn minus 1 plus n. N is the time taken to partition. And Tn minus 1 again in the worst case will have again a pivot element which is an extreme value. So for example, supposing we start with a already sorted array like 1, 2, 3, 4, right? Then what happens is that we pick 1 as a pivot, right? And then this then results in us wanting to sort 2, 3, 4, and then I'll pick 2 as a pivot, right? And this results in us wanting to sort 3, 4, and so on, right? So if I have an already sorted array, in some sense, the pivot is always an extreme value, so the next step splits the array very badly. And of course, if we expand out this Tn is Tn minus 1 plus n, we get the summation that we got for selection sort and insertion sort, so this becomes order n square. So the worst case of quick sort is actually order n square, which is the same as the worst case for selection sort and insertion sort. So why do we bother with this much more complicated algorithm quick sort when we already know several intuitive algorithms which are order n square? So it turns out that quick sort, we can show, actually does not behave in this worst case way in a very frequent manner, right? So we can actually compute, in the case of quick sort, what is called the average case complexity and show that it is n log n. So we will not actually show that it is n log n, but we will try to at least explain what it means to compute the average case analysis of quick sort. As we said in the beginning, average case is very difficult to compute, so let's see what it involves to do this. So the first reason why the average case is difficult to compute is because we need to have a way of describing all possible inputs. Now, even for a sorting algorithm, all possible inputs is an infinite space. Supposing I just take arrays of a fixed length. Supposing I take arrays of length 4. So I could have an array which look like 43, 12, 38, and then 62. Right? So this is an array with 4 elements. I could have another array of 4 elements, which is say 72, 21, 63, and 95. Right? But in this way, we can continue and put any elements we want, and there are infinitely many arrays of size 4. But there is a commonality between these, which says that the first element is bigger than the second element. In fact, the second element is the smallest element, and so on. Right? So if we look at this, we can say that there are 4 elements, and if we think of them in order, then the smallest element is here, the second smallest element is here, the third smallest element is here, and the fourth smallest element is here. So I can actually think of this as the array 3, 1, 2, 4. It has 4 elements, and the 4 elements are ordered in this way. So the actual values are not important, only the relative order matters. So we can actually think of inputs of size n to be these kind of reorderings of 1 to n, or permutations of 1 to n. Now among these permutations, we don't have any preference. Any one of them could come as our input, right? So we all know that there are n factorial such permutations, and we say that each of them is equally likely, so each of them has probability 1 by n factorial of occurring. Now we look at all these n factorial inputs of size n and see how our algorithm behaves. So we will not do the actual calculation, but if you see the average, you see the actual time it takes for all these n factorial inputs, add it up and divide by n factorial, which is what is in probability known as calculating the expected running time. Okay, then you can show that this is actually order n log n. So we have not shown it, we have just explained what is the mathematics required in order to show this, but in quicksort you can prove that the expected running time across all possible random inputs, equally likely inputs, is actually order n log n. So though quicksort has an O n squared worst case, on the average it behaves like merge sort. And without some of the pitfalls of merge sort, in particular, it doesn't require this extra space in order to create a merged array. Now you can actually exploit this average case behavior in a very simple manner. Right? So why does this worst case occur? The worst case occurs because the pivot that we choose could be a bad pivot. As we saw, if you took the first element as your pivot, then a sorted array becomes a worst case because every time the pivot is the extreme element. On the other hand, you could take the last element and you would have the same problem. If you pick the midpoint, again you can make the middle point of the array that you start with the extreme element, and you can then work backwards and construct always a worst case which takes order n square. So what we are saying is that for any fixed strategy, if I tell you in advance that I'm always going to compute the position of the pivot in a fixed way, then by working backwards, you can always ensure that that position in the current problem, you have a worst case that is an extreme input, and reconstruct something which will take O n square for that strategy. So the solution is to not fix the strategy. Each time I want to apply quicksort to a recursive subproblem, I have some position 0 to n minus 1 which I need to pick as the pivot. But rather than telling you that it's going to be 0 or n minus 1 or the midway between 0 and n minus 1, I will say that I will choose any one of these values with equal probability. So think of it as choosing a random number between 0 and n minus 1 equally likely. Or if you want to think graphically, it's like throwing a die. So a die has, say, 6 faces normally. So if you roll a fair die, you'll get any number between 1 and 6 with equal likely. So now we have an n-sided die. So we have a complex kind of object, we throw it, and whichever number comes up, we pick that as a pivot. So now the behavior of this algorithm is not fixed, right? It depends on how this die rolls. So this is a different type of algorithm called a randomized algorithm. Right? So you can now implement quicksort in a randomized way with a very simple randomization step, namely just pick the pivot at random at each call to quicksort. And it turns out that again you can do a similar calculation saying that across all the possible random choices I make for the pivot, the expected running time is order n log n. So there's a very simple, this is a kind of a dual result to the fact that the average case is n log n. You can exploit that by creating a very simple randomized strategy in order to achieve this n log n thing with good probability. The other aspect that we mentioned about merge sort, which is a bit limiting, is that it's inherently recursive. Now our solution to quicksort avoids this duplication of space, but it is recursive. Now it turns out in quicksort you can actually manually make the recursive algorithm iterative. Okay? So the point is that the recursive calls work on disjoint segments. So what you need to remember in the recursive call is not the entire segment, but just what segment you need to work on. You don't need to combine the results. So we will not discuss this in great detail, but it turns out that you can use a stack. You can actually maintain your own stack, and every time you make a recursive call, you just store in the stack the left and right endpoint of what segment needs to be sorted. And in this way, you can actually take the recursive algorithm that we wrote before and convert it to an iterative algorithm. Now, why you would like to do this in general is because you have a trade-off in recursion versus iteration depending on your programming language. Because when you make a recursive call, when you make a function call in general in a programming language, what happens is the current function that you're computing has to be suspended, right? So you need to suspend and resume, right? So when you make a recursive call, you have to put aside whatever you have, and then you have to take a new set of local variables. So in the memory of the program, you have to load some new data, then you have to execute the function. When it terminates, you have to throw that off and restore the context. So you have to resume. So this takes some time and it takes some resources. And so usually the cost of making a function call, even though we might account for it in our complexity as a basic operation, is much more than doing some really arithmetic operation like addition or something. So in particular recursion, every time you make a recursive call, you're basically going and replacing something on the stack with some new frame and then putting it back, and this takes time. So it is in general, sometimes for efficiency purposes, good to convert recursion to iteration. On the other hand, this process can make the algorithm more obscure, and many programming languages actually or optimizing compilers can try to do this automatically. So maybe this distinction between recursion and iteration does not always help so much, but it's useful to know that certain algorithms can be done both ways and certain algorithms is difficult to do one way. So a final remark before we leave quicksort for now. So in practice, quicksort is very fast. As we said, the worst case happens very rarely. For this reason, typically quicksort is the default algorithm that you see that people use when you have a built-in sort function. So if you have a spreadsheet and it allows you to sort a column, then usually the algorithm running in the background to sort that column is quicksort. Or if you have a built-in sort function, for example, C, C++, Java, all allow you to just call sort. Even Python just allows you to just call sort. In almost any programming language, the sort function that is available to the programmer by just a simple call is usually an implementation of quicksort. Of course, this implementation may use various optimizations such as the randomization and other things to make it faster, but at the underlying algorithm, the heart of it is usually quicksort. So let's look back on all the different sorting algorithms that we have considered. So one of the important criteria that we should not forget is that sorting often happens in phases. Right? So we might have a list of names of people, say Ashwin, Bharati, Chandar, and Deepa. Right? So we have sorted this in order, and they might have got some marks in an exam. So they maybe got 60, 43, 60, and 95. Now we might want to sort this by marks. So when we sort this by marks, of course we need to exchange the position of Bharati and Ashwin, but we don't want to exchange the position of Ashwin and Chandar. So in other words, we don't want to disturb the sorting of alphabetical order. So the final answer should be Bharati has 43, Ashwin has 60, Chandar has 60, and Deepa has 95. Okay, but it would be wrong if we said Chandar and then Ashwin. Not wrong, but undesirable. Right? So if we have a list of students in alphabetical order and then we sort by marks, we would expect that those with equal marks are still sorted in alphabetical order. So in a spreadsheet where we have a kind of a table with columns, so supposing we sort by this column and then we sort by this column, okay, the second sorting should not disturb the order of the first sorting. So this is called stable sorting. That is, if there was, so very often when you're sorting on one attribute, but there may be other attributes. So a data item is not typically a unique value. It's not just a number, but it's a, so you're taking names, marks, and various other things, address, maybe phone number, and you might sort on different. So think of a spreadsheet where you might sort on different columns. So each successive sort should not disturb the previous sort. So this is called stable sorting. So this is obviously desirable because we do it all the time, and we would be very unhappy if the next round of sorting disturbed our first round of sorting. So which of our algorithms is stable? So quicksort, as shown, is not a stable operation. So remember that we took the pivot, right? And in the, at least in our implementation, what we did was we constructed this lower set and then this upper set to the right of it. So, right, so this is the picture we had, and then finally, and this is the crucial point, we do this swap. So imagine that we have a situation where here we had, for example, at this point Ashwin with 60 marks and Chandar with also with 60 marks, right? So at the point of constructing the lower set, they were in the correct order as in the original input. But now after swapping, what happens is that the pivot has come here and Chandar with 60 marks has gone here, right? So this swapping operation has basically reversed the order of A and C with respect to what it was in the input, and henceforth, therefore, this order will get jumbled. So the swap operation during partitioning disturbs the original order, right? And this also happens in things like selection sort, because in selection sort, wherever we do this long distance thing, so remember in selection sort, we pick the minimum and then we exchange it at the beginning. Now, if the element at the beginning had the same alphabetical order as, I mean, it's smaller in the second one, now it moves to a later point in the array and the order gets disturbed. So any kind of long distance swapping is very dangerous for stability. What about merge sort? Well, merge sort would normally be stable provided all we want is that something to the right should not go to the left of something in the original array. So we don't want if we have two elements here and here which should remain in this order, we don't want them to be exchanged. Now, why would they be exchanged? They would be exchanged only if they were equal, right? That's the only case where stability gets destroyed, where equal elements are disturbed with respect to their previous sorting. So we have to make sure that no element from the right comes to an element to the left of something from the earlier array. And when we are merging, basically that's why we said that in the case AI is less than or equal to BJ, we pick from A, and only, so if we had made the mistake of writing less than and then we use greater than equal to select from B, then when they're equal, we would first pick from B and not from A, and that would create instability, right? So crucial in our merge operation is that when AI is less than or equal to BJ, we pick the element from A in preference to B. So this preserves the left-right order of equal elements with respect to the original order, and since merge sort, as we have done, is stable. You can also check that similarly if you do insertion sort carefully, then insertion sort is also stable. Now this is not to say that quicksort cannot be made stable, it's just that the way we have implemented it, quicksort is not stable. Another criterion which is related to what we just saw is that we have only concentrated on the number of steps required in order to compare and exchange two elements. But you might want to do other things. For instance, you might want to penalize movements which take you across large segments of the array. So you might want to say that it is not so good to exchange things far away, it's better to exchange things near each other. So something like bubble sort, which we didn't look at, which only exchange adjacent elements, would be better than something like selection sort, which exchange across large intervals. Now, this could happen if data has a cost, and supposing you're sorting an array, but this array is across different, it's so big that it's not stored on a single server, then each time you want to swap from one server to another, you could pay an extra cost which is different, right? So in other words, there might be different criteria which are behind the scenes which we don't see. Okay, so imagine when you're sorting something by hand, supposing you're sorting a bunch of heavy cartons, then you can imagine that moving a heavy carton a long distance is more expensive than moving it a short distance. Right? So there could be other criteria which govern your cost of sorting, which we have not considered at all in this, and people have looked at these things in the literature. So very often the question is asked, which sort is best? So unfortunately, it turns out that no single sorting algorithm is always guaranteed to be the best. It really depends, as we said, like sorting on the movement and other criteria. Some sorting algorithms may work well in some contexts, some in another context. In most memory-based contexts for simple arrays, quicksort is the best. And this is why, as we said, quicksort is usually the default implementation of choice for built-in sorting algorithms, provided we do something intelligent about choosing the pivot and various other things. On the other hand, when we have to move a lot of data, sometimes we cannot store the entire thing. If we are sorting a database, we cannot sort the entire thing in the memory. So actually we use a variation of merge sort, which is called external merge sort. So it really depends on the context. Sometimes you use one, sometimes you use another. If there were a best algorithm, there would be no need to study the other algorithm. So the very fact that many of these algorithms are studied shows that in different contexts, you might need to use one or the other idea in order to make things work better. We have seen merge sort as an order n log n algorithm. There are other n log n algorithms. We will see one later on in this course called heap sort. The main thing to remember is that if we have a naive n squared algorithm, which is not like quicksort provably n log n in the average case, then this will only work for small data. However, sometimes for small data, the simplicity of a naive algorithm beats the complexity of a complicated algorithm. So you could even have hybrid algorithms, right? You might use divide and conquer when n is large, and then when n becomes small, then you switch over to maybe insertion sort. Okay? So there are many different strategies that people use, and very often experimentally they arrive at some combination of strategies. So it's not enough to say that one algorithm is the best. You need to have a good idea about what works and what doesn't work so that you can tailor your sorting procedure to suit your requirement. So when we design an algorithm for a problem, we need to represent the information of the problem in a way that we can manipulate. So this is called modeling. So we need some kind of notation and structures to model the problem. So in this module, we will look at a very important class of structures called graphs, which are immensely useful in many different contexts. So let's start with the problem of coloring a political map. So here is a map of the states of India, and as you can see, the different states have different colors. Now what is the principle behind this coloring? Well, when we color a state, we must make sure that no state adjacent to it has the same color. No two states which are side by side that share a common boundary should have the same color, because otherwise it's difficult for us to distinguish one state from another. Right? So we can see that Rajasthan has a different color from Gujarat because Rajasthan and Gujarat at this point share a common boundary, right? Similarly, Rajasthan and Madhya Pradesh have a boundary, therefore Rajasthan and Madhya Pradesh have different colors. On the other hand, Rajasthan and Telangana don't share a boundary, so we can use the same color for Rajasthan and Telangana. So the question we may ask is, given such a map, how many colors do we need to color it to satisfy this criteria? Now clearly we can assign every state a different color, and thus we can ensure that no two states which have a boundary in common, in fact no two states anywhere in the map have the same color. But in many situations we might expect to do with much fewer than that many colors. So our question is, how many colors do we need? So here is a way to represent this problem more abstractly. So the first thing we do is that we actually assign to each state in the map a black dot. Right? So roughly where the state, at the center of the state, we place these black dots. Now we have to record the information about how these states are neighbors of each other. So what we do is we connect every pair of states that share a boundary. So as we saw, Rajasthan and Gujarat have a boundary in common, a border, and so we put this kind of an edge between Rajasthan and Gujarat on this map. Now our coloring problem is to assign colors to the states so that no two states which share an edge, which are on opposite sides of an edge, have the same color. Right? So coloring the state is the same as coloring the dot associated with the state. So we can start, for example, with a state like Uttar Pradesh and give it a red color. Now if this is red, it means that states which are near it, such as Uttarakhand or Haryana or Rajasthan or Madhya Pradesh or Chhattisgarh or Jharkhand or Bihar, none of these can now be colored red because they are all neighboring states. So in the next step, having colored Uttar Pradesh red, we have now colored Haryana a different color, say blue, and Uttarakhand, which has a common boundary with both Haryana and Uttar Pradesh, is now colored green. So we have used three colors. If we proceed to Rajasthan, we find that Rajasthan does not share a boundary with Uttarakhand. So it is possible to reuse the green color. So with sticking with three colors, we can extend our coloring to Rajasthan. When we get to Punjab, now Punjab is not even connected to Uttar Pradesh. So we can reuse the red color of Uttar Pradesh for Punjab. Okay. However, when we come to Himachal Pradesh, we find that Himachal Pradesh is connected to Punjab and Haryana and Uttarakhand. And therefore, we have already used up these three colors and we must use a fourth color for Himachal Pradesh. So if we keep continuing in this way, we can eventually assign colors to all the states in the country which satisfy this particular property, that whenever I see two dots, if they are connected by a line, then the two dots have different colors. Right? This captures abstractly the property that we want any two states with a common border to have different colors on the map. So now if you look at this map coloring problem, the actual map underlying these dots is now not necessary anymore because the dots capture everything about the map. So we can actually throw away the underlying picture and just keep this pattern of dots and the connections between them. And if we assign colors to these dots, keeping in mind that these lines represent common boundaries, we are solving the same problem as solving the original map coloring problem. So this kind of a diagram is what we call a graph. So these dots are called vertices, right? These are the vertices. They are also called nodes. So there are two words to describe these, nodes and vertices. It's useful to know that vertices is the plural of vertex. So vertex is one node, many nodes are called vertices. Okay? And these connections are the edges. So we have edges between vertices. So it's very simple. A graph is just a picture. It consists of some dots, which are nodes or vertices, and some connections between them, which are called edges. So the problem that we have solved is called graph coloring. So we used 4 colors. Okay, so you can check that we have used 4 colors. We have used blue, green, red and yellow, and we have managed to color this entire graph with just these 4 colors. Now you might ask, is it a property of this graph or is it a property of all graphs? So in fact it turns out that if you take any map of the kind that we drew and convert it into a graph like we did, 4 colors are always enough. Now this is a mathematical fact about graphs. So you can take a particular problem about coloring a particular map, and then we can ask a general question about all maps of this kind, and we can actually prove a mathematical fact about it, or a theorem. It says that in any map which is derived from this kind of any graph which is derived from this kind of a map, 4 colors are enough to solve the graph coloring problem. Now this is not an easy problem to solve. It was an open problem for many years, and it was a very celebrated theorem when it was actually proved. Now you might observe that though we have found a coloring of this map using our graph with only 4 colors, the original map which we started with had many more than 4 colors, right? So we have this, if you look around, you'll find 1, 2, 3, 4, and then 5, at least 5 colors on this map, 6 if you include this white and so on, right? So though we have a theorem that we can use 4 colors, in actual practice, the person who has colored this map has used many more than 4 colors. So one of the advantages of moving to a representation such as a graph is that we have thrown away all the inessential features of the problem. We don't need to know the shape of the state. We don't need to know its size. We just need to know which state is connected to which state. That is, which state is the border of which state. Okay? So now once we have the graph, then we can redraw the graph. For instance, we can expand out these kind of crowded portions to make the connections more obvious. And we can work with this modified graph, and the solution to this modified graph is exactly the same as the solution to the original graph. The problem doesn't change. Right? So one of the most important features of modeling a problem is to keep the essential parts of the problem and to throw away the inessential parts so that you can focus on the problem that actually needs to be solved. So another problem that we have seen, which is easily representable as a graph, is that of an airline routing. Right? So when we have airline routing, you might ask, given the routes of an airline, which are represented in this kind of format by cities and arrows between them indicating flights in one direction, you might ask questions about connectivity. Can I go from New Delhi to Trivandrum without changing airlines? Right? So this is again a problem where we can focus on the connectivity and throw away the actual graph. It doesn't really matter to us the actual map. It doesn't matter to us how far apart these cities are, where they are with respect to each other. All we are interested in knowing is which city is connected to which city by a flight, and given this, what kind of routes can I find between pairs of cities. So formally, a graph just consists of two parts. There's a set of vertices or nodes, okay, which is normally written V, and there's a set of edges which are pairs of vertices. Right? So each edge is a pair V comma V prime. Now if we have a graph of the kind that we had for the map where we were coloring it, then we don't distinguish whether V is before V prime or V prime is before V. When we say that two states share a common boundary, it doesn't matter which order we mention them in. So there is an edge between V and V prime if and only if there's an edge between V prime and V. So there's only one edge between any pair of vertices. On the other hand, in the airline graph, we had directions. We might have a flight from one city to another city, but not back. We had these triangular kind of things where we could go from one city to another, there and back. So this does not mean that you cannot go back directly on this direction. So these are directed graphs. So if we have an edge from V to V prime in a directed graph, we don't guarantee that there's an edge from V prime to V. And as we saw, we can now easily describe these kind of graphs as pictures by just drawing the nodes and then connecting the edges as lines. Okay, so either undirected, or we could have a directed graph in which we draw lines with arrows to indicate the direction. So the graph coloring problem is a problem on an undirected graph. And we can formally say that the problem is to find a coloring C. A coloring C is a function that assigns to each vertex V a color C of V. Right? And in terms of the graph, when we have an edge V, V prime in our edge set, then C of V should be different from C of V prime. This is what it means to be a legal coloring. Right? So we can now take this graph as a mathematical object and describe the problem to be solved in a completely objective way as a mathematical problem in terms of the vertices and the edges. Similarly, we can express the problem of finding a root in the mathematical sense. Initially, our problem is a directed graph. Then we identify the vertices corresponding to the cities where we want to find the node. So here we have V0 represents New Delhi and V5 represents Trivandrum, and our goal was to find a route from V0 to V5, from New Delhi to Trivandrum. So such a route can be described as a path. Right? So a path is just a sequence of vertices connected by edges. So we want to find a sequence of vertices such as the first vertex V0 is where we want to start, the last vertex Vk is where we want to end, and each pair of vertices along the path Vi plus 1 is a flight, right? Is an edge in our graph. Now, it's not required that a graph needs to be directed for this problem to make sense. We could take the same graph and we could assume they are undirected. That is, the airline actually serves all pairs of cities in both directions. And the problem still makes sense. Right? So now we have an undirected graph, but we say that V0, V1 is an edge, means V1, V0 is also an edge. We can go backwards and forwards. And the same question now, can we find a sequence of vertices which starts at V0, goes to V5, such that every pair on this path, every Vi plus 1 is an edge in it. So we have seen that graphs are very useful mathematical structures for modeling problems. But when we write an algorithm to solve a graph theoretic problem, we need a way to represent and manipulate the graph in our algorithm. So we'll look at that in this lecture. So recall that a graph is a set of vertices or nodes V connected by a set of edges E. We can have two types of edges, undirected edges and directed edges. An undirected edge is drawn as just a line between two vertices, and it represents the fact that V and V prime are connected. Doesn't matter whether we call this edge V comma V prime or V prime comma V, there is only one edge. On the other hand, in a directed graph, we actually associate a direction with an edge. So we could draw an edge from V to V prime, and this we would write in our edge set as a pair V comma V prime, saying that the start vertex is V and the end of the edge is V prime. And this is not the same as having an edge from V prime to V, which will be written as V prime comma V. Okay, so directed graphs, the order of the vertices when we mention the edge matters. In an undirected graph, it's just a pair of vertices. It doesn't matter whether we think of it as V to V prime or V prime to V. It's just a connection between these two pairs of vertices. So we saw two typical problems involving finding a root, which can be represented for both undirected and directed graphs. So in a directed graph, we were looking for a path from V0 to V5 such that each pair V0, V1, V1, V2, etc. These are directed edges in our graph. At the same time, we can make the same graph undirected, and again we are looking for a path where we start at V0 and every adjacent pair V0 to V1, V1 to V2 is an edge such that we finally end up in the target vertex V5. So the problem that we have abstractly, let us stick to undirected graphs, is that we are given for this at this point an undirected graph, and we are given a source vertex Vs and a target vertex Vt, and we are asked whether there is a way to go from Vs to Vt in this graph. Now what we did in the previous graph and what we can do as human beings is to take a look at the graph and see if we can visually identify such a path. Just see if Vs and Vt are connected. Okay? But when we write an algorithm to manipulate a graph, how do we get the algorithm to look at the picture? So for us, a graph is a picture, and we can easily look at the picture if the graph is not very complicated and try to understand the situation. But how do we make this picture available to an algorithm? We need a way to represent this picture, that give the graph as input to our algorithm. So let's make some assumptions. Okay? In any graph that we consider, there will only be a finite set of vertices. So if there are n vertices, to simplify life, let us just name these vertices 1, 2, up to n. Right? So our vertices are always going to be 1, 2, 3, 4 up to n. So therefore now an edge is a pair of numbers I comma j. Okay? So the first representation we can have is to just record which pairs I and j are connected. So this is called an adjacency matrix. We say in this matrix Aij is 1 if and only if Ij is an edge. Right? So when we write such a matrix, then if we take a graph like we had before, we would now rename the vertices 1, 2, 3 up to 10, because there are actually 10 vertices in this graph. And then we would write this matrix which says, for instance, there is an edge from 1 to 3, and therefore the entry A13 is 1. There is no edge from 1 to 5, right? And therefore the entry A15 is 0. So in this way, for every edge that we find in the graph, say for example A45, we will find an entry in the graph which says A45 is 1. Now remember that this is undirected, so if there is an edge 545, there is also an edge 54, and so we will see that actually there is a matching edge 54. So this graph is actually, this matrix will actually be symmetric across this diagonal. So if I see a 1 above the line, I will see a 1 below the line, because 8, 9 is the same as 9, 8 as far as our undirected edges go. So this is an adjacency matrix. So now what can we do with an adjacency matrix? Well, one thing we can do, for example, is find all the neighbors of a vertex. Supposing we want the neighbors of a vertex I, then we want to look at the row I and look at all the entries 1 in that row. For example, we want to look at the neighbors of vertex 4, we look at the row 4, then 4, the entry 4 comma 1 indicates whether or not 4 1 is an edge. It is, so we get 1 as a vertex. Then we walk further, and then the next one is at 4 comma 5, so 5 is a neighbor, and then the next one is an 8, so 8 is a neighbor. Right? So in order to find the neighbors of a vertex I, we go to the row labeled I and we scan the row from left to right, and each one that we find, the corresponding column is a neighbor. Now how do we find a path? Well, we can now look at neighbors and then neighbors of neighbors and so on. So we start with the source vertex. In our problem, if we look at the numbering that we gave, New Delhi corresponded to the vertex labeled 1 and Trivandrum was a vertex labeled 10, and we wanted to know whether we can get from vertex 1 New Delhi to vertex 10 Trivandrum. Okay. So what we do is we start at vertex 1 and we know how to find the neighbors of 1. So we will say that every vertex, any neighbor of 1 can be reached from 1 by 1 flag. Right? So we start with the vertex 1, which we have already started. We can reach because we start there. Now we scan its neighbors and then we find that there are these 3 neighbors, 2, 3 and 4. Okay. So therefore now we can conclude that if we start at 1, we can definitely reach 2, 3 and 4. So let's color these rows also green. So now we have indicated that in one step from 1 we can reach 2, 3 and 4. Now anything that we can reach from 2, 3 and 4 can also be reached from 1. So we now focus one by one to the neighbors that we have explored and look at their neighbors. So we move down to the neighbors of 2. Right? So 2 has only 2 neighbors, 1 and 3. And it turns out that both 1 and 3 have already been marked as being reachable from 1, so we do nothing about this. So the cities reachable from 2 do not add any information to our problem. So we move on to 3. Likewise, 3 can reach 1 and 2, both of which have already been listed as visited, or which can be reached from 1. So we can again skip over to 4 because 3 has nothing new to tell us. Now when we reach vertex 4, it has something new to tell us, because now from 4 it says you can reach 1, of course, which we know, but we can also reach 5 and 8. Okay. So now we will now, in our representation, we will indicate that 5 and 8 are colored green to indicate that these are also reachable from 1 by an indirect path. I can go from 1 to 4 and then from 4 to 5 and 8. So I've already processed 1, 2, 3 and 4. So the next I look at the vertex 5 to see if 5 can give us any new neighbors. So we look at 5, right? And now 5 has a neighbor we've already seen 4, but it has a new neighbor 6 and another new neighbor 7. So if I process 5, I get 6 and 7. Now I can look at any of 6, 7 or 8. So let us look at 8. Okay. So 8 has neighbors 4 which I've already seen, 6 which I've already seen, but it has a new neighbor 9 which I've not seen. So I add 9 to the list of neighbors which can be reached eventually from 1. And now if I look at 6, I find that 6 can reach 5, 7, 8 and 9, all of which are already known to be neighbors or reachable from 1. So I don't have any new information. Likewise, when I go to 7, I can reach 5 and 6, which I already know are reachable, so there's no new information. And finally, the vertex which I have not yet examined is 9. So from 9, I can reach 6, which I know, 8, which I know, and there is a new vertex 10. So I can reach 10 from 9, so I mark 10, and once I mark 10, my problem is solved. I have found that there is a way to go from 1 to 10 by systematically expanding the set of neighbors I can reach one level at a time. Right? So this gives us an algorithm. We will make this algorithm more precise as we go along. But you can see that using this representation as an adjacency matrix, we can take this matrix and use it to actually explore the problem that we have at hand and make it into a kind of a reasonable procedure which we can execute effectively. So to make this algorithm more precise, we need to make this algorithm more systematic. We have to keep track of the vertices which have been visited so that we don't keep exploring the same vertex again. Right? So we don't want to keep going around in circles and doing the same problem again and again. So it will turn out that there are two fundamental strategies to solve this particular problem, which is one of the most basic problems in graphs, which is to find out what is connected to what. Right? So the strategy that we executed is what's called breadth first. That is, we first explore all the neighbors of the starting vertex, then all the neighbors of these things which are one step away, all the neighbors of things which are 2 steps away, and so on. The other strategy is to go as far as possible in one direction. So you pick one neighbor of the starting vertex, then you pick one neighbor of the new vertex, then you pick one neighbor of that new vertex, and so on until you cannot find any new vertices. Then you go back and explore another neighbor of a previous vertex, and so on. And this is called depth first. So we will see these algorithms in detail in a later lecture. So one of the things that you can observe is that most of the entries in this matrix are actually 0. So remember that if we have n vertices, this matrix is size n square because I have n rows and n columns. Now, if you count the number of edges in an undirected graph, then each pair of vertices can be an edge. We normally disallow self loops. We normally don't consider edges from I to I for a vertex I. Right? And the number of different pairs is n choose 2. These are how many ways you can pick 2 vertices. So if we pick all the pairs, then it is n into n minus 1 by 2. Okay? So this is a basic combinatorial fact. So we could have about n squared edges, no more. And if we have about n squared edges, then many of these entries in this matrix will be 1. But in most situations, the number of edges is much less than n squared. So this is a wasteful representation in some sense because we are recording a lot of zeros in order to capture the positive information which is in the ones. Right? And also remember that these ones are symmetric. So for every one above the line, I have, so if I draw this diagonal, for every one above the diagonal, I have a symmetric one below the diagonal. So actually half of this matrix is useless. If I just know this top half, it's enough. And in this top half, I will have mostly zeros. So we can think of another representation where we only keep the relevant information at hand. So this is what is called an adjacency list. So what we do in an adjacency list is that we explicitly maintain for every vertex the list of its neighbors. So we say that 1 is connected to 2, 3 and 4. So we say that the list connected to 1 is 2, 3, 4. Similarly, 2 is connected to 1 and 3. So we have the list connected to 2 is 1 and 3. Right? So this is a node and these are the neighbors. So now in this representation, whenever I have a node, I just go to the entry for that node and I look up the list and I can scan its neighbors and I can get it in time proportional to the number of neighbors of that node. Right? So there is an advantage that I don't have any useless information because I'm not storing all the zeros on the adjacency matrix here. I'm not keeping the non-information, which vertices are not connected. So these two representations have their advantages and disadvantages. In an adjacency matrix, we need much more space than an adjacency list. But some questions are easier to answer in an adjacency matrix than in an adjacency list. If we want to know whether vertex j is a neighbor of vertex I, we just have to probe one entry in the matrix. We just check if aij is 1. On the other hand, in an adjacency list, if we want to find out if j is a neighbor of I, we need to go to the entry for I and scan the entire list. So this is similar to the original discussion we had at the beginning of the sorting module on the difference between matrices and lists. Right? So here we can probe this entry aij in unit time, whereas we need time proportional to the number of neighbors of I to find out whether j is a neighbor of I in an adjacency list. On the other hand, if we want to actually find all the neighbors of I, then regardless of how many neighbors are needed, in an adjacency matrix, we have to scan the entire row. So if there are n vertices in the graph, then even if a node has only 2 or 3 neighbors, we will have to look at all n entries in the row to determine which of these n entries are the actual neighbors. On the other hand, in an adjacency list, as we have seen, we record exactly those vertices which are neighbors, so the time to scan the neighbors is directly proportional to the neighbors. So if each vertex has only a small number of neighbors, then an adjacency list will quickly give us those neighbors, whereas adjacency matrix will require us to scan order n entries to find out that small number. So let's look at a formal algorithm to explore a graph. So recall that a graph consists of a set of vertices and a set of edges. The edges are the connections between the vertices. They may be directed or undirected. So if we look at an undirected graph, the problem we are looking at is to find out whether a source vertex is connected to a target vertex. And we said that this amounts to finding a path from V0, the source vertex, to Vk, the target vertex, where each pair of vertices on the path is connected by an edge in the graph. So we argued that we could easily do this for small graphs visually but if we want to write an algorithm, we need a way of representing the graph. So the first thing we decided was that we would name the vertices 1 to n. So if we have n vertices, we will just call them 1, 2, 3, 4 up to n. Then we can represent the structure of the graph through an adjacency matrix. In this adjacency matrix, the ijth entry indicates the presence or absence of an edge from vertex I to vertex j. So aij is 1 if there is an edge, aij is 0 if there is no such edge. In this matrix, if we want to find out whether a pair of vertices are directly connected, we just have to probe the appropriate entry. So we can do that in constant time. To find all the outgoing neighbors of a vertex, we have to scan the row for that vertex. So that takes linear time in terms of the number of vertices. Now, one thing we observed is that typically in many graphs, this matrix is largely 0. Most pairs are not connected. So we can get a more compact representation by just listing out the neighbors of each vertex. So instead of keeping a row of ones and zeros, we just record those vertices whose entries are 1. So this gives us a more efficient representation for graphs where the number of edges is closer to the number of vertices. But in this case, in order to find out whether a given pair ij is connected, we have to look at the list for I and see if j appears in it. Now our strategy for finding a path connecting a source vertex and a target vertex was as follows. We would start at the source vertex and keep exploring the graph systematically. Each time we went to a vertex, we would mark it as visited. And then we had to make sure that when we were exploring vertices, we did not re-explore the same vertex twice. So we said there would be two fundamental strategies, breadth first and depth first. So today we are going to look at breadth first search. So the idea of breadth first search is to explore the graph level by level. So we start at the source vertex and we now explore all the vertices which are one step away, connected by a direct edge to the source vertex. Then we look at all vertices which are newly connected one step away from level 1 vertices. So these are 2 steps away from the source vertex. And then for 3 steps and so on. Now while we are doing this exploration, we have to keep track of 2 quantities. We have to first note, of course, whether a given vertex has been visited. Has it been explored? Is it connected to the source vertex? Also for each such vertex, we have to explore its neighbors. Right? So for each vertex, we need to know A, has it been visited? And we may not be able to explore it as soon as it is visited. So we need to remember that we have explored it or not explored it. And those which are not explored, we have to make sure we explore them once. So the way to do this is to use some data structures to keep track of these quantities. As we said, the set of vertices is numbered 1 to n. So we can keep an array visited with entries 1 to n, which tells us whether or not vertex I has been visited. Now, whenever we visit a vertex, we need to subsequently explore it. Since we may not explore it immediately, we may have to keep it pending for a while. So we have to keep a collection of these vertices which have been visited but which have not yet been explored. There are many ways to do this, but one natural way is to explore them in the order in which they were visited. So if you want to explore in the order in which they were visited, a natural data structure to keep the list of unexplored but visited vertices is a queue. So we put each visited vertex into the queue the first time we come to it, and then we process all the vertices in the queue until all vertices have been explored. So here is some high-level pseudocode for breadth first search. When we reach a vertex I, which we have visited for the first time, we will eventually explore it. What does it mean to explore a vertex? We look at the outgoing edges I, j. If j has already been visited, we have nothing to do. On the other hand, if j has not been visited, then we will mark it as visited and add it to the queue to be explored later. So we begin by marking the source vertex and adding it to the queue. And at each stage, we will explore the vertex at the head of the queue. If at some stage there are no vertices in the queue, it means that every vertex we have visited has been explored, and so there is no new information left and we can stop the exploration. So before giving the actual code for breadth first search, let's work out the example that we have and see how these data structures are updated. So we have these 10 vertices 1 to 10, and we are looking for paths starting at 1. So in the queue, we have 2 pointers as usual. We have a pointer which we indicate in green, which is the head of the queue, and a pointer red, which is the tail of the queue. So we initialize the queue to have the starting vertex 1, and we also mark this vertex as being visited. Now we have to explore 1. So what we do is we remove 1 from the queue and systematically check each of its outgoing edges, and if those target vertices are not already visited, we add them. So 2 is the first in order of 1 to 10, first neighbor of 1. It has not been visited, so we add it to the queue and mark 2 as visited in the visited array. Likewise, we mark 3 as visited, and then we mark 4 as visited. At this stage, we have finished exploring vertex 1. So now we go back to the queue and see if there is anything yet to be explored which has been visited, and there is. So we pick up the first such, namely 2. So we remove 2 from the queue and we explore its outgoing neighbors. Now the outgoing neighbors of 2 in this case are 1 and 3. But since 1 and 3 are both visited, we have no work to do, and we go on and go back to the queue. So in the next stage, we pick up the vertex 3 and we look at its outgoing neighbors. Again, it has outgoing neighbors 1 and 2, both of which are already visited, so there is nothing to be done. We come back to the queue and pick up 4 and try to explore it. So 4 has a neighbor 1 which has already been visited. The next neighbor is 5. Since 5 is new, we add it to the queue and we mark it as visited. And then it has a neighbor 8. So we add that also to the queue and mark it as visited. Now we have finished exploring 4. So we go back to the queue and look for the next thing to be explored, which in this case is 5. So 5 has got neighbors 4, 6 and 7. 4 has already been visited, but 6 is new, and so is 7. Now we go back and explore 8. So 8 has neighbors 4, 6 and 9. 4 and 6 are old, but 9 is new. So we add 9 to the queue. Now we go back and explore 6 because 6 is the vertex at the head of the queue. So now we look at neighbors of 6. The neighbors of 6 are 5, 7, 8 and 9. So when we remove 6 from the queue, we have nothing to do. We go back and find that there is nothing to be done because all the neighbors of 6 have already been visited. Then we pick up 7. Once again, we find that all the neighbors of 7 have already been visited. Finally, we pick up 9. When we pick up 9, we find that it has neighbors 6, 8 and 10. 10 is new, so 10 gets marked and added to the queue. Finally, we go to 10 and we find it has only one neighbor 9 which is already visited. At this stage, the queue becomes empty and the algorithm terminates. Now in this case, we have marked all the vertices as visited, which indicates that every vertex in this graph is actually reachable from 1. If we had had more vertices, for example, if we had had a component in this graph, there is nothing to stop us from having many components. So we could have had a graph with more vertices 11, 12, 13 and 14. Then this process starting from 1 would have left 11, 12, 13 and 14 marked as unvisited. So here is some more formal code for BFS. So BFS is a function which takes as its argument the vertex from where we want to explore the graph. So as we said, the vertices are called 1 to n. We have this array visited which is initialized to 0, and we have a queue to mark the vertices still to be explored, and this is initialized to empty. So we begin by marking visited of I equal to 1, so vertex I is marked as visited, and we add it to the queue. Now, so long as the queue is not empty, we proceed in the following loop. We extract the head of the queue, the vertex to be explored next, for each of its outgoing edges. If it is something which has not been visited before, we mark it as visited and we add it to the queue. Right? So this is exactly the code for the algorithm we just executed by hand, and it's quite straightforward. There are two data structures, an array to keep track of the visited vertices and a queue to keep track of vertices which need to be explored further. So how do we analyze the complexity of an algorithm such as this? One way to do it is to look at the loop. So remember that when we have an algorithm like this which has a loop, the loop is usually the place where we have to look for it. So we have one iteration where we have a loop of 1 to n where we assign visited j equal to 0. So this is something which takes order n time, right? And now we have a loop here where we keep extracting things from the queue and we do things here, right? So we have to kind of understand how many times this loop is going to execute and how much time this inner loop is going to execute. So each vertex enters the queue exactly once. Right? So if we enter it exactly once, then it says that this outer loop here will take order and time, because assuming that the graph is connected, every vertex will be visited once, and when that vertex is visited, it will enter the queue and it will come out from the head of the queue exactly once. Now, for each vertex, we have to scan all its neighbors. So what we said was that this will be order n if we have an adjacency matrix, because we need to go from the big first entry for j and we have to look at the entire row for j. So this is order n. So therefore, if the graph is connected, first of all, every vertex will get into the queue. So we will do the queue loop exactly n times. And for each j that is extracted, we need to examine all its neighbors. So that will be a scan of size n. And therefore, overall, it's order n squared. Right? These two nested loops of size n. So this is clearly a situation where if we have very few edges, we can improve the complexity by using an adjacency list representation instead of an adjacency matrix representation. So if the number of edges is m, and m is much smaller than n squared, right? So if m is say proportional to n itself, then what we can do is in the list associated with j, we just have to look at the neighbors of j. We don't have to look at all the vertices, all of order n entries in the adjacency matrix. This is called the degree. So the degree of a vertex is the number of vertices connected to it. Right? So if we do this, then what we will find is that inside the iteration of the inner loop, each step of scanning for the neighbors takes time proportional to degree of j. Now, the degree of j, of course, varies from one node to another. So how do we count this correctly? So if you don't count it per loop, but count it across the entire processing of the entire set of vertices, what we will see is that for every edge in the graph of the form I comma j, there will be a time when I is processed and I will see j in its list, right? And there will be a time when j is processed and I will see I in its list. In other words, if I take all the adjacency lists of all the vertices, each edge will be represented twice. An edge ij will appear as an entry j in the list for I and an entry I in the list for j. So while it is not easy to count per iteration, if I count across all iterations, I will explore each edge exactly twice. So 2m is order m. So overall, exploring the neighbors across all n iteration takes times om. So what this means is that the first iteration of marking everything visited takes time on. Then we have an on loop across which we do om steps totally across the n steps. So it is overall n plus n. Okay, so the complexity of breadth first search, if we are using an adjacency list, it drops to on plus m versus order n square for the adjacency matrix. So if we have fewer edges, then it makes a lot of sense to use adjacency list for breadth first search. Now, in graphs, the input size is typically taken to be m and n. In other words, both parameters are somewhat independent of each other, because we could have a set of vertices with very few edges with very many edges. So usually m and n together are taken to be the input size. So order m plus n is actually a linear algorithm. So this is best possible because you have to read the input in order to process it typically. So in linear time, we are able to do breadth first search. So we can do something more in breadth first search. All we have identified is which vertices are connected to the initial vertex 1 or the source vertex in general from where you start breadth first search. So how do we actually identify how to go from the source vertex to a given vertex? Okay? So if we start at I and BFS I sets visited j equal to 1, we know that I and j are connected, but we don't know the path. So what we can easily do is to remember where we marked each vertex from. So when we mark a vertex k as visited, it is marked because it is a neighbor of some already visited neighbor j. So then we can say that k was marked by j. We will use the word parent. So we will say that the parent of k is j. Then by following the parent links, we can reconstruct a path backwards from k to the original source vertex. So this is very easy to do in our code. So we just have to add one line, okay? Or two lines. So initially we say that for every vertex the parent is undefined. So we might set a value like -1 because we know that the names of vertices are 1 to n. Okay? And then when we mark a vertex, since we are exploring an edge jk, the parent of k is going to be j. So we assign the parent of k equal to j. The rest of the code is identical to the earlier breadth search. We have just added this new array parent to keep track of how we mark the vertices so that we can reconstruct the path. So we can go backwards. So because k was marked by j, j would be marked by some other thing and so on. So by just following these links back, we can go back from any k to the start vertex, and therefore we can reconstruct the path. The other thing that we can do in breadth first search is keep track of the level. So remember we said that breadth first search actually explores a graph level by level. It looks at all the vertices which are one step away from the source. Then those vertices are one step away from these one, so they are at level 2, 2 steps away from the source, and so on. So instead of just saying that a vertex is visited, we can ask at what level it was visited. Okay? So initially we say that all the levels are undefined, and then each time we visit a new vertex, it is one level more than the vertex from which it was visited. So eventually we say that if level j is assigned some number p, it must be p steps away from the original vertex. So this can also be easily added to our code along with the parent code. So last time we added this assignment for the parent. Now we also add the assignment for level. So we say initially the level of each vertex is undefined. So it is some nonsensical value like -1, right? Then we say that the level of the start vertex is 0. And now whenever we visit a new vertex, if it is visited, then it must have a level. So if its level is -1, right? So if its level is -1, it means it's not visited. So level -1 means not visited. This is the same as in our earlier thing, same as visited k is 0. And if so, we adjust the level of k to be 1 more than the level of j from which it was visited. And of course, we set the parent as before. So we can see how this works on our earlier example. So as usual, we start with 1 and we mark its level as 0 and it doesn't have a parent. Now when we add 2, 3 and 4, all of them will be at level 1 and all of them will have as parent 1 because they were explored from 1. Then as before, 2 doesn't add anything new to our list. 3 doesn't add anything new to our list. Now 4 will add 5 and 8. So for these two, the level will be 2 and the parent will be 4, indicating that I got to 5 and 8 from 4 in my exploration. Okay? Then from 5, I will get 6 and 7. So these are now at level 3 because 5 was itself at level 2 and therefore 6 and 7 are at level 3 and their parents are 5. From 8, I will go to 9. So 9 is also at level 3 because 8 was already at level 2. So 9 is level 3 and its parent is 8. And finally, we will find that 10 is at level 4 and its parent is 9. So now we can trace back. So we can say that I got from 10, I came from 9. So 9 came from 8. So 8 came from 4. 4 came from 1. So the path is actually 10 to 9 to 8 to 4 to 1. And you can see indeed we have a path from 10 to 9 to 8 to 4 to 1. Right? So this is how you can reconstruct the path information and also the distance information at the same time when you are computing breadth first search. Okay? So breadth first search, if we add this level predicate, it actually gives us the shortest path to each node in terms of the number of edges. Now, in general, we will see that if we don't have a uniform cost, if we have different costs on edges, then the shortest path need not be just the shortest in terms of number of edges. We have to add the cost associated with each path. These are called weighted graphs. But in an unweighted graph, that is a graph which just has simple edges the way we have it now, breadth first search has the added advantage of computing the shortest path in terms of number of edges from the source vertex to every reachable vertex from it. So we have seen how to explore connectivity using breadth first search. So now let's look at the other strategy which is commonly used called depth first search. So in depth first search, instead of exploring all vertices level by level, each time we explore a new vertex, we immediately explore its neighbors. So we start from a vertex I and visit the first neighbor j from I which is not yet explored. Then we suspend the exploration of I and explore j instead. And you keep doing this until you can go no further. So when you get stuck, when there's nothing new to explore, you walk back because you've already left some vertices earlier unexplored because you suspended. So you go back to the nearest suspended vertex that still has an unexplored neighbor, and then you explore the next unexplored neighbor of that vertex. So the way to think about it is that all the vertices which are pending, which are suspended, are now in a stack. So you build up the stack as you go deeper and deeper into the graph. And then whenever you get stuck at a dead end, you walk back up and you process things earlier in the stack. So as before, let's execute this algorithm by hand on our graph and see how it works before we write the pseudocode. So this time we are starting at 4. So the first step is to mark 4 as visited. So we mark 4 as visited and we identify that it has 3 neighbors, 4 neighbors, 1, 3, 5 and 6. So taking them in order, we start with 1. 1 is not visited, so we mark it as visited and we put 4 on the stack, saying we are suspending the execution of 4 because now we are going to explore 1 instead. So now we go to 1 and then we see that 1 has neighbors 2, 3 and 4. Among these the first is 2, so we put 2 on the stack since it was not visited. We mark 2 as visited since it was not visited earlier, and we put 1 on the stack saying now we are suspending 1. So now we look at the neighbors of 2. So the neighbors of 2 are 1 and 3. 1 has already been visited but 3 has not. So we will now mark 3 as visited and suspend 2. Now when we come to 3, it has 2 neighbors, 1 and 2, but both of them are already visited, so there's nothing to be done. So we must go and we must go back to the last vertex which we suspended, namely 2, and explore its neighbors. So we go back to 2. So we had already declared that 1 was not to be done. We have already processed 3, so we have to look at 4, but 4 is also already visited, so we are done with 2. So now we must go back and restore the next vertex on the stack which was left undone. So that was 1. So now we go back to 1, okay, and we find that from 1 we had already visited 2. 3 which we had not visited from 1 was visited via 2, so it's already marked, so this is done. And 4 also is where we came from to 1, so this is done. So 1 is also useless. So now we go back to the first vertex we started with 4 and see if there's something more to be done. So having come back to 4, we find that it has more neighbors. We only explored 1 the first time. Right? So now we continue and we find that there are still 5, 6 and 8. Okay? So we pick up 5 and see it's not visited. So we mark 5 as visited and again suspend 4. So from 5 now we have 4, 6 and 7. So we will now pick up 6 and suspend 5. From 6 we have 7, 5, 7 and 8. So 5 is already done but 7 is not done. So we'll pick up 7 and suspend 6. Now from 7 we find that it has neighbors 5 and 6, both of which are already marked. So 7 is a dead end. So we come back and look at 6 again and see if there's anything new to be done. There is an 8. So now we add 8 and again suspend 6. So now we are at 8 and now we have to ask what can be explored from 8. From 8, 4 is already done. It has 4, 6 and 9. Right? So 4 is already done, 6 is already done, but 9 is new. So we add 9 and suspend 8. Then we move to 9. So from 9 we find it has a new neighbor 10. So we add 10 and then we are done because 10 has nothing to do. So we go back and process 9. 9 has no more new things to say because 9, the other neighbors are 6 and 8 which are already done. So we go back to 8. 8 has nothing more to say, so we go back to 6. 6 has nothing more to say, so we go back to 5. 5 has nothing more to say, so we go back to 4. Now when we started this whole exploration, we did it by 4 to 5. Now we look and see that 4 to 6 is already done. Sorry, not 4 to 6, 4 to 8 is already done. So there's nothing more we can do from 4. and so this exploration is done. Okay. So what we did explicitly with a stack can be done more cleverly if we just implement it recursively. So whenever we visit a new vertex j, we call DFS of j and suspend DFS of the current vertex I. So we don't have to explicitly maintain the stack that we were simulating, because it will be implicitly maintained by the recursive function calls. So DFS is therefore a very simple algorithm to implement. So initially we say for every vertex visited is 0. And remember, like in BFS, breadth first search, we want to keep track of where we came from. So we will say that everything has an undefined parent. Now we initialize, we call DFS of the start vertex. So when we call DFS from a vertex, we mark it as being visited. Right? So the first thing we do is to mark it as being visited. And now for every other vertex that it is connected to, we do the usual thing. We check whether or not that vertex is already visited. If it is not visited, we want to visit it. So how do we visit it? Well, we mark its parent as being I, and then we suspend this DFS and call that DFS. So this is what we were doing explicitly with the stack, but it's much easier to do recursively. So DFS is a very, very simple recursive algorithm. It starts an I, look at every unexplored neighbor, and recursively invoke DFS on that unexplored neighbor. So what is the complexity of depth first search? Well, each vertex is marked and explored exactly once. So we do DFS of j once for every j. So these are order n calls. There are actually exactly n calls if everything is reachable. Now when we call DFS of j for a particular j, we need to examine all the neighbors of j. As we saw before, if we have an adjacency matrix, that means we have to look at the row j and we have to look at every entry in this row. So this takes order n time. So we have order n calls, and each call takes order n times. So overall we have order n squared time. On the other hand, if we use an adjacency list, then when we look at the neighbors of j, we only have to look at the exact vertices it's connected to. And as we said before, if we count across all the calls, each edge will be accounted for twice, once from I to j and once from j to I. So the total number of calls, the total number of steps to scan the neighbors will be order of the number of edges. So the overall time will be linear, m plus n, like breadth first search. So both depth first search and breadth first search are linear in the size of the input if we use adjacency lists. So one big difference between depth first search and breadth first search is that the paths that breadth first search discovers are not shortest paths. Right? So if we have a graph, as we saw before, a triangle like this, where we have 1, 2, and 3, then what depth first search will do is it will find a path from 1 to 3 which goes via 2 if we take the smallest neighbor each time to explore. So when I actually come to the 1, 3 path, I will find that 3 is already visited and I won't mark it. Right? So it appears therefore the depth first search may not be doing something very useful. But actually this recursive way of exploring gives us a lot of information. So many useful features about the graph can actually be extracted by recording the order in which DFS visits vertices. So for this, we augment DFS with something called numbering. So we maintain a counter which we increment every time we enter a vertex when DFS starts on a vertex and when it leaves. So we associate with each vertex in the graph two values. The value of the counter that was there when I did DFS of j for the first time, and the value of the counter when DFS of j exited. So this is how we would do this in our algorithm. So we start by initializing this counter to 0. Right? Now whenever I invoke DFS of I, the first thing I do is assign the current counter value to something called the pre-number of I. Okay? So this is the number of the counter before the DFS of I actually started, and then I increment the counter. Likewise, when I'm about to exit, I mark post of I equal to count, and again I increment the counter. So this says that so in between, remember, a lot of recursive call happens. So this count at this point is not going to be the same as the count which I incremented. There's going to be a lot of stuff happening in between. And it turns out the order in which these two numbers, pre-I and post-I, fill across vertices, I can actually recover a lot of information. Okay, so let's look at this example that we did before. So supposing as before we start at 4. Okay. So we'll say that its pre-number is say 0 because we start there, and then we increment and then we go to 1. So when we enter 1, the count is 1. So its pre-number is 1. And then we go to 2, its pre-number is 2. Then we go to 3, and its pre-number is 3. And then we immediately leave 3 because we don't have any new neighbors to exceed. So its post number is now 4. So I'm writing the pre-number above and the post number below. Then I come back to 2 and I find that there's nothing more to be done at 2. So I exit from 2. So its post number becomes 5. So notice that here I entered at step 2 and I left at step 5. And in between I did 3 and 4 somewhere else. Likewise, I come back to 1 and I find that it has nothing new to say. So now I leave 1 at step 6. Then I come back to 4, but I'm not finished with 4 because I can do 5. So I enter 5 at step 7. From 5, I enter 6 at step 8. From 6, I enter 7 at step 9. Now from 7, I can't go anywhere else. So I leave 7 and I come back to 6. Okay. Then from 6, I look further and I find 8. So I enter 8. I was at 10 at that point. So now I enter 8 at step 11. From 8, I enter 9 at step 12. From 9, I enter step 10 at step 13. Then I leave 10. I leave 9 at 15. I leave 8 at 16. I leave 7 at 17. I leave 5 at 18. And I come back to 4 and I finally finish at 19. Right? So I have with each node now these two values, a pre-value and a post-value. Right? So I have a pre-value and a post-value. And it turns out that this pre and post-value can be very helpful. Okay? So we can find out things like whether a graph has a cycle. So this is a cycle, right? So whether a graph has a loop like this. Or we can find out whether there are vertices like this. So this is a special vertex because if I remove this 4 from the graph, and the graph which was earlier connected, everything could reach everything, is no longer connected because there is no way now to get from 1, 2, 3 to this lower segment. Okay? So are there such cut vertices? So these are various things that can be computed using these DFS numbers. We will see some of these computations in later lectures, but this makes DFS actually a much more useful exploration strategy than breadth first search. So BFS does give us shortest paths, but on the other hand, DFS gives us a wealth of information which is implicitly hidden in this recursive order of exploration, which we can exploit to find out various structural properties of the graph for free. More or less, while we are doing DFS, we can find out many interesting things about the graph. So we have seen how to use breadth first and depth first search to explore whether there is a path from a source to a target vertex. But one can do a lot more with these two procedures. So recall that a graph is a set of vertices and a set of edges which are connections between the vertices, and these may be directed or undirected. Now when we do breadth first search, we do a level by level exploration starting at one vertex. When we do depth first search, each time we go to a new vertex, we switch the exploration to that vertex, and whenever we reach a dead end, we back up. And one of the features of depth first search is that we can keep track of the order in which we enter and exit vertices in this recursive procedure. So now let's see how we can use BFS and DFS to find out more about the structure of the underlying graph. So one fundamental property of an undirected graph is whether or not it is connected. Can we go from every vertex to every other vertex? So you can see in these two pictures that the graph on the left is connected because you can go from every vertex to every other vertex. On the other hand, on the right hand side, some vertices cannot be reached from other vertices. For example, one cannot go from 2 to 7 or from 6 to anywhere else. Now when we have an undirected graph which is disconnected, we are also interested in finding out what the connected components are. So we want to group together those vertices which are connected to each other into one unit and find out which of these units are there and how many such units are there and which vertices belong to the same unit. So our first target is to use BFS or DFS to identify connected components. So this is quite easy to do. We start with the node labeled 1 or any other node. Now we run BFS or DFS from this node. And in this process, we will mark a number of nodes as visited. At this point, if there are any vertices which are not visited by BFS or DFS starting from the first node, this means that they do not belong to the same connected component. So it is easy to show that what is marked visited is equal to the connected component. So the connected component containing the start node. So now we go back and we look at the first node in the list which is not marked visited. And we restart BFS or DFS from that node. So we will get a new connected component consisting of those vertices which are reachable from the first node which was marked unconnected. Now if there are still nodes which are unvisited, we restart from one of those and go on. So what we can do now is we can label each DFS with a different number. So at the end, we can associate with each vertex the number of the component in which it was discovered. So let's look at an example of this. So supposing we have this graph, right? We begin by having an extra variable in our BFS, for example, or even DFS called comp to number the components. So we initially set comp to 1 and maybe we start our DFS or BFS from node 1. So in this process, we will visit 1, 2, 5, 9 and 10, and for all of these, we will set component of j equal to comp. Now at this point, we will realize that not all nodes have been visited. Only 5 out of the 12 nodes have been visited. So we go to the smallest node which is not visited, namely 3, and restart. But before we restart, we update comp to 2. Now we start a BFS or a DFS at node 3 and visit everything that we can reach. And in this process, we will identify these 6 nodes as being in component 2. At this point, node 6 is still not marked visited. So we restart a third round of BFS or DFS with comp set to 3 and identify a third component. Now there are no more unvisited nodes, so we can stop. And as a result of this repeated application of BFS and DFS, we have identified all the components and also clustered them so that all nodes in the same component are associated with the same component number. Another interesting structural property of a graph is whether or not it has cycles. So an acyclic graph is a graph such as the left in which you cannot start at any node and follow a sequence of edges and come back to the node. On the right, we see a graph with cycles. So for instance, 5, 9 and 10 form cycles. There are also other cycles. There are several cycles. For example, 3, 4, 7, 8 as a whole form a cycle, but there are also smaller cycles within it like 3, 4, 8 and 3, 7, 8 and 7, 8, 11 is also a cycle and so on. So one of the things we can do when we execute BFS is to keep track of those edges which are actually used to mark vertices as visited. Now if we have an acyclic graph such as the one on the left, you can check that every node that is in the graph will actually be used as part of the BFS search. On the other hand, if you run BFS on a graph which has cycles, then you will find that some edges are not used because when you try to explore those edges, you find the target vertex is already visited. For instance, since 10 is already visited as a neighbor of 5, when we start exploring 9, we do not use the edge 9, 10. Likewise, we don't use the edge 4, 8 because it is already visited as a set of neighbors of 3. Remember, in breadth first search, we will go to 3 and explore all its one-step neighbors. So we will mark directly 4, 8 and 7 as visited. So when we come to 4, we don't need to use the edge 4, 8. When we come to 7, we don't need to use the 7, 8 and so on. So there are these edges which are left out. Now it's easy to see that if we have a graph with n vertices and it is connected and it doesn't have cycles, then it will have exactly n minus 1 edges. This kind of a graph is called a tree. So there are many definitions of trees, but a tree is basically a connected acyclic graph. Connected means you can go from everywhere to everywhere. Acyclic means there are no loops. And any connected acyclic graph on n vertices will have exactly n minus 1 edges. So in any graph, if we explore BFS, the edges that BFS actually uses will form a tree, and this is called a BFS tree. Now what happens about the remaining edges? Well, these are called non-tree edges, and what you can check very easily is that any non-tree edge will combine with the tree edges already there to form a cycle. In other words, when we run BFS, if we find that there are some vertices or some edges rather which are not used, in other words there are any non-tree edges, then this graph will definitely have a cycle. So having a cycle is equivalent to finding a non-tree edge while doing BFS. What is a non-tree edge? It's just an edge where we come to explore I comma j and find that j has already been marked visited, so we don't go to I don't use I comma j in our BFS. So let's do the same thing with DFS and let's compute the pre and post numbers so that we get some practice at this. So we start our DFS at vertex 1 and we mark its counter as 0. So we enter vertex 1 at step 0. So this is the pre number of vertex 0. The first neighbor we explore from 1 is 2. So it has pre number 1. But 2 has no further successors, so we exit from 2. So it has post number 2. So remember, every time we enter, we increment a counter. Every time we exit, we increment a counter. So we enter and exit vertex 2 in one step. Come back to 1 and explore its next neighbor, which is 5, which we enter at time 3. Then we move to vertex 9 at time 4. Then from 9 we go to 10 at time 5. Now 10 has no further neighbors to explore. So we exit 10 at time 6. 9 has no further neighbors. So we exit 9 at time 7. Come back to 5. Again 5 has no further neighbors. So we exit 5. And then finally we exit 1. So at step 9 we have completed processing 1. Now we move to the first vertex which is not marked, namely 3. And we restart a new DFS from there. So we enter 3 at time 10. From 3 we move to 4 at time 11. From 4 we move to 8 at time 12. From 8 we move to its smallest neighbor unvisited, which is 7 at time 13. From 7 we go to 11 at time 14. Now 11 has no new neighbors to explore because both 7 and 8 have been seen. So we exit from 11. 7 has no more neighbors to explore, so we exit from 7 and we exit from 8. No, we don't exit from 8. Sorry, from 8 we still have to explore 12. So we enter 12 at step 17. Then we exit from 12 and now 8 is finished. So we exit from 8. Now we come back to 4. 4 obviously has no other vertices, so we come back to 3. And finally we exit from 3 at time 21. At this point 6 is still not marked. So we start a new DFS from 6. So we enter 6 at time 22, but 6 has no neighbors, so we exit 6 at time 23. So this, like BFS, generates a collection of trees. So when we do DFS on a disconnected graph, each connected component will generate a tree. Now if we look at the edges which we did not explore, these will again be edges which are outside the tree. So we can draw them in a different color. So we have the edge between 5 and 10 which we did not explore because we explored 10 directly from 9 and so on. So once again, just like in BFS, once we have finished DFS, if there are non-tree edges, then we have a cycle. Right? So both BFS and DFS on an undirected graph can reveal a cycle through the presence of a non-tree edge. So the situation with directed graphs is a little more complicated. So let's see what happens when we have cycles in directed graphs. So in a directed graph, we need to follow the edge arrows along the edges. So for example, 1, 3, 4, 1 is a cycle because we can go around without changing direction. Whereas 1, 6, 2, 1 is not a cycle because on the way back, I have to switch directions from 2 to 1, which I cannot do. So let's do a DFS and see what this can tell us about cycles in this graph. So we begin with vertex 1 as usual. So 1 has pre-number 0. Its smallest neighbor is 2. Okay. Then the smallest neighbor of 2 is 5. The smallest neighbor of 5 is 6. The smallest neighbor of 6 is 7. Now from 7, there are no outgoing edges. So we backtrack to 6. From 6, the only node that we can go to is 2, which we have seen before. So we leave 6. Now we come to 5. 5 still has an outgoing edge which is 8. So we come to 8. Now from 8 we can't do anything, so we return from 8 back to 5. Now 5 has nothing left to explore, so we leave 5. Likewise we leave 2. Finally we come back to 1. Now at 1 we have explored this left path, so now we don't look there, we look in the other direction, go to 3. So we explore 3. Now 3 will explore 4. But 4 cannot go to 8 or 1 because 1 has already been seen and so is 8. So 4 will exit. So 3 will exit and then 1 will exit. So this happens to be a single connected graph, but it has cycles. Right? So now we can first look at these edges. The edges that we have drawn are tree edges as before. Now if we look at the edges that have not been part of the graph, they fall into three groups. So the first type of edge which is not a part of the tree is what we call a forward edge. So a forward edge is an edge which goes from a node to a node below it in the tree. So we have a node from 1 to 6, for example. So this edge, okay, is a tree edge. Is not a tree edge, but it's a forward edge because 1 was above 6 in the graph. Likewise, the node from 5 to 7, right? Because we actually explored this graph as 5, 6, 7. So 5 to 7 was not used. So these are forward edges. The other category of edges which are there in the graph, which are not in the tree, are backward edges. They go up the tree. So from 6, there is this edge back to 2, which we did not use because 2 had already been explored. Likewise, from 4 back to 1, there was this edge which we did not explore because it was already there. There is another category of edges which are not there in the tree but which are there in the graph. And these are edges such as from 6 back to 2. So this was an edge from a later vertex to an earlier vertex, or from 4 back to 1. So these are what are called back edges. So a back edge is an edge in the graph which in the DFS tree goes from a lower vertex to a higher vertex. And finally, there are some edges which are neither going forward nor backwards but sideways. So these are edges like 8 to 5, okay, 8 to 7, and from 4 to 8. So these cross, so 4 is not below 8 nor is 8 below 4, 7 is not below 8 because they are both below 5 and so on. So these we call cross edges. Now it's easy to argue that a cross edge will only go from right to left. In other words, it will only go from a higher number to a lower number. Because if we wanted to draw an edge like this, for instance, then this would mean that there was an edge from 2 to 4, so we would explore 4 through 2 rather than wait and go back to 1 and explore it. Right? So we cannot have cross edges which go from lower numbers to higher numbers. It must go from higher numbers to lower numbers. So now we have not one but three types of non-tree edges. Unlike the directed case, when we had a clear distinction between tree edges and non-tree edges, here we have three types of non-tree edges. Now which ones of these correspond to cycles? So if I look at this 1, 3 edge, okay, so this 1, 3 edge, this 1, 6 edge, okay, so this 1, 6 edge doesn't actually create a cycle because we already saw that this is not a cycle. Okay, so in order for it to complete a cycle, it must be the case that there is a path including this edge which forms a directed cycle. Now it's easy to see that the only situation where this will actually happen is there is a back edge. Because if there is a back edge, we know that there is a path coming from 2 down to 6, and then by following the back edge, this forms a directed cycle. Okay, likewise, we know that there is a path coming from 1 down to 4, and by following this back edge, we follow a directed cycle. On the other hand, if we look at the other types of edges, for instance, then we have this path here, but this is parallel to the other path here, right? So together, these are both two different ways of going from 1 to 6, but they are not a cycle. Okay? And the same way, we can see that if we have a cross edge like this, then we have some path coming from here and some path going from there. But again, they are just two different ways of reaching 7 from 5, and they are not really a cycle. Okay? So it turns out by a little analysis that only back edges form cycles, and this is actually something that you can prove. We will not prove it formally, but it's argued the way we did just now, that a directed graph has a cycle if and only DFS reveals a back edge. Now, it turns out that these pre and post numberings are very useful to help us classify the types of edges that are there in the graph. So for both tree and forward edges, so you will notice that if you go back to this numbering, okay, that these things form an interval, that you can think of this as from 0 to 15. From step 0 to 15, I was exploring 1. From step 11 to 14, I was exploring 3. From step 2 to 9, I was exploring 5 and so on. So if you look at the pre and the post number, it says I started exploring the number at the pre and I finished exploring at post, and everything else that was below happened in between. Right? So for a forward edge, the interval above will be bigger than the interval below, because I went below during this period and I came back before it ended. So for instance, the forward edge from 0, 15 to 3 comma 6. So the interval 3 6 is inside 0 50. Okay, this is also true for tree edges, because in the tree edge also, if I'm going forwards, I enter the lower node after I've entered this, so its starting point will be later and its ending point will be earlier. Okay? So for both tree edges and forward edges, if I'm going from U to V, then the interval with the start node U will contain the other one. So this will be sitting inside this. The pre-V post V will be sitting inside pre-U post U. Right? So I'll have this picture. So this is the interval for U and this is the interval for V. Conversely, it's exactly the opposite for backward edges. I start from a smaller interval and I go to a bigger interval. So the smaller interval will be the starting point of the edge and the bigger interval will be the ending point. So if I look at an edge in my DFS tree and if I look at the pre and post numbers associated with the endpoints, I can determine whether it's a forward or tree edge or a backward edge. And finally, it will turn out that for cross edges, the intervals are disjoint. So we can see here that we have finished processing for vertex 7 before we get to 8. So there is no intersection between the intervals 7, 8 and 4, 5. Likewise, we have finished processing 8 before we went to 4. That's why it's a cross edge. They are on different branches of the tree. So there is no intersection between 7, 8 and 12, 13. Right? So therefore, a directed graph has a cycle if and only if DFS reveals a back edge. And we can classify edges as being forward edges, backward edges or cross edges by just looking at the pre and post numbering of the endpoints of the edge. Now, it's important to identify cycles because if we don't have cycles, we have a very nice class of graphs called directed acyclic graphs. These are useful for modeling dependencies. For instance, if we want to list out a bunch of courses which are being offered and they have prerequisites, then a natural way to model this is using a directed graph where the edges represent prerequisites. For instance, if they have an edge from algebra to calculus, it indicates that algebra is a prerequisite for calculus. We will not have cycles because we cannot have two courses which are prerequisites for each other, otherwise we will not be able to take either course. So we will look at directed acyclic graphs or DAGs soon in a later lecture. What about connectivity in directed graphs? So connectivity in a directed graph is not just a question of having these edges between the graphs, but having them in the right direction. So we say that two nodes are strongly connected if I can go from I to j by a path and I can come back from I to j to I by a path, right? So it's not enough to just have edges in some haphazard direction. I must be able to go from I to j and come back from j to I, in which case I say they're strongly connected. So it turns out that a directed graph can always be decomposed into what are called strongly connected components. A strongly connected component has a property that every pair of nodes in that component is strongly connected. From every node in the component, you can go to every other node in the component and come back. So for instance, if we look at this graph, then the strongly connected components, one is this cycle 1, 3, 4. We can go from 1 to 3 to 4 and come back. So from any node in this cycle, we can come back to any other node. Likewise, 2, 5 and 6 forms a strongly connected component. 7 on its own is a strongly connected component because we can't go anywhere. And 8 also is a strongly connected component because if we leave 8, we can't come back to 8, the way this graph is structured. Okay, so this graph has 4 strongly connected components. Now it turns out that DFS numbering using pre and post numbers can be used to compute strongly connected components. A very elegant algorithm is given in the book by Dijkstra, Papadimitriou and Vazirani, and if you're interested, you can look it up in that book. So we have seen some concrete examples of what you can compute. There are many other properties that you can compute using BFS and DFS. For instance, there are these things called articulation points. If your graph looks like this, where I have some vertex which is a crucial vertex, if I remove this vertex, this graph falls apart into disconnected components. I can identify such vertices using BFS and DFS, in particular using DFS. Similarly, if I have a situation where I have an edge like this, where if I remove this edge, then the graph gets disconnected, then I can again identify such an edge using DFS. Now these are important because if these graphs represent some kind of communication network or some road network, then these are bottlenecks. These are critical points. If this is an intersection and if there's an accident, no traffic can go from any part on the left to any part on the right. Or if this is a network wire, if this cable gets cut, then the network will get cut, disconnected into two components. So these kind of properties can also be computed during BFS and DFS. So it is important to realize therefore that BFS and DFS is not just for connecting to finding out whether vertex S can reach vertex T. You can get a wealth of information, and these are linear time algorithms, and these are all operations which can be performed during BFS and DFS. So very efficiently you can compute various properties of the graph and use these to exploit these to design more efficient procedures or to identify other things that need to be done. So we now turn our attention to a very interesting and important class of graphs called directed acyclic graphs, or DAGs. So to motivate this class of graphs, let's look at a problem where we have a bunch of tasks to perform with some constraints. Suppose we are going on a foreign trip. Then of course we need a passport. We need to buy a ticket. We require a visa probably. We want to buy some travel insurance. We probably need some foreign exchange as well. And perhaps we want to buy some gifts for our hosts. Now, these tasks are dependent on each other in certain ways. Without a passport, you cannot buy a ticket, nor can you buy any travel insurance. For the visa, you need both the ticket and the insurance to be available. And without a visa, the bank will not give you foreign exchange. And finally, you would not like to buy gifts for your hosts unless the trip is confirmed. So unless you have all these things, including the visa in hand, you don't want to invest in the gift. So our goal is that given these constraints, in what sequence should we perform these 6 operations? Getting a passport, buying a ticket, getting insurance, getting a visa, buying foreign exchange, and buying gifts for our hosts. What sequence should we do it so that whenever we want to approach a task, the constraints that are required for that task are satisfied. So as you would expect, we will model this using a graph. In this graph, the vertices will be the tasks, and then we will have an edge pointing from T1 to T2 if T1 must come before T2. In other words, T2 depends on T1. You cannot do T2 unless T1 has been completed. So as an example, getting a passport must come before buying a ticket. So if T1 is getting a passport, T2 could be getting a ticket. Similarly, you must have a visa before you buy foreign exchange. Right? So there will be an edge from getting a visa to buying foreign exchange. So if we look at the constraints that we wrote, this is the graph that we had. Right? So we had a constraint which said you need a passport to buy a ticket, you need a passport to buy insurance, you need both a ticket and insurance to get a visa. So there are 2 constraints pointing to visa. Then you need a visa to buy foreign exchange. And finally you said we will buy a gift only if the trip is confirmed. And at some point at this stage, when all these operations are done, we can assume the trip is confirmed because nothing is blocking us getting on the plane. Right? So this is a graph that we have, and now our goal is to sequence these 6 operations in such a way that whenever we want to perform a task, whatever it depends on has already been done. So we can see that you need a passport to do anything, so we always need to start with getting a passport. Now there is no dependency between buying a ticket and buying insurance as per the constraints we have so far. So after a passport, you can either buy a ticket first and then buy insurance, or you can buy insurance first and then buy a ticket. So there is a different ordering possible which does not violate the constraints. On the other hand, for a visa, you need both. Right? So visa must come after both ticket and insurance. But again, having done the visa, then there is no constraint between buying the foreign exchange and buying gifts. So you could do the foreign exchange before the gift or the gift before the foreign exchange. So there are, in this particular example, there are 2 possible ways of reordering the ticket and the insurance, and there are 2 possible ways of reordering the gifts and the foreign exchange. So overall, there are 4 different sequences which are compatible with these constraints. So this class of graph is an important class, and it has 2 important features. One is, of course, it is directed because these dependencies are from one task to another task. It's not a symmetric dependency, and there are no cycles. So if you had a cycle, it would mean that a group of tasks depend on each other. So there's no way to start because each task depends on something else in the cycle. So you have to break the cycle somewhere in order to get started, but you can't break it anywhere because each task depends on something else in the cycle. Right? So this graph will have directions on the edges, and there cannot be any cycles in this graph. So we call such a graph a directed acyclic graph. Right? So a directed acyclic graph is just a directed graph in which there is no directed path from any vertex back to itself. So if I start at any vertex v, it should not be the case that I can follow a sequence of directed edges in the same direction and somehow come back to v. So this should not be there. Right? So there should not be any cycle. We abbreviate the name directed acyclic graph as DAG. So very often, for simplicity, we will call these graphs DAGs. So the problem that we had addressed in our example is that we are given a set of tasks and we want to write them out in a sequence which respects the constraints. The constraints are nothing but the edges. So in general, we are given a set of vertices. These are our tasks abstractly, 1 to n. And we want to write out 1 to n in such a way that the constraints are respected. What this means is that we will write out a sequence of numbers which is a permutation of 1 to n in such a way that whenever there is a constraint of the form jk, that is, there's an edge jk, then in the enumeration that we have performed, j must come before k. Right? So it cannot be that we have to do j before k according to our constraint, but in the sequence that we produce, k happens before j. Right? So the order of vertices in the final sequence must respect the constraints given by the DAG. So for various reasons, this is known as topologically sorting the DAG. So the first observation is that if the directed graph had a cycle, then you will not be able to topologically order it. Because if it had a cycle, then for instance, supposing j and k are vertices on the cycle, then you will have a path from j to k and a path from k to j. Now it is easy to see that the topological ordering constraint extends to paths. That is, if I have j before k as an edge, I know that j must appear before k in the final sequence. Also, if there's a path from j to k, then there is a sequence of dependencies from j to k, so j must appear before k. Now if I have a cycle, it says that j must come before k and k must come before j, so there is no way to break this dichotomy. So we will end up with a situation where we cannot order this set of tasks to respect the constraints. So if the graph has cycles, then it is clear that there is no topological ordering possible. So what we claim, however, is that for DAGs, that is, if there is no cycle, if the graph is actually acyclic, then we can always order it topologically. So the strategy is to order the vertices as follows. You first list all the vertices which have no dependencies. In our earlier example, the vertex which had no dependencies was getting a passport. We did not need to do anything before getting a passport, so we can do that first. Now once we have knocked off that dependency, you see any vertex for which all its dependencies are now satisfied, and then we can enumerate that. Okay? So we can systematically list out vertices with no incoming edges, then vertices all of whose incoming edges have already been accounted for in our enumeration, and so on. So to formalize this notion, we introduce some terminology. So recall that for an undirected graph, we use the term degree of V to refer to the number of vertices connected to V. So if V was connected by an edge to 4 vertices, then we would say that the degree of V is 4. Now since we have a directed graph, we have directions on these edges. We have some edges which are coming in and some edges which are going out. So we separate out the degree into the in degree and the out degree. So the in degree is the number of edges pointing into V, directed into V. The out degree of V is the number of edges pointing out of V. So our first claim is that every DAG has at least one vertex with in degree 0. In terms of our example, a vertex with in degree 0 is something which has no dependencies. Nothing, it doesn't depend on anything. There's nothing pointing into it. Now, how do we prove this? Well, supposing we start with any vertex V such that it has in degree greater than 0. Since it has something pointing into it, then it must have some edge coming into it. So let us call that V2. Now supposing this does not have in degree 0, then it must also have something pointing into it. So then I get a third vertex. So in this way, if I keep finding that the vertices I am encountering have in degree greater than 0, eventually I must enumerate all the vertices in my graph. Now if there is still not the case that the nth vertex, if there are n vertices, the nth vertex still doesn't have in degree 0, then it must have an incoming edge, but that cannot be from a new vertex, so it must point from one of the existing vertices which I've already seen before. Right? So therefore, if I have a continuous sequence of vertices, all of which are pointing into the previous one with in degree not equal to 0, then I will end up with a cycle. But this is a contradiction because we have an acyclic graph. Right? So in any directed acyclic graph, there must be at least one vertex with in degree 0 which corresponds to a task with no dependencies from where we can start our enumeration of the tasks. So this is a more elaborate version of the algorithm that we described earlier. So we pick a vertex with in degree 0. Right? Recall that such a vertex has no dependencies. Now we enumerate it because it now has it's available for enumeration, and then we delete it from the graph. So when we delete a vertex with in degree 0 from a graph, so supposing we have a DAG like this, okay, so supposing we pick this one and we delete it, then clearly what remains is a DAG because it is still directed and we have not introduced any cycle. So it was already acyclic, and by deleting an edge we can't introduce a cycle, so clearly it's a DAG. So we can apply the same criterion. This new DAG must also have at least one degree with a vertex with in degree 0, so we can enumerate that and keep going. Right? So we keep enumerating vertices with in degree 0 until the DAG becomes empty. Each vertex we enumerate, we will delete from the DAG. So let us apply this strategy to this DAG. So we first begin by labeling every vertex by its in degree. So in red we have indicated the in degree of every vertex. So for instance 1 and 2 have no incoming edges, so they have in degree 0. Vertex 3 has 2 edges coming in, so it has in degree 2. Vertex 8 has 4 edges coming in, so it has in degree 4, and so on. Now we have to pick a vertex of in degree 0, enumerate it and eliminate it. So we have a choice between 1 and 2. So let's suppose we start with 1. So we start with 1, we eliminate it, and now when we eliminate it, we also eliminate the edges going out of it. So the edges coming into 3, 4 and 5 will reduce by 1 because the vertex 1 is gone. So if the edges coming into them reduce by 1, their in degree is also reduced by 1. So what happens when we eliminate 1 is that we enumerate it and we reduce the in degrees of 3, 4 and 5 from 2, 1, 1 to 1, 0, 0. So recall that before that the in degrees were 2, 1 and 1. Now these edges which are coming into them have been deleted, right? So when we delete this, we also delete the incoming edges. So now we have 1, 0, 0. Now we have three choices, 2, the original one which are index 0, and we have now two new vertices, 4 and 5, which correspond to tasks, if you want to call them, whose prerequisites have been completed. So task 1 was a prerequisite, only prerequisite for 4. Task 1 was the only prerequisite for 5. It has been completed, so 4 and 5 are now available. So we can choose any of 2, 4 and 5, it doesn't matter. So let's suppose we choose 4, then again these two edges will go. So this will reduce to 1 and this will reduce to 3. So we can do that. We eliminate 4 and reduce the in degree of 6 from 2 to 1, the in degree of 8 from 4 to 3. Now perhaps we decide to eliminate task 2. So when you do task 2, then the in degree of 3 reduces and the in degree of 8 again reduces. So notice that 8 still has two pending requirements, namely 5 and 7. Okay, so it cannot be done yet, but 3 and 5 are available. So perhaps I do 5. So now 8 still has 1, and now I have no choice. The only task with in degree 0 is 3. So then I do 3. So now I can see that this is actually the way it is drawn is just a sequence. I must do 3 before 6, 6 before 7, 7 before 8. So I have no choice at this point. I must enumerate it as 3, then 6, then 7, and then finally 8. At this point my graph is empty and I have obtained a sequence of vertices which is a valid topological ordering, because every pair of vertices which occur as an edge in my original graph is ordered so that the source of the edge appears before the target of the edge. So let's look at some pseudocode for the algorithm which we just executed by hand. So in this particular algorithm, we first start by computing the in degree. So in order to compute the in degree, we need to find out how many, for a vertex I, we need to find out how many j satisfy the property that aj I is equal to 1, because this corresponds to an edge from j to I. So in an adjacency matrix, this corresponds to looking at the column containing I, because in the column containing I, we will have entries of the form a1i, a2i and so on, right? So we will have these entries and we want to scan all of these and then add up all the ones. So we start by setting in degree equal to 1, in degree I equal to 0, and then for every row j we add aj, so it's either 0 or 1, and so we therefore collect all the incoming edges which point into I as the in degree of I. Now we start enumerating. So we know this is a DAG, so we know there is at least one j with in degree 0 at every point. So we choose any such j. Okay, choose a j which has in degree 0, enumerate it. Now when we enumerate, we want to eliminate it from the graph. Rather than going and actually modifying the graph itself, we will just work with in degree as a kind of approximate version of the modified graph. So we first set the in degree to -1 for this particular vertex. So -1 means it cannot be in the graph because you cannot have -1 edges pointing. You can have at least 0 edges or more. Right? So this effectively means that j is not going to be considered henceforth. And now for every outgoing edge from j, so wherever we have j pointing to k, we want to decrement this because we're going to eliminate this edge. By eliminating j, we eliminate this edge. So for every k from 1 to n, we scan all the outgoing neighbors of j, and if jk is an edge, ajk is 1, we reduce the in degree of k by 1. So what is the complexity of the algorithm? It's fairly easy to see that for this adjacency matrix representation, it's n square. As we saw, initializing the in degree itself takes time n square, right? Because we have one outer loop from 1 to n, and then for each outer loop, we have an inner loop from 1 to n. So this is an n square loop. And then when we enumerate the vertices, again, we have an outer loop which will enumerate every vertex once, okay? And then for the inner loop, we have to enumerate, check all its neighbors and decrement, right? So we have two n square loops, and therefore this whole thing takes order n square. Now we can, as we saw with BFS and DFS, right? If we use an adjacency list, we can be a little more clever and we can bring down this time to linear. From n square, we can bring it down to order n plus n. So how do we do this? Well, we have these lists, right? So we have lists, say 1, 2, and for each of these, we have a list of its neighbors. So if we go through this, as we said, each edge in this, now this is a directed graph, so each edge is represented only once. If there's an edge from I to j, it will appear as an entry j in the list for I, right? So if we scan these lists, every time we see a j, we know there's an edge pointing into j, and we will increment. So we start off by setting all the in degrees to 0, we scan all the lists, and every time we see an entry in a list, we increment its in degree. So in one scan of the list, that is in time order m, we can find the in degrees. Now we have the list of in degrees, so we can put all the in degree vertices into a queue. This makes it easy to find which vertex to enumerate next. Right? So at the end of this scan, we have done an order m scan to find all the in degrees. Now in an order n scan, we can put all the 0 degree vertices into a queue. Now we can do the rest pretty much as we did before. We enumerate the first vertex in the queue, and then we go to its list, which is now explicitly available to us in this adjacency list, its outgoing neighbors, decrement its in degree, and if any of those in degrees become 0, we can add it to the queue. So we know it is to be processed now. Right? So this becomes, overall it takes order m time to scan the list, it takes order n time to start the queue off, and then this is a loop of order n where across all the updates, we will overall update the in degrees order m times. So this is order n plus n. So here is the corresponding pseudocode, right? So the first step is to initialize the in degree to 0 for every vertex in our graph. Then we go through all the edges, right? So we do this by looking at each adjacency list. For each vertex, we look at each neighbor ij in the adjacency list, and for each of these, we increment the in degree of j, because we are looking at edges pointing into j, not pointing out of I. So this pointing into j will come in different lists, but as and when we encounter them, for each of them, we will account for them and add 1 to it. Now we go through the list one more time, a list of vertices, and every time we see an in degree 1, 0, we add I to the queue. And now we do this loop till the queue becomes empty. We know there's at least 1 at every point. Remember, as long as the graph, a DAG is not empty, we know there's at least 1 in degree I vertex with in degree I is 0. So it must be in the queue, because we added them all originally to the queue, and each one we generate, we will add to the queue. So as long as the queue is not empty, we take off the first element of the queue. Then we look at its adjacency list, decrement the in degrees of all those vertices, and if any of them happens to now become in degree 0, we add it to the queue. Right? So this becomes now a linear implementation of topological sort using adjacency lists and a queue to process the elements, because the problem with the reason why we need this queue is that otherwise if we have to scan all the vertices every time to determine whether a vertex has become in degree 0, then that becomes an order n scan within this, so it becomes order n square again. So we need the queue to make sure that we don't spend time trying to identify the next vertex to enumerate. We don't have to go through all the vertices and check the in degrees. When we see the in degree 0, we put it into the queue, so automatically it will come out without having to do any further check. So it gets absorbed in this order m work that we are doing here. So let's continue to look at DAGs, and in this section we'll look at a different problem called identifying the longest path in a DAG. So recall that a directed acyclic graph is just a directed graph in which there is no directed path from any vertex back to itself. So it is directed and it is acyclic. Any directed acyclic graph can be topologically ordered. If we think of the vertices as being 1 to n, we can write out 1 to n in a sequence in such a way that for every pair jk which is an edge, if jk is an edge in my graph, then j will appear before k in the sequence. So if we think of these as tasks with dependencies, it means that I can do the task in such a way that before I do k, I would have finished its dependent task j. Right? So this is called a topological sorting. So let's look at a different question about DAGs. So supposing we have this DAG and we imagine that the vertices represent courses and the edges are prerequisites. Now these are courses that we have to do to maybe complete a degree. Every course requires a semester, but we can do more than one course in a semester. So the question is, what is the minimum number of semesters that I need to complete this program consisting of these 8 courses with these prerequisites? So clearly I can start by doing courses 1 and 2 in this first semester because they have no prerequisites, so they can be done immediately. Now having done 1 and 2, I can do 3 because 3 only depends on 1 and 2. Similarly, I can do 4 and 5 because they depend only on 1. Now 8 depends on 1 and 2. I need the material, or at least it depends on 2. I need to have done 2 to do 8, but I still cannot do 8 because it also requires 5, 4 and 7. So at this point, the only courses which are available are 3, 4 and 5. So in my second semester, I can do 3, 4 and 5. Now the only course for which all prerequisites are satisfied is 6, because 7 requires 6 which has not been done and 8 requires 7 which has not been done. So in the third semester I'm stuck with doing only one course, namely 6. In the fourth semester I can do 7, and finally after 5 semesters I can complete these requirements. So in general we can ask this question, okay, if I think of these as DAG as representing courses, what is the minimum number of semesters? Now this problem corresponds to asking for the longest path in the DAG. What we are saying is that it takes 5 semesters to complete 8 because there is a chain of dependencies where 8 depends on 7, 7 depends on 6, 6 depends on say 3 or 4, it doesn't matter which one we choose, and 3 depends on 1, and this chain forces us to spend 4 semesters, because there is a chain of length 4 semesters before I can do 8. Notice that it is not the shortest chain, because there are shorter chains. For example, 8 to 2 takes us back to a vertex which has in degree 0. But this doesn't help us because after 2 I cannot do 8. So I must wait for everything that has to happen before 8 in order to get the job done. So unlike other problems where we might be looking at shortest paths, here we're actually interested in the longest path. So we can set up this problem as follows. So we can say that for any vertex which has in degree 0, the longest path to that vertex is of length 0 because I can do it immediately. And on the other hand, if I have a vertex whose degree is not 0, then it has some incoming edges. So I have a vertex k, right? So I must wait for all of these to finish and then do it. So if I take all of these, I have to take, among all of these, I have to take the maximum length because that will be the last thing to finish. And after that, I have to do plus 1 to account for k. So if the degree is not 0, then the longest path to k has length 1 plus the maximum of the longest path to all its incoming neighbors. So therefore, in order to compute the longest path to k, I need to compute the longest path to all its incoming neighbors. Now, if we have arranged the vertices in topological order and we compute the longest path in that sequence, then when we get to k, every incoming neighbor j will be on its left. Hence, we would have already computed its longest path. So we would be able to take the maximum of all of those and add one, right? So by sorting this vertices in topological order, I can then compute the longest path in the same order with the guarantee that when I want to compute the longest path to a given vertex, I have all the information available needed to do that, namely all the longest paths for its incoming neighbors. So if I do it naively, right, then I will write out my vertices in some topological order. And now when I come to this vertex and I want to compute its longest path, I will look at in my graph all the incoming edges and they will all be from vertices which appear before. So I can take the value here, the value here, the value here, and then take its maximum and then add one. Okay. So actually we will see that you don't need to do this backwards, you can actually do it forward. So we can actually incrementally compute the value at ik as we are going forwards, because going backwards requires to scan this list and look for all the incoming neighbors. So we will kind of implicitly do this longest path calculation along with topological sort side by side, as we will see in the next example. So here is an example in which we are going to compute the longest path as we are computing the topological order. So as before, the red numbers against the vertices are used for topological sort and they denote the in degrees. Right? So the initial in degrees are given by the initial edges in our graph. And what we do is we compute the longest path incrementally by starting by assuming that the longest path to every vertex is actually 0. Now when we enumerate a vertex in topological sort, what we did earlier was to update the in degrees. Right? So this is something that we already did. But now the additional thing that we do is we say that, well, if the vertex 1 had to be enumerated before 3, 4 and 5, then among the values that I know for the incoming edges of 3, 4 and 5, 0 was the maximum in length. So I must do 1 plus that. So these paths are at least of length 1. So the longest path to 3, 4 and 5 is at least 1. Okay. Now if I enumerate vertex 4, okay, then its longest path is at least 1. So therefore the longest path to 6 must be at least 1 plus 1. Similarly, the longest path to 8 must be at least 1 plus 1. And of course the in degrees will also reduce as before. So the in degree of 6 goes down to 1, the in degree of 8 goes down to 3, but the longest path to 6 is now the longest path to 4 plus 1. So it is 2, the same with 8. Now supposing I enumerate vertex 2, okay. Now 2 will again say that the longest path, because of 2, the longest path to 3 is 1, but it's already 1, so we don't change it. This will say because of 2, the longest path to 8 is at least 1, but we know it's at least 2, so again we don't change it. So when we delete a node, then we take basically the current value of the longest path for its outgoing thing plus 1, or the current value of the deleted node plus 1 and what is already known about that node, and we keep the maximum. So in this case, this 1 will become 0, this 3 will become 2, but here there is no change and here there is no change. Okay? Now likewise, when I remove this 5, this 2 will become 1, but because 1 plus 1 is 2 and we already know that 8 has a longest path of at least 2, we don't make any change in the 2. Now when we go to 3, 3 says it has a longest path of 1. So therefore, because of 3, the longest path to 6 is at least 2, but we already know it's 2, so again there is no change. Now we should do something interesting. So we say that 6 has a longest path of 2. 7 we so far have believed it has a longest path of 0, but through 6 it has a longer path. So the path to 7 must now be updated from 0 to 3. And now because of this, when we go from 7 to 8, the longest path for 8 must be updated from 2 to 4. Okay. And now finally this is my last vertex, so I just enumerate it and I compute its longest path as 4. So what this has said is the longest path is 4. Now we said that it would be done in 5 semesters, the same example, which basically means that in the first semester, all those whose longest path is 0. The second semester, all those whose longest path is 1. And so we have the same sequence you had before. So we initially do 1 and 2 in the first semester. Then we do 3, 4 and 5 in the second semester. Then we do 6 in the third semester, 7 in the fourth semester, and 8 in the fifth semester. So this is exactly the solution that we obtained informally on our initial example. So the pseudocode for longest path, as we saw, is very similar to what we did for the topological sort. We just have to keep track of this extra longest path value. So when we initialize the in degree, we also initialize the longest path to I to be 0 for every vertex. Okay, so this we are doing again first the adjacency list version. So we do n square work, right? For each vertex, we compute the in degree by looking at the column of the adjacency matrix with column entry I. But we also update, we initialize longest path to each I as 0. Now, when we are doing this enumeration, as before we choose any vertex with in degree 0, we enumerate it and we update the in degree of this vertex to -1, so it is no longer in contention for being chosen again. Now for all its outgoing neighbors, we update the in degree and we also update the longest path. So we take the longest path that we already know to that neighbor, LPT of k, and we take 1 plus the longest path for this node, and whichever is larger, we replace that back in LPT of k. So it's a very simple variation of the basic topological ordering thing, which allows us to also compute the longest path. Right? So this has complexity order n square for the same reason that we had found that topological sort with adjacency matrix as order n square, because we have these nested loops in order to scan all the neighbors. So as before, we can update this whole thing using adjacency lists and a queue to make it a linear time algorithm. So if you go back and look at the topological ordering algorithm, you'll find that the same changes are required to make it additionally compute the longest path. So what we do is initializing is again the same. We do it for every vertex. So this is an order n step. Right? We initialize both the in degree and the longest path. Then we go through all the adjacency lists, and together this is an order m step to compute the initial in degrees. And now we have an order n step in order to set up this queue where we will process the topological ordering. And then we do an outer loop of order n. Okay, so this is an order n loop because everything is going to go into the queue once and come out. So we are going to remove from the queue n times. And now, because we are scanning the list across all the n iterations, we are going to process each edge once. So the total work done in this loop is going to be order m. Right? So we do exactly as before. We update the in degree. We update the longest path to k as the maximum of the current value plus and 1 plus the value of the current node. And if we do find that the k has now become a vertex with in degree 0, we add it to the queue. So DAGs are very useful because there are many situations where we want to model dependencies between various objects. And topological ordering is a canonical algorithm to list out vertices without violating dependencies. And what we have seen today is that we can compute the longest path in a DAG. Okay? And the longest path in a DAG, in some sense, if we can list out vertices in groups, the longest path in a DAG represents the minimum number of steps in order to enumerate all the vertices. So if we can do courses in groups, then if we want to bunch it and do things which are at the same level at one time, then the minimum number of steps we need, then a minimum number of semesters to complete a set of courses, or the minimum number of days to complete a set of tasks, okay, is given by the longest path. Now it is important that we have been able to find an efficient linear time algorithm for longest path only because we restricted our attention to DAGs. If we look at arbitrary graphs, which are not necessarily DAGs, and we want to find longest paths, of course, if we have loops, the longest path will be undefined because we can go round and round a loop. So if we define a longest path to be one in which we have a sequence of vertices with no duplicates, so the length is at most n, okay, then in an arbitrary graph, this is a very challenging problem and there is no known efficient algorithm. In fact, it is part of a group of highly intractable problems which are all equivalent to each other and all believed to be very hard. So DAGs are a very significant subclass of graphs which have many practical applications, and which admit efficient solutions for very important problems which are not in general solvable easily on the full class of graphs. So let's turn our attention now to weighted graphs, graphs in which edges have costs associated with them. The most important thing that we can do with weighted graphs is to compute shortest paths. So let's review what we have seen so far. So we have been looking at unweighted graphs, that is sets of vertices and sets of edges where each edge is just a connection between two vertices. We have seen two systematic strategies to explore such graphs, breadth first search and depth first search. Now both of these will be linear in the size of the graph if we use an adjacency list representation for the edges. Now we saw that while we explore a graph using either BFS or DFS from a given vertex, not only do we discover which vertices are connected to the start vertex, we can also recover the path back to the start vertex by keeping extra information such as the parent of each node we visit. We observed that breadth first search, because of its layer by layer strategy, actually uncovers the shortest distance to every vertex in terms of the number of edges from the start vertex. And depth first search, though it does not find the shortest path, it gives us a lot of other information in terms of the order in which we visited. So by keeping track of the pre and post DFS numbering, we can actually recover structural properties of the graph. Now we look at what happens if we add costs to the edges. Now depending on the application, these costs have several natural interpretations. For example, in the initial example of a graph, we looked at an airline routing map. So on such a graph, the edge weight, the cost associated with an edge, could be the ticket price on the flight. Or if edges represent roads in a network of highways, then we might have a cost representing the toll that one has to pay on a particular segment of road. Or if we have a railway network, it might represent the distance between two stations. Or on a simple traffic road map of a city, it might represent how much time one might expect to take between two intersections at busy times. So in general, a weighted graph is just a normal graph along with an extra function which tells us the cost of each edge. It's usual to call this a weight function. So a weight function just assigns each edge in E some number. So let's think of it some real number. Right? So now if we have a path from V0 to Vn, okay, so we have a path from V0 to En, we have a sequence of n edges, V0, V1, V1, V2. Each of these in a weighted graph would have a weight, and a natural thing to do would be to add the costs of these weights. Right? So supposing these are distances, then the total distance, if we follow this path from V1 to Vn, will be the sum of the distances. If it's a sequence of flights, the total cost that we pay for a ticket will be the sum of the cost. Right? So we will extend weights from edges to paths by just adding up the sum of the weights along each path. And now a natural problem that we want to solve is to find the shortest path between a given pair of vertices. That is, what is the minimum cost that I can incur to go from V0 to Vn? So we have seen before that breadth first search will solve this problem if our cost is in terms of number of edges. Another way of saying it is that we can assume that each edge has the same cost, 1 or any fixed number, so that as I traverse more edges, the cost is proportional to the number of edges traversed. But if we don't have this property, if the costs can be arbitrary, then breadth first search does not work. For instance, in this example, we see that between 1 and 3 there is a direct edge, but its weight is 80. And we can do a shorter cost path from 1 to 3 by going via 2. So it has 2 edges, but the total cost is only 10 plus 6, which is 16. Right? So the shortest path in a weighted graph need not be the shortest in terms of number of edges. We are talking about the sum of the costs along the edges. So we might have longer paths in terms of number of edges, but shorter total cost. And our goal is to compute such paths regardless of the actual length of the shortest path. So we can ask two types of questions regarding shortest paths. One is the so-called single source problem. In the single source shortest path problem, we have a designated place from where we start all our paths, and we want to find the shortest distance to every other path. Now this has very natural application. So supposing you are a manufacturer and you have a factory where you make all your items. Now you have to distribute these items across the country. So how do you find the shortest way to transport your items from the factory, which is a single point, to all the places where it can be sold, to all the retail outlets? Or you might be a courier company. Now a courier company will ship all items to a given city to a centralized office, and from this centralized office it has to be distributed to all parts of the city. So how do you compute the shortest path from the distribution office to all the different addresses to which the courier items have to be delivered? Another problem would be to compute the shortest distance between any pair of cities or any pair of vertices. So this would be a natural problem. For example, if you have a routing network of an airline or a train network, now whenever you want to travel from city A to city B, you would like to compute the shortest path between A and B. For instance, if you use a service like Google Maps and you say that you want to go from a source to a destination, it will try to compute the shortest path and give you the time in terms of walking, driving, etc. Right? So we have two different types of problems. One where we have the single source and we want the shortest path to every destination, but only from that source. And another version where we want to find the shortest path between every pair of vertices. So we will begin by looking at the single source shortest path problem. So we have to designate in such a problem what is the start vertex. So maybe our start vertex, let us by convention assume it is the vertex 1. Remember that we usually call our vertices 1, 2, 3 up to n. So here we have a graph with 7 vertices, and the edge weights are written by the side of the edges in red. And we want to start at 1 and find out how to get from 1 to every other vertex in the shortest possible cost and a systematic way to compute this. So here is an analogy which will help explain the algorithm. So let's assume that every vertex is an oil depot and all the edges are pipelines, and the pipelines the costs are the lengths of the pipeline. Now when we set fire to this original vertex, start vertex 1, a fire will catch on all the pipes connected to vertex 1. Assuming that the fire travels at a uniform speed, right, it will reach the closest vertex first. Right? So the first oil depot that catches fire after the first vertex is the nearest vertex to 1. Then the second oil depot that catches fire is the second nearest vertex to 1. And assuming this fire is traveling at a uniform speed, by measuring the speed at which the fire reaches each vertex, we will actually end up computing the shortest path. So let's try to execute this analogy, this strategy on this particular algorithm. Right? So we begin by setting fire to the source vertex at time 0. Right? And now a fire will start going along the edge 1, 3 and the edge 1, 2. Now since the edge 1, 2 is shorter, in 10 units of time vertex 2 will burn. At this point we have indicated by the fact that there is a small burnt portion here that there is a partial fire going from 1 to 3, but it has only traveled 10 out of 80 units. Only 1/8 of the way it has traveled from 1 to 3. So at t equal to 10, vertex 2 burns, and we can say that this is the shortest cost or the shortest distance to vertex 2. Now the fire continues to propagate through 2 in two directions, right? From 2 to 3 and from 2 to 5. And meanwhile, of course, the fire from 1 to 3 also continues in the same rate as it was before. Now we can see that after 6 units of time, vertex 3 will burn. Right? So at t equal to 16, vertex 3 has burned. Now this has, the fire from 1 to 3 has traveled 16 by 80 of its distance. That the fire from 2 to 5 has traveled 6 by 20 of the distance. Right? Now having burnt 3, a new fire will continue in this direction. This old fire from 1 to 3 continues as before. And of course the fire from 2 to 5 continues as before. So now we have to see which of these will reach its destination first. So we can see that the fire from 2 to 5 has, in 14 units of time, will reach 5, by which time neither 3 nor 4 would have burnt. So if we continue another 14 units of time, at t equal to 30, we find that vertex 5 burns. And here we have done 14 out of 70 from 3 to 4. And we have done 30 out of 80 totally from 1 to 3. So these fires are still on their way from the source, the starting point of the edge to the ending point of the edge. Now continuing in this vein, the fire now propagates from 5 to 6 and 7, and you can see that in 10 units of time, we will find that vertex 7 burns. Okay? And now from 7, a new fire starts towards 6, there's an old fire coming from 5 to 6, but this will overtake it because this has only done 10 by 50, so there is still 40 units of time to go before the fire reaches 6 from 5, but in 5 units of time it will reach from 7. So therefore at t equal to 45, we find that vertex 6 burns. And now the only vertices which are remaining to burn are actually 3 and 4, right? So at this point, if we continue, we will find that at t equal to 86, actually sorry, vertex 3 had already burned. Though this fire had not reached it, vertex 3 had burnt. The only vertex remaining to burn was 4, and at time 86, that is 70 units after the fire started at the beginning of the edge, right? It finally reaches, and now everything is burnt, and now we have labeled each vertex by the shortest time it took for the initial fire to reach them, and this we claim is the shortest path to each vertex from the start vertex 1. So let's see how we would actually compute this burning process that we described. So what we do is we associate a time to the shortest distance as a quantity with each vertex, and initially we don't know anything, so we assume that the vertex is not reachable. That is, the shortest cost to every vertex is infinity. Now we know that the vertex 0, vertex 1, the start vertex is reachable in no time at all, so we assign its cost to be 0. And having assigned its cost to be 0, we can now recompute its neighbor's cost as the minimum of the cost that you can reach through 1 and the cost that we already know. So from 1 to 3, we can go in time 80, we believe right now it's infinity, so we know that we can improve the infinity to 80. Similarly, we can improve the infinity of 2 to 10. Okay? So in this process, we get 2 updates. Now all the other vertices, we still don't know how to reach them, so they don't get changed. Now among these two, we find that 10 is smaller than 80, so 10, now there can be no shorter path to 10. So we say that 10 is burnt, and we update its neighbors again. So we say that vertex 2 burns at time 10. Now because it burns at time 10, we can update the cost to 3 as the minimum of 10 plus 6, 16, or 80, which is 16. And now we can reset 5 from infinity down to 10 plus 20 is 30. So we continue in this vein, now using the fact that now among the things that are going to burn, 3 is going to burn at 16 and 5 is going to burn at 30, it's clear that 3 burns next. So we reset its status to burnt, and we update its neighbor, namely 4, to 16 plus 70 is 86. Now among those which are not burnt, namely 4 and 5, which have a finite value, 5 will burn next. So we set its status to burnt, and we update its neighbors to 80 and 40. At 6 we have 80 and 7 we have 40. Now 7 burns next, so we now look at the costs going out of 7, and we replace the 80 at 6 by 45. And now 45 burns next, 6 burns next at 45, so we mark it burnt, and finally we mark 4 burnt at 86. So to write this formally as an algorithm, we maintain this information about burnt vertices and the time it takes to burn a vertex in 2 different arrays. So we have an array called burnt vertices, which is a Boolean array. So it tells us whether a vertex has been burnt or not. And then we have an expected burn time array, which tells us the time at which a vertex is believed to burn. So initially we said that no vertices are burnt, so we set all the vertices to have burnt vertex value false. And initially we set the expected time for every vertex to infinity. Now infinity, of course, is a concept which is difficult to estimate, but we can easily check that no vertex can be at a distance which is bigger than the sum of all the costs in the graph plus 1. Right? Because at most you can actually, the shortest path will actually take even fewer edges, but at most you can use every edge. There's no point in using an edge twice. At most you can use every edge once. So if you add up all the costs in the graph and add 1 to it, then this can definitely be treated as infinity. No actual cost can be larger than this cost. Okay? So we can use infinity, but for infinity there is a concrete strategy to assign infinity. Now we start with the source vertex, which we assume is 1, set its expected burn time to 1, and now we repeatedly look at the smallest expected burn time, burn it next, and reset the expected burn time for all its neighbors based on the current burn time of that neighbor and the minimum of that and the value of the burn time through this vertex. Okay? So this is a very simple algorithm. So here it is in pseudocode. So we have these 2 vertices burnt vertex array and we have the expected burn time array. So we initialize burnt vertex to false and expected burn time to infinity for all vertices. Now we set the source vertex expected burn time to 0, and now we choose the smallest unburnt vertex. So we look for a U which has not been burnt and whose expected burn time is minimum, make it burnt, right? And for each of its outgoing neighbors which is not burnt, if the current estimate for that is bigger than the estimate of going through U, that is the burn time of U plus the wait from U to B, then you update the burn time of B to be the new one. So in our actual algorithm, burnt and expected burn time have a natural interpretation. So burnt is just visited. So when we have visited a vertex, we have burnt it. And the distance is just the expected burn time. So we can just rewrite exactly, this is the same algorithm. Okay, it's just that BV has been replaced by visited and EBT has been replaced by distance. Right? So we set visited to false, distance to infinity, start with the initial distance to the start vertex is 0, and then it repeatedly for each unvisited vertex with minimum distance, set it to be visited and update its neighbors. This is Dijkstra's algorithm for single source shortest paths. So now let's analyze Dijkstra's algorithm for the single source shortest path problem. So recall that Dijkstra's algorithm operates by burning vertices in the analogy we used. So we keep track of vertices which have been burnt or visited. Initially nothing is visited, and initially we don't know any distance to any vertex, so we assume all distances are at infinity. Then we start at the source vertex, let us call it 1 by assumption. So we set its distance to 0. Then we repeatedly pick up the first vertex which is not burnt and which has the minimum distance among those which are not burnt, visit it and recompute the distance to all its neighbors. So before we look at the complexity of this algorithm, we actually first have to verify that it is correct. So Dijkstra's algorithm now makes a sequence of updates. It is a bit analogous to BFS or DFS because it keeps visiting vertices and it visits every vertex only once. Now it visits vertices in a particular order which is different from breadth first or depth first, and we need to justify that this order is actually correct. So in some sense, at every point, breadth first search looks at all its neighbors and visits them, say, in the order of their vertex number. Depth first search will pick the first neighbor and then explore it further. Now Dijkstra's algorithm uses a different strategy, which is to pick the smallest distance unvisited neighbor. So we have to justify that this choice, which is never undone, that is, you keep going forward and you never go back and say, oh, maybe I should have chosen a different one, that this kind of a strategy actually is correct. So this is a general class of algorithms called greedy algorithms, where you have a number of possible trajectories or paths that you can choose to solve the problem. At each stage, you make the next choice based on some local information. At this point, this looks like the best choice to make. And then somehow, magically, this best choice that you make on local information turns out to be globally the best trajectory to take. So for such greedy algorithms, it's important to establish that this local choice of the next step actually gives us a global optimum, because very often this kind of a local heuristic does not give us a correct algorithm. So let's first look at the correctness of Dijkstra's algorithm. So the key to establishing correctness in this particular case is to establish what is called an invariant. Right? So now Dijkstra's algorithm proceeds, as we saw, in a sequence of iterations. There are n iterations. The invariant is that at each iteration we have this characterization of vertices as burnt and unburnt, and what we want to claim is that the burnt vertices are correctly solved. That is, at any point, if we look at the distances assigned to the vertices in the burnt set, then those distances are actually the shortest distances from the source vertex to that burnt vertex. So if we assume that this inductive invariant is true, now it is certainly true at the beginning, because right at the beginning the only vertex that we have burnt is the start vertex S. Right? So the first vertex we burn is S and we set its distance to 0. So certainly at that point this property is true, that among the burnt vertices the distances are in fact the shortest distances. Now assuming that we have extended the set for a few vertices, now we want to add a new one. So what we said is that we will pick a vertex V, okay, such that if we look at the distance to x plus the weight of x v, if you look at this total sum, which will be the updated distance to v, this is smallest among all the vertices which are not burnt. So the claim is that if we now add this to our burnt set, right, so we extend our burnt set like this to include v, then the distance to v cannot be actually smaller than what we have computed now, and it will not change because of a later update. So how will it change because of a later update? It could be that at some later point we actually extend our burnt set to include a new w. Now can it be that there was a path from y to w to v which is shorter than the path we have claimed just now via x to v? So it's easy to see that the distance to y plus the cost of wxy, now this must be bigger than or equal to the earlier thing, because we chose v and not w, because at this point w was not the smallest one, v was. Now perhaps they were equal, but certainly w was not less than v. So at a later stage, if we go to w, we know that we will take at least that much time to reach w, and then we have to additionally incur a cost of going from w to v. So there is no way that a later path that we can discover via y to w to v can be better than the current path from x to v. Right? So this re-establishes the invariant that the vertex we burn next is correctly solved. So this is a way to show that Dijkstra's greedy strategy actually solves this problem correctly. So now, having established that it is correct, let us look at the complexity. So there are some obvious loops in this. So there is an order n loop of initializing the visited values to false and the distances to infinity. Now there is another order n loop here, okay? And inside this order n loop there are two loops. One is more obvious than the other. So here, once we have visited a vertex, a new vertex, then we have to go through all its outgoing neighbors, right? So there is a scan of all edges which are going out of U. So that is one loop. But also there is a loop here which is kind of implicit, which is before we visit a vertex, we have to choose it, right? So we have to go through all the unvisited vertices and pick the one whose distance is minimum. So this, in general, we have seen that if we have a list or an array which is not in any particular order, then to find the minimum, we may have to scan the entire array. So this is implicitly an order n step. So this is an order n step, and the time it takes here depends on how we represent the edges. Right? So the outer loop runs n times, as we saw. In each iteration, we burn one vertex. This requires an order n scan to find the minimum vertex to burn. After we burn the vertex, we have to scan its neighbors to update the burn times of those vertices. Now, if we have an adjacency matrix, as we have seen, then if we are going to burn U now, then in order to find its neighbors, we have to scan the row for U in the adjacency matrix. So this will take order n time. Right? So we have an outer order n, and inside we have two order n things independent of each other. One is to find the minimum unburnt vertex to burn next, and second is to update all its neighbors. Right? So because we have this order n thing inside an order n loop, overall it is order n square. So now, one of the bottlenecks certainly is this adjacency matrix, right? So we have seen in BFS and DFS that if we move from an adjacency matrix to an adjacency list, scanning all the vertices of a particular, all the neighbors of a particular vertex becomes more efficient. So we can do the same thing here, right? So if we move from an adjacency matrix to an adjacency list representation, certainly the second order n loop within each iteration can be now counted as an overall order m cost, because across all the iterations we will explore every edge only once, because we'll explore it when we burn its source vertex. Right? So therefore, the second contribution of order n gets solved by using an adjacency list, but unfortunately we still have the first order n step, which is to find the minimum. So we have a list of burn times associated with the unvisited vertices, and we have to find the minimum among them, and this remains an order n step. So overall, though we have moved to an adjacency list, this alone does not help us, because we still have an order n step inside the big loop. So we are still at order n squared. So actually, to get around this bottleneck, we need to maintain the burn times in a more sophisticated data structure. So it turns out that we need data structure in which we can, of course, find and remove the minimum element quickly. But once we have that, we also need to be able to update the values quickly, so that overall both updating and extracting are roughly equally the same. So this can be done using a tree-like structure. In particular, we will see in a later lecture that there is a nice data structure called a heap, which precisely allows us to do these two operations in log n time. So if you have n values, then in log n time you can find and delete the minimum value, and we can insert a new value or update a value which is already in the heap. All these operations take only log n time. So if this, which we will see later, if this can be done, then what it says is that finding the minimum burn time takes log n time. Now when we update the vertices which are adjacent to the current burnt vertex, overall we do this OM times, right, because there are OM edges, but each update again takes O log n. So we have now two contributions to our complexity. So this comes from choosing the minimum vertex, right? So in order to extract the minimum vertex, we do this n times, and each time it costs us log n time. And then in order to update the distances once we burn a vertex, each time it takes us log n time, but we do this for each edge, so it's m log n. So we have n log n for choosing a vertex, and this is for updating the distance. Right? So overall, our algorithm becomes n plus m log n. So remember that in a graph, n plus m is really is the size of the graph. So this is really an n log n algorithm as opposed to the naive O n square. And we have seen in sorting and other such problems that this is a huge practical jump going from O n square to n log n. It's a huge jump in terms of the size of the problem we can hope to solve. So Dijkstra's algorithm makes a very crucial assumption which underlies the correctness of its greedy step, and that is that there is no negative cost associated with an edge. Okay? Our argument was that if we choose V as the next neighbor to add to our burnt set, then we can never find a shorter path coming this way. But obviously, if we have negative edges, then we could have a situation where I had, say, a path of length 2 here, right? And then I chose not to follow another path because maybe it is of length 4, but if I come back from there, right, maybe this has length -3. So if I come around this way, then I incur a net cost of only +1, whereas if I go this way, I get +2. Right? So therefore, by locally looking for the nearest neighbor, I don't necessarily find the shortest distance. So now, of course, you might ask why you would want to put negative weights in a graph at all. Well, remember that graphs are a very general model, and there are many situations where you can actually interpret negative weights in a sensible way. So supposing we are looking at, say, a taxi driver, and we are looking at a graph as a list of places where he picks up and drops off people. Now, obviously, there are segments where a passenger is in the car, and there are segments where he may not have to be, may not have a passenger. He may have to just be returning to a place to pick up. For instance, a taxi driver who operates from the airport might typically go back to the airport after every trip because he expects to find longer trips from there and within the city, right? So there are segments where he travels empty, there are segments where he has passengers. So some segments earn money, some segments lose money. So there are some positive edges and there are some negative edges. Another situation which is completely unrelated to anything we have seen so far, you can think of, say, chemical compounds, and we can represent a graph saying how we can transform one compound to another compound. And here, for instance, the edge weight can represent the energy which is either released or absorbed in this process. So again, it could be positive or negative, right? So there are many situations in which negative edge weights actually make sense. So what do we do if we have negative edge weights? So the first thing to notice is that if you have a negative cycle, okay, so if I have a graph in which I have, say, a loop like this, and all of the things add up, say, -3, -2, and +1. Then if I go around the cycle once, right, and come back, then I will incur a total cost of -4. So this means that if I had a path which started somewhere else, came here and left the cycle and went somewhere else, so supposing I had a source and a target, then I can make the distance from the source to target arbitrarily small by going round and round this loop any number of times. At each time I go around the loop, the cost reduces by 4. So I keep adding -4 to my cost. So the cost can be as low as I want, just depending on how many times I go around the loop. So if I have negative cycles in a graph, the question of a shortest path doesn't even make sense. I mean, there's no notion of a shortest path because the quantity is not well defined. But it turns out that if I rule out this, I could have negative edges but not negative cycles. So for instance here, if instead of +1, okay, I said that this was +7. Right? If I make this weight +7, and going around this cycle will cost me +2. So therefore it doesn't help me to go around the cycle because it will only add to my cost. So therefore in a situation where I have no negative cycles but I do have negative edges, it still makes sense to talk of shortest paths. And we will see later that there are other algorithms other than Dijkstra's algorithm which can handle these. In particular, we will look at the Bellman-Ford algorithm, and we will also see that the all pairs shortest path problem, which generalizes the single source shortest path problem, or the Floyd-Warshall algorithm, will also solve this thing regardless of whether the paths are negative or the weights are negative or not, provided there are no negative cycles. So now let's look at shortest paths in graphs where we allow negative edge weights. In particular, let's look at the Bellman-Ford algorithm. So recall that the correctness for Dijkstra's algorithm relied on an invariant property that every vertex that we burn automatically has the shortest path computed at the time when we burn it. However, as we saw, this argument doesn't work if we can have negative edge weights, because we may find later a path via a vertex which we have not burnt yet, which becomes a shorter path to a vertex we have burnt earlier. We also said that allowing negative edge weights is one thing, but allowing negative cycles is not a good idea, because once you have a negative cycle, you can go around the cycle as many times as you want and arbitrarily reduce the length of the path. So the shortest path is not even a well-defined quantity. So long as we have negative edges but not negative cycles, shortest paths do exist and we can hope to compute them. So let's first look at two basic properties about shortest paths, which hold regardless of whether the edges can be negative or not, provided we don't have negative cycles. So the first property is fairly obvious, that a shortest path will never go through a loop. So supposing I want to go from S to T, right? And suppose along the way I actually go through the same vertex twice and then I continue. Now what we know is that this is a loop, right? And since it is a loop, the weight is greater than or equal to 0. It cannot be negative because we have ruled out negative loops. So therefore, if I take this path and I just cut out this loop, then I have a direct path from S to T. And if I look at the cost of the direct path from S to T, it cannot be any bigger than this one, because at best this loop has 0 and I have decreased nothing, but in the general case, the loop has some positive cost and I have actually reduced the cost, right? So shortest path never loops, so it will never visit the same vertex twice. This means that it can at most n-1 edges, because I can only allow, so I totally have n vertices. So if I don't allow any vertex to repeat anywhere along the way, then obviously I can only have n-1 vertices, n-1 edges. Right? So there is a bound on the length of the shortest path. The other property is that regardless of how the shortest path looks, right, along the way every path that makes up the shortest path is itself a shortest path. So for instance, if I have a path like this from S to T, which goes through some intermediate vertices V1, V2 up to Vm, then if I look at the path only up to Vm, then this is the shortest path from S to Vm. There cannot be any shorter path, because supposing there was another shorter path, okay, suppose there is a shorter way to get from S to Vm, then I can take this, and the red path now will be shorter than the green path. Right? So therefore the fact that I am going to T via Vm and this is the shortest path means that there must also be only this much of a short path from S to Vm, and this holds at every point. So again, for example, S to V2, this must be the shortest path, because otherwise if there were a shortest path, then I will take that shorter path and then I will add on this path which I already have, and I will get a shorter path to everything from V3 onwards. Right? So every prefix of a shortest path is itself a shortest path. So these two properties are enough for us to arrive at the Bellman-Ford algorithm for shortest paths in the presence of negative edge weights. So to get to the Bellman-Ford algorithm, we have to analyze a little bit more about what is happening in Dijkstra's algorithm. So in Dijkstra's algorithm, whenever we burn a vertex, whenever we visit it, we update all its neighbors. Right? So we update the distance of when we burn a vertex j, we update for every edge jk, right? We update the distance to k to be what distance we already know for k, together with the distance to j and the edge from j to k. So we have a newly discovered distance through j perhaps, and we compare it to the distance we already know and we keep the smaller of the two. So let's call this operation an update, right? Updating k from j. So in Dijkstra's algorithm, we only do this update when we burn j. And the correctness of Dijkstra's algorithm says that when we burn j, the distance to j is the correct distance to j. Right? So what we have seen is that in the negative edge weight case, if we use the strategy of Dijkstra's algorithm, this may not be the case. That when we burn a vertex, just because it's in the shortest expected distance among the unburned vertices does not guarantee that this is the correct distance. Right? We might find later on a smaller distance. But in spite of this, this update operation has some useful properties which we can exploit. So the crucial thing is that the update gives us an upper bound on the distance to k. Right? We already have, so at any point the invariant that we have is that the value that we have in distance to k is greater than or equal to the actual shortest distance from the source to k. Initially we may assume it is infinity, so that is surely greater than the actual shortest distance. At any point when we reduce it because we have found a concrete path which gives us a shorter distance. Right? So when we do this, after this update, we know that the distance to k is no more than the distance we have just discovered through j. Because if it was already less, then we keep it that way because we found it through a previous j prime, or we have found it now, in which case we have updated it in this update operation. This also means, because of our previous observation about shortest paths, that if actually on Dijkstra's algorithm also, that if distance j is actually correct, and the shortest path now consists of just adding this edge, okay, we are not claiming it is, but if it is the shortest path, then the distance to k will be correctly computed. Okay? So in a nutshell, this update operation is a safe operation because it will never bring distance of k below the actual value. So it will always be above the value that we want. So we can keep doing spurious updates or unnecessary updates and it doesn't hurt us. Okay, so redundant updates cannot upset this calculation. It just may not make progress, but it will not send us to a situation from which we cannot recover the minimum cost. Because we will always be at or above the minimum cost. So whenever we do a min, we will always be coming down but not crossing below the actual value we want to find. So if we look at Dijkstra's algorithm, then what it does is a particular sequence of greedy updates. Right? It chooses the smallest distance vertex which is not burnt and burns it. And the proof breaks down because this sequence does not necessarily give us the shortest path if the weights can be negative. So a natural question to ask is, what sequence of updates should I do in order to actually get the shortest path? Is there a better way of computing this, the sequence of updates rather than going via the greedy heuristic of Dijkstra's algorithm? So suppose we have two vertices s and t. We want to find the shortest path from s to t, and suppose there is the shortest path, okay, which goes via v1 to vm as we have seen before. Now, if we do the updates in this order, that is, we first compute the update from s to v1, then we compute v1 to v2, then we compute v2 to v3. In between, we can do other things. It's only that these updates happen in this sequence. Then v3 to v4 and so on, and finally we do vm to t. Then what do we know? Well, we knew earlier that if we had correctly computed the distance up to s, then this update will correctly compute the distance up to v1 because this is the second last node on this, right? So if distance of j is correct and j is the second last node on the shortest path to k, distance of k is correct after the update. So because distance of s was 0 and it was correct, when we do update SV1, this distance becomes correct. Now we might do all sorts of other updates which don't bother us. But now when we come to V2, we will be updating V2 from V1, and V1 is the second last path and this shortest path. And therefore this also becomes a correct value. And then this also becomes a correct value. Right? So in the middle of all these updates, if we identify this particular subsequence of updates, S to V1, then V1 to V2, then V2 to V3, then we have got the distance. Okay? So now the question is, how do we make sure that we have this sequence of updates for S and T? So Bellman-Ford algorithm basically says, don't try to find a particular sequence, just generally compute all possible sequences of updates. So at a high level, this is the algorithm. It says initially assign the distance of S to be 0 and the distance of U to be infinity for every other vertex. Now you just blindly do every update n minus 1 times. Right? So what you do is initially you update for every edge, given the fact that s has distance 0 and u is infinity otherwise. Then we update everything. So all of these updates where s is the source vertex and v is the target vertex, these will give us now some finite values for these v's, whereas these will just remain infinity. Right? So this will become finite and these will become infinity. Now you have done one full sequence of updates in which other than s, all the neighbors of s now have some finite values. Now you do this whole thing again. Right? So you update every edge again. And then you update every edge again. Now we know that a path, shortest path between any two vertices has at most n minus 1 edges. Therefore, if we do this thing n minus 1 time, the claim is that if I want any sequence of updates, I might find a sequence of updates which goes like this, or I might find any sequence of n minus 1 updates which is a legal path will be represented in this. Okay, so this is a very clever matrix which has all the updates after one iteration, all the updates after two iterations. Now if I want a particular sequence of update E1, then update E2, then update, then I will find E1 here, then I will look for E2 here, then I will find E3 here, and then so on. Right? So every possible path is represented. In particular, given our example here where S goes from, the path goes from S to V1, V1 to V2 and so on, then we find that the first update comes in iteration 1. Then after having updated V1, the next iteration V1, V2 gives us the correct distance to V2. Iteration 3 will give us V2 to V3 and so on. And finally, iteration n minus 1, actually this may not be n minus 1, it depends on the length of this path. So if this path actually has n minus 1 steps, then the last one will give us the update from Vm to t and the correct distance for t. But this could actually be even less than n minus 1 if the path is of lesser length. So the algorithm is actually remarkably simple. Right? You start from a source vertex S. So initially you assign the distance to be infinity for every vertex and you initialize the distance of S to be 0. Now n minus 1 times you blindly repeat the following operation. For every edge in your graph, apply the distance update. So you take the distance of the target of that edge to be the minimum of the current distance for that target or the distance to the source of the edge plus the weight of the edge. Right? So you just blindly do this n minus 1 times, and because of this property that you will find for every valid shortest path, you will find a sequence of updates which matches that path in this sequence that you are computing here, you will always get the shortest path to every other vertex starting from S. So let's look at an example and see how the Bellman-Ford algorithm actually works. So here is a graph which has some cycles and it has some negative weights, but there are no negative cycles. For instance, you'll see that here we have a cycle whose weight is minus 2 plus 1 is minus 1 plus 2 is plus 1. Okay. Similarly, here we have a cycle whose weight is, if you go around from 6 to 3 to 4 to 5, you have minus 2 plus 1 is minus 1 plus 3 is plus 2 minus 1 is plus 1. Right? So this is again a cycle of plus 1. So there are negative weights but no negative cycles. And now in this we want to compute shortest paths from 1 to every other vertex. So 1 is our source vertex. So we set up this iteration. So in the initial step we set the distance of vertex 1 to 0 and everything else is infinity. Now we will, in the first step, try to update all neighbors of things that we have here. Now all values which are infinity will not update their neighbors, but the value 1 will. It has two neighbors, right? 2 and 8. So these two things now become finite values, 10 and 8 respectively. Now we have these three vertices which are got finite values. So you would expect that their neighbors, namely 7 and 2 has a neighbor 6. So the only outgoing edge from 2 is 6, the only outgoing edge from 8 is 7. So you'd expect 7 and 6 to get updated. And indeed, in the next step, you find that 6 and 7 get values which are updated from those values. So 8 plus 1 is 9, 10 plus 2 is 12. Okay. Now having got this, you will find that we have now updated 1, 2, 8, 7 and 6. Now notice that I now have another path, not this path from 1 to 2, right? But I have a path which goes this way from 1 to 2 via 7, and this becomes a smaller path because of this minus 4, right? So in this iteration, I will actually find the first non-trivial update which would violate the Dijkstra assumption that all burnt vertices are invariant, right? So the distance to 2, which was already computed to be 10, will actually shrink. In addition to that, of course, because we have new neighbors of 6, so 6 will now give us a new value for 3 and so on. So in this iteration, I find, as I said, that the value of 2 reduces, the value of 3 becomes something finite. Notice the value of 6 itself changes. Why? Because earlier we were looking at a path like this, and now we have discovered that there is actually a better path like this, which has also a negative edge to add to the benefit. Okay, so we come down from 12 to 8 plus 1 minus 1 is 8. So we continue like this. At the next step, the path to 3 shrinks further. Okay, and that's because now having got a better path for 6, so in the previous path we said, oh, the path to 6 was 12 and 12 minus 2 was 10, right? Now we said, oh, it's not 12, it's 8. So 8 minus 2 is actually 6, right? So we've got a better path to 3. We have discovered a new path because we had a path to 3 from 10 plus 1 is 11 and so on. Okay. So we continue one more step, and then because now we know that 4 was reachable in 11 steps, 4 plus 3 is 14, so 5 is reachable, but 4 itself now, because the value of 3 got updated, so the value, in this iteration the value of 3 gets updated from 11 to 7. This will get propagated after one more iteration, so now this value comes down from 14 to 7 plus 3. But in this process, what has happened is that the value of 3 has itself gone down one more time, right? So its value again reduces the value of 4. And then finally, after the n minus 1th iteration, we get a stable set of values. So these now turn out to be the shortest paths to all the vertices from the start vertex 1. So what is the complexity of this algorithm? Well, we have this outer loop. So we just run this update n minus 1 times. So it runs order n times. And now in each loop, we basically blindly update every edge. So we have an adjacency matrix. We have to identify the edges. The only way is to look at every entry, and wherever we see an entry, we take that jk and we update it. Okay. But in an adjacency list, we have exactly the edges that we want, right? So we have 1, 2 up to n, and we have exactly the edges. So we can do this update in order n time. So if we use an adjacency matrix, just identifying which are the edges takes us order n square time, because we have to probe every entry in the adjacency matrix. Adjacency list, we can do it in order m time. So therefore, if we use an adjacency matrix representation, overall Bellman-Ford algorithm takes n cube time, whereas with an adjacency list representation, we can reduce it to mn, and so if therefore the number of edges is small, this is going to be a much better solution than n cube. So let's now turn our attention to the all pairs shortest path problems, where we try to find the shortest paths between every pair of vertices in a graph. So recall that we are working with weighted graphs. We allow negative edge weights but not negative cycles, because with negative cycles the shortest path is not well defined. With negative weights, it is well defined. We saw that the Bellman-Ford algorithm allows us to generalize Dijkstra's algorithm and compute single source shortest paths in weighted graphs with negative weights but without negative cycles. So now we want to further generalize this and compute not just the shortest paths from a single source, but the shortest paths between every pair of vertices. So as we explained at the beginning, an example would be if you are trying to run a travel website or an airline website, and somebody wants to find the minimum cost or the minimum time flight or train between any pair of cities. So we made the following observation about shortest paths. Okay, that a shortest path, even in the presence of negative weights, will never loop, because we can always remove the loop without increasing the length of the path. So therefore a shortest path never visits the same vertex twice and has length at most n minus 1. So we exploited this algorithm in one way for Bellman-Ford, and we will find that we can use it now for an inductive algorithm for all pairs shortest paths. Right? So we will come up with an inductive solution of how to build up the shortest paths. So we are basically going to build up shortest paths in terms of vaguely their length, but more specifically what vertices we allow in between. So the simplest shortest path you can imagine between a pair of vertices is just a single edge, right? So if you have a single edge and this happens to be the shortest path, then you're in good shape. But in general, this may not be the shortest path, because even if there is such an edge, there may be a way because of edge weights or even because of negative edge weights of reaching from I to j via a longer path of edges, but with a shorter overall cost. But what we do know, because of this characterization of shortest paths, is that this path from I to j goes through some intermediate vertices, all of which are different from each other. No vertex is visited twice. And secondly, now none of these vertices is either I or j. There's no point in coming back to I and then going to j. So there is no loop anywhere in this path. So what we will do for this inductive thing is to restrict what can happen in between I and j. Okay, what are the vertices that are allowed and we'll gradually increase the set. If we allow any vertex, then of course we will get arbitrary shortest paths. So recall that vertices are numbered 1 to n. So we will compute a quantity wk of ij to be the weight of the shortest path from I to j, where we restrict the vertices that can be used to go from I to j to be between 1 and k. In other words, we have the set of vertices v, right? So we cut it off saying we have 1 to k and we have k plus 1 to n. And we say that only these vertices can be used in the path. Now, the endpoints themselves need not be, but if the point is that if the endpoint is outside, okay, then it can still, so I could have one vertex here and then it could have a path which goes like this and then come back here, right? So it only says that the intermediate vertices, so when I start with I and go to j, what happens in between lies in the set 1 to k, right? So in particular, if k is 0 because our numbering is 1 to n, it says that the vertices that can appear cannot be include 1. So in other words, if I have w0, then it says all of the vertices 1 to n cannot appear on the path. So the only way that we can have such a shortest path is with a direct edge, right? So w0, the base case of this inductive definition, says that the shortest paths between I and j, which exclude all vertices from 1 to n, are of the form edges between I and j. Okay. So now, since this is an inductive definition, what we have to say is, supposing we know the shortest paths which use 1 to k minus 1, then how do I compute the shortest paths that use 1 to k? Right? So we know among all the paths which use at most 1 to k minus 1, what is the shortest path from I to j? How do we now compute? If we allow vertex k also to be used, how do we compute what would be the shortest path from I to j? So there are two cases. The first case is that this extra vertex k is not useful. The shortest path, even if I include k, does not use vertex k. It's enough to use 1 to k minus 1. In this case, the shortest distance from I to j using 1 to k is the same as the shortest distance from I to j using k minus 1. So I can say wk of ij is the same as wk minus 1 ij. On the other hand, it could be that using k does give us a non-trivial improvement, right? So we have now some path which goes from I to j, and on the way it visits k. So if it visits k on the way, then we can break it up as a path from I to k and a path from k to j. But notice that we have already said that this vertex k, or any vertex for that matter which appears on this path, if it is the shortest path, appears only once. Right? So if k appears here, there is no k between I and k, and there is no k between k and j. This means that I have a path from I to k already, which goes through 1 to k minus 1, and I have a path from k to j already which goes through 1 to k minus 1, and I am combining these two. Right? So I can break up the path as a path from I to k and a path to k to j, each of which uses only 1 to k minus 1. And what is the cost of that path? Well, we inductively know that we have the cost of the best path from I to k using only 1 to k minus 1 in wk minus 1. We also have the best path from k to j in our matrix wk minus 1. So if I add these two, this must be the best way of going by k. Right? So combining the cases, we say that either we don't use k, in which case we take the value of the old matrix, or we do use k, in which case we combine two entries going via k in the old matrix and we take the smaller of these two. Right? So whichever one of these is smaller will be the correct value of the shortest distance from I to j going through 1 to k. So this gives us an immediate algorithm which is called the Floyd-Warshall algorithm. So we start off with a matrix representing the function w0. So w0 has entries which are exactly the edge weights. So if there is an edge from I to j, w0 I to j says there is a direct path of that weight. Because remember, w0 cannot go through any intermediate paths. And if there is no edge, since I can't go through any intermediate vertex, w0 ij must be infinity. Now for k in 1 to n, I basically repeat this n times. I first allow 1 to be used, so I compute w1 from w0. And how do I do that? I use the update rule we said earlier, that is, you take the minimum of what you already have plus the possibility of going through the newly introduced vertex. Then I will allow 1 and 2, then I will allow 1, 2 and 3. And obviously, if I have allowed 1, 2, 3 up to n, I have allowed all the vertices to appear in between. Wn will now have the shortest paths with no constraints. So I need to do this update exactly n times, so that after n times I have captured the shortest weight paths which include any arbitrary combination of vertices on the path. So the actual code is again like Bellman-Ford, extremely straightforward. Right? You just have first an initialization which sets every weight to infinity and then updates the non-trivial weights for those edges which are in the graph. So we are keeping track of this function W0 of ij by a three-dimensional matrix. So I and j represent the two vertices and the 0 represents the iteration number. Right? So initially W0 ij is either the weight of ij if there is an edge, or it's infinity, and that's what these first two steps are doing. And now we do this n times we do this iteration, that is, we update all the wij's at level k to be the minimum of the wij's at level k minus 1 or the sum of the two. Right? So implicitly here it should have been written. So this is for I equal to 1 to n, for j equal to 1 to n. Okay. So we have this update rule, and we do this blindly n times, and at the end we claim that the matrix W in the entry k has got the correct shortest paths for all pairs of vertices. So let's look at the same example that we saw for Bellman-Ford. Okay. So initially we assign to each, so W0 okay, has the edge weight. So we have an adjacency matrix like representation in which, for instance, we say 1 to 2 there's an edge of weight 10, 7 to 6 there's an edge of weight minus 1, and so on. Right? So we just duplicate all of these edges in the matrix and everything else is left at infinity. Now from W0 we go to W1 by considering all new paths that we can find by going from 1. But now notice that there is nothing that is coming into 1. So this is signified by the fact that the column 1 has infinity. No edge goes into 1. So no other vertex can use the fact that 1 is connected to 2 and 8. Right? So if you update using update rule, you will find that W1 is actually equal to W0. Nothing changes because allowing 1 to be used in between two vertices doesn't help us. It is not in between any two vertices. I cannot go from anywhere to 1 and then from 1 to that vertex. On the other hand, if I can now include 2, then I can do interesting things. I can go, for example, from 1 to 2 to 6. And I can go from 7 to 1 to 6. Right? So allowing 2 and 1 as an intermediate vertex, so 1 doesn't help right now, but allowing 2 gives me something. So if I now look at W1, I don't need W0 anymore. If I look at W1, then I will, as I said, be able to explore paths through 2. So in particular, 2 goes to 6. So anything pointing into 2, so 7 to 2 to 6, 3 to 2 to 6, and 1 to 2 to 6. These three entries will get updated. Right? So 1 to 2 to 6, so I get a new entry 12. 3 to 2 to 6, so I get a new entry 3. And 7 to 2 to 6, so I get minus 4 plus 2 is minus 2. Okay. Now from W2, likewise, I have to compute W3. Again, to compute W3, we'll come back to this later. I don't need W1, I only need W2. So I can throw away W1 for now and just look at W2. Right? So now having got, now I'm allowing myself to use 1, 2, 3. So I will look for things that can go through 3. Right? So for instance, now through 3, I can go from 6 to 4, for example. Okay? So I will get entries of that form. So I can go from 6 to 4 with a new thing. I can also go from 6 to 2, right? So now I have a new way of going from 6 to 2. Okay, so that also gets updated. And interestingly, I also discovered that there is now a path from 6 to 6. Right? Because earlier I didn't know that, but now that I'm allowed to go through both 2 and 3, I can go from 6 to 6. So I've discovered this loop which has a positive weight. If it didn't have a positive weight, we were in trouble because this didn't have a well-defined solution and so on. Okay, so you can just keep on doing this. We will not update up to W, but if you would now go all the way and you go up to W8, okay, then after you allow everything from 1 to 8 to be an intermediate thing, this matrix will actually compute all pair shortest path between any ij. So this algorithm, it is very easy to see that the complexity is order n cubed because you have n iteration, and in each iteration we are updating the entire matrix which has n square entries. Okay, so there's not much you can do to improve this because it is an adjacency matrix based algorithm. We cannot move to lists. We don't have to compute any minimum, maximum. So there's nothing much we can do. It's an n-cubed algorithm. Okay. Notice that it sort of solves, as a trivial case, the Bellman-Ford algorithm, because once you've computed all pairs, okay, so this generalizes as a solution Bellman-Ford, because in particular, if you now want all the shortest path from a given S to everything, you just have to look up that particular row in the Floyd-Warshall matrix, right? You look at the row S and all the entries will say the shortest path from S. But remember that in that particular case, if I only wanted from S, Bellman-Ford with a clever adjacency list representation would take order mn, whereas here this will require order n cube, right? So this does generalize Bellman-Ford in the sense you get the same answers that you would have got from Bellman-Ford and more, but you are always spending n cube time. Whereas if you have very few edges in your graph, which is typically the case, Bellman-Ford will be more efficient. So if you are using, you only want to do single source shortest path, you should not typically jump directly to Floyd-Warshall. You should probably do Bellman-Ford instead. About space complexity, so we said that we are going to represent each W0, W1, etc. as one coordinate. So we basically have n times n because we have n times n is the actual matrix, and we have n of these matrices because we have level 0, level 1 and up to level k, level n, right? But we saw that in our worked out example that when you need to compute the level 1, we only need level 0. Then we can throw away level 0. And when you need to compute level 2, you need only level 1. So in some sense, you can keep only 2 copies and keep switching back and forth, right? You overwrite the 0th level as a second level, you overwrite the first level as a third level, and so on. So you need only 2 slices, as I'll call it, of this 3-dimensional matrix at a time. So you can just keep oscillating between these 2 slices. So overall, you have 2n squared space, right? So we don't normally worry about space, but just an observation that in this particular thing, you don't really need to have this n cubed array. You can have 2 n squared array or an n squared array with 2 indices and keep oscillating between the 2 and get the same effect because you only need 1 copy to compute the other copy. So let's conclude this discussion with some historical remarks. So Floyd-Warshall, as you can see from the hyphenation, is a hybrid name for this algorithm, and actually there are 2 distinct algorithms which comprise it, which have a very similar structure. So the original algorithm, which was proposed by Warshall, is for what is called transitive closure. So transitive closure is exactly the same as computing a path from edge relation. So supposing you have a relationship like friend, right? So you know among a group of people who is a direct friend of whom, then you might want to ask who knows indirectly, right? So I know somebody indirectly if I have a friend who knows that person, or if I have a friend who has a friend who knows that person, and so on. So knowing somebody indirectly is the transitive closure of the friend relation. In the same way, in a general, so in every graph, if you put the friend or the whatever relation you want as the edge relation, the transitive closure is a path relation, right? So you want to you have an adjacency matrix which represents the edges. You want to compute a path matrix which represents the paths, which are the pairs of vertices computed by which are connected by paths. And so Warshall described the similar algorithm what we wrote now, and we will just do it in a little detail in the next couple of slides. To do this, compute P from A, and what Floyd observed was that you can adapt the same algorithm. So in Warshall's algorithm, you're only checking is there a path, and Floyd's algorithm says that you can actually adapt it to compute shortest paths. So the idea is very similar to what we've seen before. Let's go through it quickly. So we have an adjacency matrix A, which tells us the edges. So Aij is 1 if there is an edge, and we want a path matrix Pij is 1 if there is a path from I to j. So we will again compute iteratively this quantity Pkij, which says that there is a path and this path uses only the vertices in 1 to k. So k plus 1 to n cannot appear in the path, right? And again, the endpoints are not included. So I and j are arbitrary. It's what is between I and j which is restricted by this superscript k, right? So between I and j, you can only see things from 1 to k. So as before, if you do P0, it says nothing can appear because you rule out everything from 1 to n. Okay? Therefore, P0 is just the adjacency matrix. Okay? So now we have a very similar update rule. So if I know the paths which can be discovered using 1 to k minus 1, what are the paths I can discover using 1 to k? Right? So if there is a path already without using k, then I can just keep that path. So we could either have that pk. So remember now, this is there a path, is there not a path? So this is like an adjacency matrix, there's no weight. So it's a 0-1 matrix or a true-false matrix. So initially the adjacency matrix has 1 or true whenever there is an edge, false whenever there's no edge. So if I've already got an entry true with k minus 1, then I can keep it. On the other hand, maybe I don't have an entry true, I have to go by k. But once again, that means that there is a path from I to k and there's a path from k to j. And here I use only k minus 1 and here I use only k minus 1 because k needs to appear only once. Just like in the shortest path, if I'm just looking for some connectivity, I don't gain anything by going back from k to k because I can just remove that and I and j will remain connected. Right? So I need to only look for paths which have one copy of every vertex along them. So therefore I can assume there is a path from I to k which does not use anything outside 1 to k minus 1 and likewise from k to j. Right? So here now instead of min and plus, my operations now become or and and. So either I want a path from I to k and a path from k to j, or I want an existing path from I to j which never use k at all. Right? So I have this and operation for combining these two existing paths. So this should be p, sorry. And then I have an or operation which combines it in case 1. Right? So earlier we had w k minus 1 ij. And then we had this wk minus 1 ik plus wk minus 1 kj, and we took the min of this. Right? So here instead of this plus we are using and instead of this min we are using or. Right? So you can see that the algorithm is not exactly the same, but it's very similar. So this was the algorithm proposed by Warshall. Right? So you initialize everything to false, and then again this should be for I is equal to 1 to n, or j is equal to 1 to n. So you initialize all the paths to false, then you set explicitly that the 0th level paths are true if there is an edge, and then you keep updating the kth level path by either saying that there was already a k minus 1 level path, or I can find 2 k minus 1 level paths via an intermediate level k, intermediate vertex k. Right? So it's a very similar thing, we just have these operations of or and instead of min and plus. And then Warshall's algorithm was used for transitive closure, and Floyd generalized it for shortest paths, and these work in the presence of negative edges. It doesn't matter, Floyd's algorithm doesn't care whether the edges are negative or positive, so long as there are no negative cycles. So having seen a variety of algorithms for shortest paths on weighted graphs, we now move to a completely different problem, that of computing what is called a minimum cost spanning tree. So to motivate the problem, let's consider the following example. Suppose we are in a district which has a road network, and after a bad cyclone, the roads have all been damaged. So the first priority of the government is to restore the roads so that relief can be sent to various parts of the district, and also people can start moving around again. So the priority is to restore enough roads so that everybody can move around. So the first criterion for the government to restore roads is to ensure connectivity. So given this, which set of roads should the government restore first? So if the main criterion is minimum connectivity, then it should be clear that there is no point in restoring roads which form a loop. For instance, supposing we restore all these 4 roads, right? Then we could have deleted any one of these roads, say 3 to 4 or 2 to 3, and still one can get from any of these 4 towns to any 4 other towns in the district, right? So removing an edge from a loop cannot disconnect a graph, and our aim is to find some subset of edges within this graph which are connected in such a way that this is a minimal such set of edges. So what we want is a connected subgraph of this original graph which doesn't have any loops, which is acyclic, and this is precisely what is called a tree. Right? So tree by definition is a connected acyclic graph, and in particular we start with an arbitrary graph, and we are looking for a tree which sits inside that graph, which is a subgraph in terms of the number of edges, which connects all the vertices in the original graph. So such a tree is called a spanning tree. Right? It spans the vertices of the original graph, but it forms a tree out of a subset of the edges. So in this graph, for instance, one spanning tree we could form are the red edges shown here, 1 to 2, 2 to 3, 3 to 4 and 4 to 5. Of course, we could form other spanning trees, for instance this green one, which is 1 to 3, 2 to 3, 2 to 5 and 4 to 5. Right? So there are many possible spanning trees that one can construct on a given graph. Now suppose that the graph also has weights. In this example, the weight, for instance, could be the cost of repairing a road. So supposing restoring a road has a cost, and now the government would like to not only restore connectivity, but do it at a minimum cost. Right? So if, for instance, the government chose to repair this tree of roads, then the total cost is 18 plus 6, 24 plus 70, 94 plus 20, 114. So it would incur a cost of 114 to restore this spanning tree. On the other hand, if the government chose this green spanning tree, then the cost reduces to 10 plus 6 is 16, plus 20 is 36, plus 8 is 44. Right? So different spanning trees now will come with different costs, and the goal would be to reduce the cost to the minimum. In this particular example, you can check that this green tree, which has cost 44, is actually the minimum cost spanning tree on this particular graph. So before we move ahead to algorithms to compute minimum cost spanning trees, let us look at some basic facts about trees. So remember that by definition, a tree is a connected acyclic graph. So the graph in general will have n vertices. So the claim is that any tree has exactly n minus 1 edges. Right? So this is very easy to prove. There are many different ways of proving it, and here is one way of thinking about it. So supposing we have a tree, right? So initially the tree is connected by definition. So the entire graph forms one connected component. Remember that when we did breadth first and depth first search, we said that we can take a node and look at everything connected to it, and it forms a connected component. So this tree defines one single connected component if we look at it as a graph in isolation. Now, because it is a tree, if I have an edge from I to j, right, there cannot be any other path going from I to j by some other edges, because if not, that path plus this edge would form a cycle. Right? So if there is an edge from I to j and I remove it, then by definition, this component containing I and the component containing j must get disconnected. So if I started with one component, now I get two components. Right? So I delete the first edge from the graph from my tree, and I have one component more. Now I delete one more edge. By the same argument, whichever component that edge belongs to will split again. So each time I delete an edge, I increase the number of components I have. But then I know that in the end, if I have n isolated vertices, I can have at most n components. Right? I cannot have more than n components if I have n vertices. So I can only do this deletion n minus 1 times. Right? So I start with a tree, I keep deleting edges until everything is disconnected. I can only do this n minus 1 times, and I must do it n minus 1 times to get everything disconnected. Therefore, the tree must have had exactly n minus 1 edges. Now, if I take a tree and then I add an edge, it must create a cycle. We already saw this in the previous argument that we said. So supposing I have a tree, right? So a tree in general looks something like this. So it is a graph which has kind of no cycles but many things branching out. Now if I create a tree, supposing I add an edge, supposing I take some I there and some j here and I decide to add an edge. Right? So we know that because it's a tree, there is already connection. So there is some path, which in this case through this vertex from I to j. So for that path p plus this edge forms a cycle. Right? So in a tree, I have exactly n minus 1 edges. And when I add any extra edge, no matter which edge I add, it will definitely form a cycle. So another consequence of all these definitions is that between any two paths, any two vertices in a tree, there can only be one unique path. So supposing there are actually two paths. So let us look at two vertices here. We have drawn them as I and j, and suppose there are two paths. Right? So if I follow the two paths, okay, then it's very clear that because there are two different ways of going there will be some loop somewhere in between. Okay, so notice that it need not be a loop including I and j, it could be somewhere in between I and j, but if you consider all the cases carefully, you can convince yourself there is no way to have two distinct paths from I to j without creating a loop. And if we have a loop, then the graph is no longer acyclic, so it's not a tree, which is our assumption to begin with. Right? So we have actually the following claim that if we have these three properties, that G is connected, G is acyclic, and G has n minus 1 edges, then any of these two imply the third. So if G is connected and G is acyclic, by definition it is a tree, and we have just shown in our first argument that any tree has n minus 1 edges. So the fact that the first two imply the third is what we have already shown. Now you can easily convince yourself or find a formal proof that if G is acyclic and has n minus 1 edges, then in fact it must be connected. Everything must be connected to everything. And finally, if G is connected and it has n minus 1 edges, then it can only be an acyclic graph. It cannot have any loops. Right? So these are various ways of looking at trees, and sometimes we will use one property or another property. So it's useful to keep these things in the back of our mind when we talk about trees in general. So our target right now is to build a minimum cost spanning tree. So there are two natural greedy strategies that one can think of. One is, since we are looking for a minimum cost tree, to start with the smallest edge and incrementally build the tree. So we keep adding edges to the existing tree so that the new graph remains a tree and it grows as little as possible in terms of cost. This will give rise to an algorithm which is called Prim's algorithm. It will also turn out to be very similar to Dijkstra's shortest path algorithm with a single source. The other strategy we can have is to look at edges in ascending order of cost and keep adding them so long as we don't violate the tree property. Now this is different from Prim's algorithm because here we don't build a tree to start with. We keep adding edges so that we don't create a cycle, but we could have disconnected groups of edges, but eventually they will all connect up to form a tree. So we will see these in more detail in the next two lectures, but let's just look at an intuitive example of how these two strategies work. So let's look at these two algorithms intuitively. We'll come to them in more detail later. So let's start with Prim's algorithm. Remember that the strategy in Prim's algorithm is to start with the smallest weight edge and then incrementally grow a tree. So we start with the smallest edge here, which is the edge weight 6 between 2 and 3. Now we have to look at the existing tree, which consists of this part of the graph, and decide whether to add one of these 4 edges to extend it. We can't add that edge over here. We cannot add this edge because it would not form a tree. It would be disconnected from this edge. So we can add any of these, but we choose the smallest one. So in this case, we choose the edge with weight 10. So the next step in the tree is to add the edge 1, 2, and now we have this tree. Okay. Now if we look at the possible edges that we can add, we have this edge, we have this edge, and we have this edge. Now the smallest among these is the edge with weight 18, but if we add that, we get a cycle. Right? So this is not a good edge to add. So therefore we must add one of the other two. Again, we pick the smaller one, which in this case is the edge labeled with weight 20. So then we get this tree, which has now this shape. Right? So this is our given tree. Now we can't add this, we know. So we can either add the edge 70 or the edge labeled with weight 8. And obviously 8 is smaller. So finally we add that, and this is the tree that we get. Right? So this is the final tree that we get from Prim's algorithm by starting with the smallest edge and incrementally growing the tree. The other strategy we said was to start with the edges in ascending order. So we start with the edges with 8, then 8, then so we have, this is the first one, this is the second one, then this is the third one, and so on. So we consider the edges in this order: 1, 2, 3, 4, 5, and 6. Right? So we have the weights 18, 20, and then finally 70. So we have these 6 edges, and we consider them in this order. So among these, of course, the smallest is 6, so we add that. So this is the start of our tree. Now the next one is 8, and that doesn't form a cycle. It doesn't violate a tree property. So we add that. So notice now the crucial difference between Prim's and Kruskal's algorithm. At this point, we don't have a tree. We have two separate trees in some sense, or we have two different acyclic components within this graph, which are not connected to each other, but we are just going in order of edges. So next we see that 10 is the next edge that we can add. It doesn't form a cycle, so we add that. So in some sense, we have grown this component and left that component alone. Now the next one would be 18, but if we add 18, it would form a cycle. So we skip 18, we move to the next one, which is 20. 20 is fine, and 20 will in fact connect the two components and form a tree. So we add 20, and now we are done because we have added n minus 1 edges. There are 5 vertices, we have added 4 edges, and therefore we have definitely got a tree. So we are looking at the problem of constructing a minimum cost spanning tree in a weighted graph. We said there were two basic strategies one could think of to do this. The first one leads to an algorithm called Prim's algorithm, and the second one to an algorithm called Kruskal's algorithm. So in this lecture, we will look at Prim's algorithm. So the problem domain is the following. We have a weighted undirected graph. So V is the set of vertices, A is the set of edges, and W is the weight function. We assume that G is connected. Because if G is not connected, then there is no way to build a spanning tree. A spanning tree, remember, is a subset of the edges which connects all the vertices in G. So if G is originally not connected, then there's no way we can actually connect it using a subset of edges. So G is a connected, weighted, undirected graph. And now we want to identify a spanning tree with minimum weight. So the strategy in Prim's algorithm is start with a minimum cost edge and keep extending the tree with the smallest edge connected to the current tree. So here is a kind of high level version of Prim's algorithm. Right? So we start with the minimum cost edge and we add it to the list. So TE is a list of edges that form the tree. So we will describe the tree as a collection of edges. And then we note that we have added I and j to the tree. So I and j are now connected. So this leaves n minus 2 vertices which have to be connected. So we have to do something n minus 2 times. So at n minus 2 times we have to add an edge. Each time we add an edge, one more vertex will be connected. So we know that after that many edges, we will have a tree. Remember that a tree has totally n minus 1 edges. So we have added the first edge by starting with the minimum cost edge. So we can add n minus 2 more. So what do we do? N minus 2 times we choose the smallest edge which has one endpoint in the tree and one endpoint outside the tree. Right? So this is a vertex V now which is not connected to the tree, so we connect it. So we append this this new edge to our list of tree edges, and we add this vertex to our list of tree vertices. And at the end, after doing this n minus 2 times, the claim is that we have connected all the edges and we have a spanning tree. And moreover, the claim is because we are choosing the minimum cost edge to add at each point, the overall thing is a minimum cost spanning tree. Of course, we will have to prove all this, but this is what the aim is of Prim's algorithm. Right? So why do we need to prove something? Well, you can see that like Dijkstra's algorithm, Prim's algorithm is a greedy algorithm. Right? At each point, we have to decide how to extend the tree. So we look in the neighborhood of the current tree, we look for the nearest vertex which is connected to the tree by the shortest edge, and we add it. So this is a local choice. And then we keep making this sequence of local choices, and ultimately we arrive globally at a spanning tree, and our claim is that globally we have built the best possible tree. Right? So this is always an example of a greedy algorithm where you make a sequence of local choices, never go back and reconsider them, and finally achieve a global optimum. And very often, as we mentioned before with Dijkstra's algorithm, such a strategy may not give you the right thing, so you have to always justify that this works. So in order to prove Prim's algorithm correct, and indeed we will also use this to prove Kruskal's algorithm correct later on, we prove a very useful lemma called the minimum separator lemma. So let's assume that we have this weighted undirected graph and we look at the set of vertices B, right? And we assume that it is divided into two parts. Right? So it's called partitioning. So there are two separate disjoint parts which I will call U and W. Okay? And I'm assuming that both of these are non-empty. So there's at least one vertex in U, there's at least one vertex in W. Now let me look at the smallest edge which goes across this partition. Okay? Now remember that the whole graph is connected. So there must be a way to go from U to W. So among all the ways I can go from U to W, let me check the smallest edge. Let me call the endpoints small u and small w. So now the claim is that every minimum cost spanning tree must include this edge. Okay? This is a very powerful claim. Of course, there is a side condition which is that we are assuming for the moment that no two edges have the same weight. We will see later on how we will relax this condition. Right? So under the condition that no two edges have the same weight, the minimum separator lemma says that whenever you separate V into two parts which are not empty, then the smallest edge connecting these two parts must lie in every spanning tree, every minimum cost spanning tree. So now why is this the case? So let's assume that we have these two parts. So I will draw one part as say this yellow thing. So let's call this U, and the rest which I have not drawn a boundary for. So this is B. So this is W. Okay. So now let's look at the smallest edge connecting U and W. Right. So now the claim is that this must be in every minimum cost spanning tree. So suppose it is not. Okay. So then suppose there must be some minimum cost spanning tree, because we know that the graph is connected, so there are many spanning trees, and let's assume that there is a minimum cost spanning tree T, okay, which does not include this edge. So in that tree, U must be connected to W, because any spanning tree connects all the vertices. So there is a red path from U to W in my hypothetical spanning tree T, which does not include this edge. Okay. So now the claim is, if I take that particular tree and then I remove the edge U prime V prime and replace it by the edge U V, I get a new tree, right? I get a tree T prime. So T prime is T minus the edge U prime V prime plus the edge U V. But now, by assumption, U V was the smallest vertex, smallest weight edge going from inside U to outside U. Right? So therefore, U V has weight strictly less than U prime V prime. Therefore, T prime has a weight strictly less than T, and you can check that everything else is connected, right? Because any things which are connected, so U prime is now connected to V prime through this long thing, and therefore all other vertices which are connected by T remain connected in T prime. Therefore, T prime is a valid spanning tree. It is of smaller cost, and therefore T could not have been a minimum cost spanning tree. Right? So this is our proof that the smallest cost edge from inside the partition to outside the partition must lie in every minimum cost spanning tree. Now before we move ahead, I just want to make one small remark. So we have to be careful when we prove this lemma a little bit. So it is true that there are, among all the edges going from inside to outside, UV is the smallest one. So one might be tempted to just say, okay, so UV is the smallest one, pick any edge in my given tree T prime, given tree T which goes from inside to outside, and replace it. So for instance, we might accidentally pick up this edge and replace it with this edge. But notice that if I pick up this edge and replace it with this edge, then perhaps there is no other way to get to V double prime, right? So it is very crucial that we choose the correct edge to replace. So we have a target edge, we want to introduce U to V. Therefore, we must follow the path in T from U to V. And that path must start inside and go outside, so it must cross the boundary somewhere. And this is the edge to replace. Okay, so we should not make the mistake of replacing some arbitrary edge. We must replace that edge which allows us to go from U to V in the tree, hypothetical tree, in order to make the new tree. So once we have this lemma, the correctness of Prim's algorithm is very obvious. So at every stage, remember in Prim's algorithm, we have built this tree TV which consists of a few edges, and then we have everything that's lying outside. And now among these, we want to connect one of them. Right? So if we think of this set, the set inside is my U and the set outside is my W. And we are picking, by assumption in Prim's algorithm, the smallest weight edge which connects U to W. By this minimum separator lemma, this edge must lie in every spanning tree. So the algorithm that Prim's algorithm, the edge that Prim's algorithm picks is in fact the edge that the lemma forces us to pick. So therefore Prim's algorithm is definitely correct. So in fact we can use the lemma to make Prim's algorithm a little more relaxed. Recall that in our original formulation we started with the smallest edge. Okay. But now it's easy to see that if I take any vertex, right, and I look at all the edges going out of it, then I can take U to be the vertex itself, and I can take W to be everything else, the set minus this vertex. Then I know that the smallest edge which goes from V to this set must be in every spanning tree. So in other words, if I start at any vertex and look at the smallest edge attached to it, I can start with that because that must be in every spanning tree by the minimum separator level. So this gives us the following algorithm for Prim's strategy. So we start with any vertex S. Okay. Now for each vertex which is not in our current set of tree vertices, we maintain the smallest edge weight from that vertex to some tree vertex. So we call that distance of V. And we also, because we want to build up the tree as a set of edges, we also remember where that edge goes to. So we remember it as a neighbor. Right? So if I have some tree at any given point, and I know that for this V, this neighbor U is the smallest edge connecting it to V, then here I will keep its distance as the weight of the edge, and I will keep its neighbor as U. This will allow me to keep track of which edges I'm adding. So now at every stage I look for the smallest vertex which is outside in terms of the distance. Okay, then I add it to the set and I update its neighbors' distances and values. Right? So this is very similar to Dijkstra's algorithm. Right? The only thing is the update of the distance doesn't involve adding the my distance plus the weight. It only involves considering the weight. So when we see the algorithm itself, you will see the parallel to Dijkstra's algorithm even more clearly. So here is the final algorithm for Prim's shortest minimum cost spanning tree. Right? So you initialize all vertices to be unvisited. This is the burnt thing. We initialize them all to have no neighbors because nothing is in the tree, so they have no neighbors in the tree, and they are all at distance infinity. This is initialization. Now I pick some initial starting vertex, say 1, and I mark it to be visited, but I don't have any edges yet. Right? So now for each edge going out of 1, I update its status. So I say for every edge 1 of the form 1 comma j. Okay? So I say that the neighbor of j in the tree, so the tree now consists of just this one vertex. It's a trivial tree which has one vertex and therefore 1 minus 1, 0 edges. Right? So the neighbor of j is 1 because that's its connection, and the distance is the weight of this edge. Right? So this is my first thing. Now I have to add the remaining n minus 1 edges to my tree. So n minus 1 times I do what you would do in Dijkstra's algorithm in a different format. You pick that u which is not visited and whose distance is minimum. Mark it as visited. Now you know how it is connected to the tree. So you add that edge to my, so you add the edge which tells us how it's connected. U and the neighbor of u. This edge we add to the tree set of tree edges. Now for every edge out of u whose neighbor is not visited, if the current distance to the tree is more than the weight of this edge. So basically I have now added this u and there is another vertex v and it claims to be connected somewhere else. Right? So maybe this distance d and this distance d prime, okay, suppose d is bigger than d prime. Then now that this is in the tree, now that u has been added to the tree, now v is connected by a smaller edge to the tree. Right? So if the distance that I currently have for v is bigger than the weight of the uv edge, then I will replace that weight by the weight of the uv edge and I will say the neighbor of v is now u. So that when I add v to the tree, I will add the edge uv. So this is exactly what Dijkstra's algorithm does, except for this update. Okay, in this update we add d of u plus the weight of u. Right? So in Dijkstra's algorithm we want the cumulative distance. Here we want the one-step distance from the nearest node in the tree. But otherwise, Prim's algorithm is basically a restatement of Dijkstra's algorithm with a different update function. And additionally, we have this thing that we could have done it in Dijkstra also. We could have maintained in Dijkstra's algorithm the path. Right? So had we maintained the path, it will be exactly like this neighbor relation here. We want to know when each edge is added to my shortest path set, the burnt set, why it was added. Right? So here we are doing that. We are adding it. We are also remembering the edge through which it was added. So let's try and execute it before we do a complexity analysis of this thing. So remember, we can start anywhere. So let's start at 1. Right? So we start at 1 and we mark our tree consisting of 1. Now since this edge starts at 1, we have to update the values of the neighbors of 1, namely 3 and 2. Okay? So we mark for 3, we say that its distance, which we mark in green, to the tree is 18 because the tree consists of only the vertex 1 and its neighbor in the tree which is at this distance is the vertex 1. Similarly, the other neighbor of 1 is 2, so we will say that its distance is 10 and its neighbor is 1. Right? Now so everywhere else I have not mentioned it explicitly, but everywhere else the values are -1 and infinity and -1. So we say the distance is infinity and the neighbor is -1. Right? So this is the default value. So wherever the default value is present, we will just leave it out, indicating that the value is effectively not been set yet. We know it's a connected graph, so we will eventually set it, so we don't have to worry about it. But in this illustration, we will just leave it out. So we have these two candidates now, which are not visited and which have some reasonable distance associated. So we will pick the smaller of the two. So we'll pick the one which says 10, and therefore at our next step, we visit the vertex 2 and we add this edge 1, 2 to our tree. Now having added 2, we have to do this update. So we look at the neighbors of 2. So the neighbors of 2 are the vertex 3 and the vertex 5. So for the vertex 2, from 2 we have a new distance 6. So if we go by our 2, the distance of 3 to the tree is only 6, and then it would be connected to 2, which is 6 is smaller than 18. Right? So 18 was our earlier best estimate of how far 3 was from the tree. So now we will replace 18, 1 by 6, 2, indicating now the vertex 3 is 6 distance away from the tree, and if it were to be connected at that distance, it would be connected to 2. Similarly, 5, which was earlier unlabeled, now becomes labeled as 22, indicating that it is at distance 20 from the tree, and its neighbor in the tree, the nearest neighbor, is the vertex 2. Now again we pick the smaller of the two, so we'll pick this vertex 3 to add to the tree, right? And once we add it, we will update the status of 4 because that's the only new neighbor. We don't update the status of 1 because 1 has already been added to the tree. We only look at those neighbors of 3 which are not visited. So now 4 gets the distance 70 with a neighbor 3. Okay. Then among these two, now 20 is smaller than 70. So we will add 5 to our tree, and then we will update the status of 6 and 7. So 6 is now a distance 10 with neighbor 5. 7 is also a distance 10 with neighbor 5. Now we have two vertices with distance 10. We could pick either one. Okay, so let's, for example, pick 7. So if we pick 7, then we add it to the tree, and now we update the status of 6. Earlier it was at distance 10 with neighbor 5, but now it's at distance 5 with neighbor 6. So we reduce its with neighbor 7, so we reduce its distance, and we change its neighbor. Now among 5 and 70, we have 6 as the vertex 6 as the nearer one, so we add that, and finally we add 4, and this is the tree that we get. Okay, so this is how Prim's algorithm works. It is very similar to Dijkstra in principle, but it uses a very different update function. So the complexity is also similar to Dijkstra's algorithm. We have an outer loop which runs n times, order n times, because we have to add n-1 edges to form the tree. And at each iteration, we add one vertex to the tree. Now there is this order n scan in order to find the minimum cost vertex to add. So we already saw that this is a bottleneck in Dijkstra's algorithm also, to find the minimum distance vertex to add. And then when we add a vertex, we have to do again a scan to update all the entries. So if we have an adjacency matrix, this will again take order n time, and therefore overall it takes order n square. So exactly as in Dijkstra's algorithm, moving from an adjacency matrix to adjacency list representation of the edges allows us to reduce the complexity of the updates. So across the n iterations, we do a total of order m updates because we update only according to the neighbors, the sum of the degrees of all the vertices. However, in order to bring it down from order n square, we also need to be able to compute the minimum distance efficiently, for which we need a heap, right? So once we have a heap, which we will examine in a later lecture, the claim is we can find the minimum and update the distance information in log n time. So then this gives us overall this complexity exactly like Dijkstra of n log n plus m log n. So this comes from the finding the minimum, because n times we have to find the minimum, and this comes from the updates because we have to do m updates overall. Each update takes log n times, so we get m plus n log n exactly as we did for Dijkstra's algorithm. So one last point before we leave Prim's algorithm. Remember that in our correctness, we had used the minimum separator lemma, in which we had assumed that edge weights are distinct. So of course, as we have seen even in the example that we executed, we could have edges, multiple edges with the same weight. So how do we deal with this in the lemma? Well, we could argue that we can make the cost to be not just exactly the weight, but the weight plus some other component. So in general, we could say that we fix an overall ordering of the edges. There are m edges, so we just number the edges arbitrarily 1 to m. And we say that one edge is smaller than another. It has a smaller weight if either the weight is actually smaller or the weights are equal, but the index in this ordering is smaller. Right? So with E and F, we have the weight of uv and the weight of u prime v prime, but we also have this index I and j. So this is some I between 1 to m, this is some j between 1 to m. So either the weight of E must be smaller than the weight of F, or the weights are equal, then I must be smaller than j. Right? So this gives us a tie-breaking rule. So this will now basically tell us that we can always compare two edges and declare one is smaller than the other, and what Prim's algorithm will do is pick the smaller of the two. Right? So what this corresponds to saying is that we are actually giving a strategy for choosing when we have two equal things. So the algorithm says choose a u such that distance is minimum, and if there are multiple u's with the same minimum distance, we pick an arbitrary one. So what does it mean to pick an arbitrary one? Well, it means in some sense to choose an order among them and go in that order. Right? So if we choose different orderings, then we'll get different trees. So therefore, if we have multiple edges in a tree which have the same weight, in general we may not get a unique spanning tree. In fact, you can check if you have all weights the same, for example, that basically you can have keep adding or dropping different edges and you will have an exponential number of trees. Okay, because an edge could be there in one tree, may not be there in another tree, and so on. Right? So overall, the number of possible minimum cost spanning trees could be very large. What Prim's algorithm does, and what Kruskal also will do when we look at it in our next lecture, is to use a greedy strategy to efficiently pick out one of these possible things. Now, if the edge weights are unique, there is not much choice. You have to pick out the same tree, but if the edge weights are duplicated, you can definitely have multiple trees. And this strategy of picking out the smallest one at each stage will give us a quick way to identify one of the smallest ones, but not a unique one. So we have seen one algorithm for the minimum cost spanning tree, namely Prim's algorithm. Now look at the other. Let's look at the other strategy we talked about, namely Kruskal's algorithm. Right. So we are looking for a minimum cost spanning tree in a weighted undirected graph. So Prim's algorithm starts with some edge and gradually expands the edge into a tree, whereas Kruskal's algorithm follows the other strategy, which is to order all the edges in ascending order of weight. So it keeps trying edges from smallest to largest, and for every edge, if it can add the edge without violating a tree property, it adds it. Now in the process of adding the edge, it may not actually construct a tree. All it makes sure it doesn't violate the tree property, namely it doesn't produce a cycle. So if we keep adding edges so long as they don't produce cycles, and at the end the claim is we get a minimum cost spanning tree. So here is a kind of high level view of the algorithm. So let the edges be sorted in order E1 to EM. So we start with an empty tree. Right? So again we will keep the tree as a list of edges, and now we are going to scan this in order 1 to m. So let I be the index of the edge to be tried next. Right? So long as we have not yet added n-1 edges, remember that if we add n-1 edges and we have a connected graph, it must be a tree. Right? This was one of the various characterizations that we said about trees. Trees have n-1 edges, but any connected graph with n-1 edges must be a tree. So once we have n-1 edges, we can stop. So long as the length of the tree in terms of number of edges is not n-1, we have to add some more edges. So we look at the next EI. If EI does not form a cycle when added to TE, we append it. And then we look at I plus 1. If it does form a cycle, we just discard it and go ahead. Right? This is all Kruskal's algorithm. It's scanning through all the edges, and until we have formed a tree, it will just keep looking at each edge in turn in ascending order of the weight. And every time if it can add it, if without forming a cycle, it will add it. If it cannot add it without forming a cycle, it will drop it. So let's look at the same example that we saw for Prim's algorithm. So here the smallest edge weight, so remember that we have sorted it in edges. So 5 is the smallest, then 6, then we have 3 of weight 10, then we have 18, then we have 20, and then we have 70. Okay. So now if we pick among these the smallest one, we start with the edge 5. So we first add the edge 5 to our tree. Now the next one is 6, so we add 6 to our tree. Now we have to pick one of the edges labeled 10. We can pick any one. So let's assume that we pick this one. Okay. Now we want to pick another edge labeled 10 because the next two edges are again labeled 10. So supposing we pick this edge labeled 10. Okay. Then this edge labeled 10 forms a cycle. So we cannot add it. So we discard it. So we discard it and go to the next one. So now we pick this one. So we'll throw this away. Right? And now we'll go to this one. And now this one we can add. So now we have finished the 10s, so the next one is 18, but again adding 18 is going to form a cycle. Right? So we discard it, and now we go to the next one, which is this 20. Okay? Now having added 20, then we still are not done because we have still to add enough edges. We have 1, 2, 3, 4, 5 edges, and we need 6 because we have 7 vertices totally. We need n-1 edges. So the only edge left is the 70, so we add that, and now we are done. Right? So this is the spanning tree formed by Kruskal's algorithm. We actually scanned through all the edges in this particular case, and on the way we dropped a couple of them. Right? So Kruskal's algorithm is also a greedy algorithm. In this case, we don't make so in Prim's algorithm or in Dijkstra's algorithm, we make incremental choices, local choices. At every point, we look at what to do next based on what we know now. Here we make a choice well in advance. We say right at the beginning, let us sort all the edges and do it in that order. And again, it is not clear why doing it in this particular order, which is decided right at the beginning, gives us overall an optimum solution. So once again, we will use the same result that we use for Prim's algorithm, this minimum separator lemma. So recall what the lemma said. It said that if we take a set, our set of vertices, and separate out into two non-empty groups U and W, and if we take the smallest edge, now the graph is connected, so there must be an edge connecting these two. If we take the smallest edge which connects the two parts together, then this edge must be there in every spanning tree, every minimum cost spanning tree. Right? This is what the lemma said. Okay. So now, in Kruskal's algorithm, unlike in Prim's algorithm, okay, at the intermediate stages, we don't have a tree. We just have a collection of components. So we will have, in our overall graph, we'll have some vertices which are connected here, then maybe some other vertex there, and then another part there, and so on. Because as we add edges, it just connects them. Okay? And now whenever we add an edge in general, it will take two currently different components and connect them. We can't add an edge within a component because each component is like a tree. So adding an edge in a tree, remember, forms a cycle, right? So this won't happen. What we will do is we will add edges across, right? So this is the strategy of Kruskal's thing. Now, what we therefore know is that whenever we add an edge, okay, its two endpoints are in disjoint components. So in terms of using the lemma, let us call capital U to be the component containing one endpoint of the edge, and capital W to be the rest, okay, whatever is outside this. So this is whatever is outside component, right? So we have U and whatever it is connected to. So this is my set U, and then I have the rest of the vertices. So U is connected at this point to something in a different component, but that and all the other components is what I will call W. Okay? So now what do we know? This is the first time that we are trying to connect U to V. U to V have not been connected so far, but we have been looking at edges in ascending order of weight. So if we look at all the edges, so this current edge we have called EJ, right? So if we look at all the edges E1 to EJ minus 1, none of them connected U to V, or the component connecting U, because had it connected the component connecting U to the component containing U to the component containing V, then we wouldn't be adding this edge. This edge would form a cycle. So this is the first edge that we can use to connect these two. Moves that no edge we have seen so far connects these two. Okay, so putting all this together, this is the smallest edge which connects capital U to something outside capital U. Right? And since this is the smallest edge, the lemma tells us this must be in the tree, and therefore Kruskal's idea of including this in the tree is sound. Right? This is an edge which must be in the tree. So every edge that Kruskal's algorithm adds is actually a valid edge justified by the minimum separating lemma. So now we have to just decide how to keep track of this property of forming a cycle. Remember that whenever we add an edge, we must first check if it forms a cycle, and if it doesn't form a cycle, we must include it. Right? So the easiest way to check that the edge doesn't form a cycle is to keep track of the components. If the edge is incident on two different components, that is one endpoint of the edge is in one component and one endpoint of the edge is in the other component, then inductively each component is a tree, and therefore these two trees are disjoint, and therefore the new edge doesn't form a cycle. If the two endpoints are in the same component, then it will form a cycle. Okay? So keeping track of whether or not a new edge forms a cycle is equivalent to keeping track of components. So how do we keep track of components? Well, we can basically label the components by numbers, and since we have n vertices and initially they are all n independent vertices with no edges in the initial starting point of Kruskal's algorithm, everything is disconnected. So initially we have n vertices, n components. The most natural thing to do is say that each vertex I belongs to a component called I. Now I can add an edge UV if the component of U is different from the component of V. Okay? And if the component U is different from component of V, what happens after this is the two components become the same. So I have to somehow merge the two components. In other words, I have to give them the same label. Right? So this is now a detailed explanation of the algorithm. So as before, we let E1 to EM be the edges sorted by weight. Now initially we say that every vertex 1 to n is in its own component. For every j in 1 to n, component of j is j. So 1 is in component 1, 2 is in component 2, and so on. Now we start off with an empty set of edges, right? And now we are going to run through, as we said before, these edges in ascending order. So we have the index pointing to the first edge in my sorted array. So this is my index. So long as we have not added n minus 1 edges, we look at the ith edge in this sorted order. It is of some u to v. If the current component of u is different from the current component of v, then we are sure that the edge ei does not form a cycle. So we add it to our tree, right? And now we have to do this merging of components. Now what is the component of a vertex? It's just a number. So for every j in our set, now the problem is that these components could have been merged earlier. So component of u could contain other vertices, component of v could contain other vertices, and all of them must now be given the same component number so that they're all in the same component. So I have no choice but to scan every j in my set of vertices, and whenever such a j has the same component as v, I reset its component to u. Okay. So after this, everything which has the same component number as v has got the same component number as u. So therefore, effectively, the two components have been merged into one component, all labeled by the value component of u. Right? So this is Kruskal's algorithm. It just says keep considering edges, and if they connect different components, add them and merge the components. If they don't connect different components, it will form a loop, so just throw it away. So what is the complexity? Well, the first step in Kruskal's algorithm requires us to sort the edges. So we know that we can sort m edges in m log m time. But m is at most n squared. Okay, so log m will be 2 times log n. Right? So order of log m is the same as order of log n. So I can also write this as m log n. Okay, so this will be it's just another way of writing this. So the sorting takes m log n time. Now we have an outer loop. Okay, so this loop which runs here in general runs through all the edges in this list, because it could very well be that for some reason I have to go all the way and only the last one forms a tree. Okay, even in the example we saw, the largest edge has to be included in the tree because it's the only one that connects us to some particular vertex. So we have an outer loop which runs m times. Now among these m times, okay, we will update the components for each edge we add. That will happen only n minus 1 times. Right? But when we update the component, that's when we have a problem, because we have to scan through all the vertices in order to change the component number. So each update of the component, each merging component step takes order n time, and this itself happens n minus 1 times, because we have to keep doing it each time we add an edge to our tree. And there are going to be exactly n minus 1 edges. So we have n minus 1 updates. Okay, and each update takes order n times. So we have an overall complexity of order n square. Okay. Now remember that in Prim's algorithm, n square was the worst case, and then we said with a better data structure we could bring it down to m plus n log n. So what can we do here? So let's look at the problem. Okay. The problem is basically this labeling strategy. Okay. Now when we label the components and do this linear scan, we are spending order n time in order to merge components. So we'll find, just like we can use a heap for Dijkstra's algorithm and Prim's algorithm to find the minimum vertex to be added quicker and to update the distances. Here we will find that what we need to do is maintain this component structure. Okay? So assume that we want to deal with a set V which is broken up into different components. Right? So it has components at any given time, say called A, B, C, D, E. And then you have individual elements which belong to these components. So some of them have many, some of them have one, and so on. So one of the things we want to do is, given the name of a vertex V, we want to ask which component does it belong to. Okay, so this is called find. Okay, given V, find the component containing V. The other thing is, given two vertices, supposing I'm given a U and a V, we will say merge these two. Okay, so take these two components and give them the same name. Right? So either call them all C or call them all D. Right? So this is called union. Okay, so union doesn't take the components, it takes two representatives, one representative from one component, one representative from the other component, and then says merge everything which is in the component of U with everything in the component of V. And these are the two operations obviously that we do in Kruskal. Right? Find V is what we, if we have an edge UV, right, to check if they're the same component, we find the component of U, find the component of V. If they are the same, that means they're in the same component. If they're different, they're in different components, and we can add this edge. Now if we add the edge, then we have to do union UV. Right? So these are precisely the two operations, and we will find that there is this data structure which is called union find because of these two operations, which can actually do this efficiently. And efficiently means what? It means it can eliminate this n squared thing and bring everything down to the cost of m log n. Now remember that this we need to sort. Right? So our first step was to sort the edges. So Kruskal's algorithm starts by sorting the edges. So m log n is something which we need to do anyway to sort the edges. In addition, these essentially this updates as in a heap, the updates to this union find will give us is actually log n. And remember that there are going to be these updates are happening in this iterative loop. So we'll actually get something similar to this Prim's algorithm complexity.